Good morning, one and all. I welcome you to the third day of this value-added workshop on smart nanotechnology in societal applications. Now, I request Ms. Monica Jaiswal to take over and coordinate the session.
Good morning to one and all gathered here. It gives me immense pleasure to extend you a very warm welcome to the third day of value-added workshop on smart nanotechnology for societal applications, coordinated by Dr. Richa Krishna. Without any delay, let us start this informative session with brilliant speakers who have expertise and contributed their whole career in this field. To start with, we are honored to have Dr. P.K. Bhatnagar today with us. Dr. Bhatnagar received his PhD in metal oxide semiconductor solar cells in 1980, then worked as research associate. He joined as associate professor in 1985 and became professor in 1995. He worked as chairperson during 2000 to 2003 and then 2012 to 2014. Presently, he is UGC BSR Fellow and Faculty Fellow in Department of Electronic Science at University of Delhi. Dr. Bhatnagar research work is documented in 96 publications in peer-reviewed high-impact factor research journals and conference proceedings. Let us invite Dr. Bhatnagar with a warm welcome to enlighten us today on his today's talk, which is Science and Technology of some Nanomaterials for their role on well-being of society. Sir, I humbly request you to conclude your talk in 45 to 15 minutes, followed by 10 to 15 minutes question answer session.
Okay, so
platform is yours.
I'm trying to share the screen now. What is happening? Okay, just a moment. Share. This will stop other screen sharing. Do you want to continue? What should I do? This will stop screen sharing. Are you seeing my screen?
We can see your screen, sir.
Yes, sir, it is visible, sir.
So should I put yes or no? This will stop others screen sharing. Do you want to continue? I should say yes, yes. Let me see. Okay, now you can see it. Fine?
Yes.
Yes.
Okay, sir, please come. Yes, absolutely fine, sir.
Okay,
First slide is visible.
Okay, right. Now I start, with my talk. First of all, I would like to thank the organizers of this very important meeting, and the theme being smart nanotechnology for societal applications. Very timely theme. I'm not spending more than a minute on this. First, the theme is so important that everybody is looking into this. In 2007, the Department of Science and Technology established Nano Mission, and since then it is continuing. So now everything is becoming very, very smart nowadays. In earlier days, people were smart. Now the devices are becoming smart. So I will come to that also. So my main aim will be impact of nanomaterials, nanoscience and nanotechnology on society in general, some applications and hazards. Some important points I'm just giving you, and then nanomaterials and some of their applications in electronic devices and biosensors. That will be the part of the talk. Now, I'll be discussing only those devices with which I have worked in my laboratory. A number of devices which include solar cells, light emitting diode, quantum dots, graphene-related devices, and many more. So I will take a few as an example, and I will tell you how these devices make an impact on the behavior of the persons in the society, because it's mainly societal applications. And if I would like to mention that in a society, everybody wants basic 4 or 5 things, which are good food, clean water, clean environment, then he needs everything clean. So clean in the sense which are good for the health of the persons. I would like to mention here, when we talk of the smart material, what smart means. Smart means self-monitoring analysis and reporting technology. So it is used to provide cognitive awareness of objects. So a person is making logical conclusions, and on the basis of here the device is making logical conclusions, and it is conveying those, or it is communicating with other devices. So that is the smart technology. You must have heard smart meters are there for electricity. So a number of examples are there. Now today, in today's talk, it will be partly technical, and partly it will be telling you about what are the various applications of the smart technology. Technical part is also important, and the social part is also important in this case. Now, in the smart technology, we can say that nanotechnology is being used. What is the role of nano? So I would like to just mention in 5 minutes what are nanomaterials, what is nanoscience, and what is nanotechnology. It's all for the security, health, and control problems. So examples, as I told you, smartphones are there, smart cars are there, smart electronic meters are there. So a number of devices are there which are smart. They can communicate. They can use the system of fuzzy logic, or they can use the system of various electronic controls. You have smart refrigerators, you have smart washing machines, smart glasses, smart everything go to things which is smart, which is communicating of its own. You can have a CCD camera in your house, and you can see sitting here at MET that what is going on in the particular part of the house. So that is the smart technology, and this technology can be able to talk back to us and even guide us. Now I will take you to the small and beautiful world of nano. So nano, is now is the most commonly used word, and in every walk of life, I think the nano is coming into picture. So smaller is the smaller and beautiful is more beautiful. It's more handy. It's more effective. So the devices are being made which are nano. So what happened in 1959? This era started in 1959 when Richard Feynman gave a lecture, and he gave a very important point that the principles of physics, as far as I can see, do not speak against the possibility of maneuvering things atom by atom. So maneuvering things atom by atom is nothing but nanotechnology. He said in 1959, published in 60, which is coming true now. Many years before, I saw a movie in which a doctor is entering in the body of the person, treating the person and coming out. Now the same purpose is being done by the nanotechnology. You must have heard drug delivery, targeted drug delivery. So no doctor has to go in, but the drug is going through some means, through some nanoparticles, and it is being targeted to the point, mainly it is for the cancer patients. So I would like to mention here that if we go from bulk to nanoscience, nanotechnology, so most of you must have heard that we have three-dimensional materials, which is the bulk, then 3-dimension to 2-dimension. If we reduce 1 dimension, then it becomes 2-dimension. When we reduce means we are saying that technically we are saying that we are putting an infinite barrier, potential barrier in that direction, in one direction, so that it becomes 2D. Now, if we bring it to 1D, then what we are doing, it is reducing in 2 dimensions, means we are putting infinite potential barrier in 2 dimensions, remaining is 1 dimension. And if we apply the infinite potential barrier to in all the direction, if you take a particle in a box, and if you apply infinite potential barrier in all the dimension, then we call it 0 dimension, or sometimes we call it as quantum dot also. So this is how we are saying here that it's very important to know about. There's one more thing before I forget. Everybody says that when you reduce the size of the particle, the surface area increases. This statement is partly correct. Everybody has, those who say that complete statement, and this is not for them, but for the students and for the undergraduate students or new researchers, I would like to say that when the size of the particle is reduced, the surface to volume ratio is more important. Surface to volume ratio is reduced. I would like to bring everything connect to the kitchen. I will make the device using similarity with the preparation of a recipe in the kitchen. And you will really appreciate it when I'll be going for really making of the devices like solar cells or light emitting diodes or DNA sensor or something like that, or quantum dots. So I would like to mention here why I am doing it, or taking this similarity with what you are doing in the kitchen. Now, it is a timeline. I do not know if it is very clear or not, but right from 1900, the work started until date it is continuing. So we are going from bulk level to micro level, millimeter, then micrometer, then you go to the nanometer, then picometer. So the size is being reduced And not only size is being reduced, but at the same time, the efficiency of the material of the device improves. That is the beauty of the things. So when you reduce the size of the material, what happens? Why we need nanotechnology at all? See, in earlier days, I'll come to a transparency later, that when we are talking of the material, I'm not saying about what I'm going to say in the present talk. I have already told you, but I'm going to tell you that this is a, you know, many people should have shown you this type of thing, that you have the microwaves, then you have the paper, you have the red cells, and until and to the end you have CC bonds. Bond length 0.1 nanometer. This is how we can say the scale is moving, and a two-dimensional can be compared with a paper, a three-dimensional can be compared by a small thin rod, and a quantum dot can be compared by a small dot. So these are the various things which we have to keep in mind, and we use these nanomaterials, means quantum dots, carbon nanotube, many more, graphene, phosphorine, fullerene, germanium, in nanoform. These are the two-dimensional. When I talk of the germanium, phosphorine, silicene, graphene, I'm talking of two-dimensional material. And there we come across the quantum wells. If it is one-dimensional, we say carbon nanotube, because it is one-dimensional. And if it is zero dimension, it's not exactly zero, but we call it zero dimension, because the dimensions are very small. We call it quantum dots. So when we talk of these materials, some of the familiar materials which you should have also heard are the metals, silver and gold nanoparticles. They are used in targeted drug delivery. You must have heard about the graphene, silicon nanotubes, nanorods. Nanorods are, full, and nanotubes are hollow. Then zinc oxide nanorods, quantum dots, and so on and so forth. So these are used for electronics and optoelectronic devices. Because I was associated with electronic science devices, electronic science department, so my main emphasis will be on physics and electronics of these type of materials and devices. When you want to play with these devices, you don't have anything to measure 500 years back, when there was no SAM, no TAM. You were simply working with these materials, but people were working on this material. It will be very surprising. It's not surprising, I will tell you. These are the materials I have already mentioned to you, and you can make the powders. Everybody should have heard, a lot of things have been said about top, down, and bottom approach. So I'm not going to, again, repeat this thing. So both type of approaches are there. And then nanoscience, as I tell you, that though it is a billionth of a meter, and I have already mentioned that the surface to volume ratio increases. See, if you are cooking a potato in the kitchen, you just go on cutting small pieces. What happens? It's cooked earlier, because a lot of surfaces are now open. Similarly, when we take the nanoparticle, lot of surfaces or big surface, because the surface to volume ratio is increasing. If you take a sphere, what is this surface area? It is 4 pi r square. What is the volume? 4 by 3 pi r cube. You take the ratio, 4 pi r square divided by 4 by 3 pi r cube, you will get 1 by r. So surface to volume ratio is proportional to 1 by r. So if you reduce the radius, in other words, if you reduce the size, so surface to volume ratio will increase. So more and more, surface is open to, you can say, if you want to sense a gas, if you want to sense a vapor, so it's more and more open. And that is how the nanoscience is coming into picture. Now, what is nanotechnology? I had told you about the nanotechnology. Then in the nanotechnology, I would like to say that you have to manipulate materials and the creation of structures which exist in the scale of atom and molecule. There are many materials which can be brought, many chemicals which can be brought into this scale. And when we play with 1 or 2 or 3 or 10 molecules or 10 atoms, their property change drastically. I will tell you that their electronic property, optical property, thermal property, structural property, and whatnot changes with dielectric properties. They all change when you just reduce the size of the material. So now, if we go a little ahead, I have already mentioned you the definition of the nanotechnology. If someone says that 2 to 10, 100 nanometer is nano size, okay, that is okay. But if you say that 10 to 100 nanometer gives you quantum confinement, or 2 to 100 nanometer, or some nanometer gives the quantum confinement, this statement is not correct. I'll correct it, and I'll tell you why this statement is not correct. See, size can be okay, 10 nanometer or 5 nanometer or 50, but quantum confinement will follow. I will tell you later, because quantum confinement is a property which is being used for making many devices. Why I am saying, I am only touching those devices at the moment with which I have worked, and those are used by the persons, the society at large. So how do they make impact on the society? I'll tell you. And then top down, bottom up, I have already mentioned. I am not saying much about these things. So this is a very important slide I am going to show you. You know, in our country, you know, let us say thousands of years, we had Vedas and Purans, and you have many things where the treatment was being done. So you must know, even as on date, use of silver and gold nanoparticles, जिसको आजकल हम कहते हैं भस्म, भस्म are being used. What are nothing? They are nothing but the nanoparticles for treatment of a number of diseases. So if you have seen the sword of Tipu Sultan, what was used? Perhaps they must have used the nanoparticles without knowing that they are using nanoparticles, because there was no means to measure that the particles that they are using are nanoparticles. You must have seen something near Qutub Minar, the pole which is not rusting. They should have used something which is not, which is responsible for not having any rust in that pole. So this is how the nanotechnology is not new. It's very old. About 400 years ago, in Chandni Chowk, people used to make colored glasses. So how did they get colors? So they simply change the size of the material. Then what happens? When you change the size, the color changes. Why the color changes? Because when you change the size to very small size, there is a quantum confinement, the band gap changes, and corresponding to band gap, Eg is equal to h nu or hc by lambda. So lambda changes or color changes. So that is how the things are happening. And this technology, people say that finally it has been concluded in the science and technology that Taniguchi put this name nanotechnology for the first time here, and not Simon. This we have to remember, just for our knowledge purpose. So when we are going for nanomaterials, I'll tell you which properties change. And the property changes in the interest of us. They are useful for us. I'll tell you later. But first of all, I would like to tell you why it is so exciting that material at nanoscale change their all physical, chemical, structural, optical, electrical, thermal, and that can be harnessed for useful applications. And some of the examples of nanomaterials are conducting polymers, DNA, fullerenes, carbon nanotube, and so on and so forth. So this is how, these are the materials with which, in fact, my students have worked. I have worked with the students, and they have done very good research on this. Now, you can see the change in color. If you see the gold, silver nanoparticle, the size is changing. And similarly, gold nanoparticle, the size is changing. Silver, the color also will change. The color is changing. And similarly with gold, the color is this much, and others this much, and like this. So why the color is changing, I already told you. Here there is a plasmonic effect, and in semiconductors, there is a change in band gap. The band gap increases. Why does it increase? Because of the quantum confinement. What is quantum confinement? The energy bands which were lowest of the conduction band and highest of the valence band, that we used to call as band gap. Okay, but now because the energy levels have broken, then we have bigger band gap. I'll show you somewhere. There's a very important thing, you will really like to love it, that what is the importance of quantum interference? If you have not heard this thing, the quantum interference is a phenomenon. Suppose some of you are listening to my talk, and some of you are forcibly sitting there and do not want to be there. So there was no mechanism earlier when you are sitting in the classroom. What you have to do, the teacher is monitoring you. But the quantum mechanics gives you a very good thing that you are sitting in the classroom and you are sitting in the canteen also. See, it's very important. The photon is in two places at the same time. That is the quantum states at the same time. There are two detectors, detector 1 and second detector, detector 2. This is says detector 2 is the classroom and detector 1 is the canteen. So that is the quantum interference. So wonders are being done, and these are used in making quantum computers. You know, all both the states are there. Zero is initially it was 0 or 1. Now it is both 0 and 1. So if you do 0 and 1, what's going to happen? In a classical computer, you had one bit at any time. Either you had 1 or 0, but you have the quantum bit, or you call it qubit. So it is 1 and 0. So if you have to do an operation with n bits, suppose you had n bits and there were 2 to the power n possibilities. You know, 3 bits to the power 3 and 4 bits to the power 4. So this one. And for any operation to complete, you have to do 2 to the power how many cycles? 2 to the power n cycles of operation. That was classical computer. Now, if you go to the quantum computer, because you are using both the bits, all the 2 to the power n possibility, here only one possible, all possible. So here you had to have 2 to the power n cycles, and here you do it only in one cycle. So you see the importance of the quantum computer, how fast it becomes. Only in one go you are doing 2 to the power n calculations. So this all, whatever I'm saying you, it's all itself is a topic. All in itself is 4 to 5 hour talk. But I'm just trying to make you familiar with the things. Now, if you talk of the quantum dots, I mentioned that all the three dimensions are blocked, in the sense you have the infinite potential barrier in all the three dimensions. So the quantum dots are being used in making quantum dot solar cells. They are used in making the DNA testing. I'll come to the DNA testing. I have done some work on DNA testing. Then 3D image making, and you know, quantum dot TV. Samsung is making quantum dot TV now, and some displays are being made, and they are very, very sharp and very, very fine controls are there. Resolution is very, very good. So these type of matter, I'm just giving you, just passing very, very fast about the advantages of the, because all these things, most of the things you will find in it, I mean, internet also, literature also. I'm just passing these and take only those which are used for the societal applications. Now, applications of the nanomaterials are there in nanoelectronics, MEMS and NEMS. MEM was the micro electromechanical system, and NEMS is nano electromechanical system. In your MIT, Dr. B.K. Jain has done a lot of work in this direction when he was in solid state physics laboratory, and we are trying to make, I mean, we are teaching these things in our classes also now. Then there's a nanobiotechnology. See, earlier days there used to be electronics. Then there used to be bioelectronics. Then now nanobioelectronics. So everything is becoming interdisciplinary. A single person knowing physics or chemistry or some single discipline cannot work nowadays. He has or she has to come to all the disciplines, sit together and do a lot of engineering at nanoscale, using biology, using chemistry, using physics. And it is a new department in our South campus. Not new, it's 25-year-old now. Department of Interdisciplinary and Applied Sciences. So interdisciplinary sciences have to be there. Now, lifestyle applications, I can say societal application. People are using cosmetics, sunscreens, water filters, clear filters, inks, stain clothing paints. You have some paints on the wall that the dust does not stay there. It's very, very important why the dust is not coming here. Take an example. You throw a ball on the wall, it comes back. Similarly, if the paint is nanoscale and the dust particle is like a ball, when it goes to the wall, it comes back. Understand? If the ball is painted by the nanoparticles, then it will repel the dust as the ball is being thrown back when it strikes the ball. So these are the various things which are there. And nowadays foldable devices are there, mobile phones are there, foldable displays. You should have seen about 1.5 to 2 lakhs in OLED based mobile phone is coming, where you can fold the display to your pocket and roll it. I'll show you a video also. You have the water shortage problem. you use nanoparticles to pure it. Some people are using silver nanoparticles. Now, surface to volume ratio is also important. Then silver kills the bacteria also. So generally people are working for killing the bacteria of E. coli. I have made some sensors where I have made how to detect E. coli. I'll tell you, I'll keep in mind the time also. So agriculture, people are using nano manures and nano fertilizers for agriculture. And people are using it has not come yet in the market, quantum computer. It is only at a very, very small has come, but it's possible that the computers becomes billions of times faster. So when this comes, all your computers will go and you will have a very, very small computer, maybe at the chip, actually half of your nail. So these things are coming now. And then various living conditions are there. I'm just passing these things now. The technology can be used for various applications. Now, medicine is very, very important. I'll come to the medicine also, because nowadays diagnostics is very important and it is very, very expensive. And diagnostics, unless it is done very carefully, the treatment is not possible. So in many, medical applications, whether it is the medical equipments or whether it's the targeted drug delivery, or it is the medical, you can say a number of drugs, you can say the nanomaterials are being used. They can be used for making lighter, harder, wear resistant, durable, stronger components. Like you see, plastic is very light, but it's not that durable. So if you use the nanotechnology, you can use it for making the wings of the aeroplane or body of the aeroplane. So nanotechnology has made it possible. Similarly, silicon, if you're taking nanoparticle size or nano size, they are very, very useful for offshore applications. So many applications. I can spend a full day on this, and you can say as much as on internet as possible. So don't go on this. I'm just coming to the roadmap, and I've done up to slightly extrapolated before 2020. So this was the roadmap earlier, and the materials and tools, materials now are developing. They are coming very slowly. Tools are coming. What are the tools? I'll tell you: SAM, TEM, and a number of things, photoluminescence measurement system, X-ray diffraction method for these type of materials. Then size and the devices are coming. So now we are in this era of the devices where we are going for new materials and new tools for making the devices. This gives you the technology of making devices, and finding the materials, technology for making the materials, processing the materials, and characterizing the material. Unless you do that, you cannot make use of the technology for making the useful devices. Now, there are smart fluids, there are new sensors, very small in size, very reliable sensors. There are energy applications, very efficient energy conversion can be done. There are very good fuel cells available in the market. Still some work is being used. People are using lithium-ion batteries. Now people are trying to go for sodium-ion batteries, which may one day replace the lithium-ion batteries, which are very, very expensive. And here you use the nanoparticle of 1 to 5 nanometer diameters. I'm not saying anything of quantum confinement. I'm saying the size of the nanoparticle here. Quantum confinement comes when I'm going for the electronic property and optical property of the material. So now there are ultra capacitors, there are nanocatalysts, there are nanoporous filters. I will go to the light emitting diodes because I have worked on this area. And then there's nanofiltration, so many things. These filters are, able to do 99.9999 plus 0% virus can be filtered. So you have the very good nanofilters available. So just repeating it and then going ahead, you can use it for information and communication in communication technology. The problem is when you do go for smaller dimension, I'll tell you the number of problems are coming. Scaling is a big problem. When you reduce the size, the device with which you are working, its property gets changed totally. And now you have to do scaling according to that. The ICs are 50 nanometer, even less. So you have to use now new properties. You have to use new computer programs to account for or analyze the working or predicting the working of the devices. So gate length is reducing every day, and in FET, field effect transistor, and in MOSFET, and this is reduction is not only reducing the size of the device, but it is making them highly efficient because as I told you in the very beginning, reducing the size makes some of the property very useful for the device applications. Then there are some novel devices you must have heard. I don't know whether you've heard about the magnetic resonance or not, or giant magnetic resonance. There's no time to tell about all these things, but giant magnetic resonance is used for making very high memory devices, and it is used for tunneling devices. So you can use it for very high storage density of the hard disks. So it is still going on, and people are working in Singapore, and I've been to that lab also. I've seen the work going on. Then there are nano optical devices, photonic crystals. You must have heard. Those who have not heard, for them the photonic crystals are the materials which, with a periodic variation in refractive index, with a lattice constant, with lattice constant as a function of the wavelength. So these are the materials which are being used, and these are the nanomaterials. Of course, colors change. I have already told you. I'm not going to repeat it. Displays are there. Nanologics are there. Quantum computer I have already mentioned. Diagnostic devices. I'll tell you one diagnostic device which I have made in my laboratory. Drug delivery. All of you know that the silver and gold particles are used as a materials which take the delivery, or which deliver the drug in the body. Then tissue engineering is there. Gas sensors are there, electrochemical sensors are there, optical sensors are, so many go on going. So I'm stopping it here. And when I talk of the sensors, I'll tell you about a DNA sensor also. In all sensors, all the undergraduate students should know, sensor basically is a thing which is sensing something, and you get electrical signal or something in lieu of that. Then it should have four things. It should have a good sensitivity, one. It should have a good selectivity. It should have a good, very small response time, and it should have a small recovery time. The four parameters, they are good. The sensor is really very, very good. So I'll come to that also. And this transparency was shown by Professor Vikram Kumar long back in 2002. And he was expecting that by 2015, this 2015, we'll be going to, 10 nanometer. But now the things are coming much lesser than that. And then if you go beyond that, then as I told you, there are various constants of miniaturization. Tunneling starts happening. You have unwanted mesoscopic effects. You have high electric field. Field is what? V divided by distance. If the distance between the two particles is very small, the field is very, very high. V by small distance. Heat dissipation is there. Lithography is not possible. It was not possible. Optical lithography is not possible, which is used for making patterns on the semiconducting material. Then silicon wall. So these are the problems. Otherwise, the development in nanotechnology would have been very, very high. Although it is not bad, but see, silicon, there was a limitation. There is a silicon wall. If you go less than 15 nanometer, it's not possible to dope silicon. So that is the problem. One thing more I would like to say, whatever things we are eating, I told you four things: food, materials, then water, environment, and agricultural materials, the crops which we eat in the form of wheat or something like that. The nanoparticle should not be more than 50 nanometers there. If it is more than that, our kidney will not be able to filter that. And it will remain in the body, and it will do a lot of toxicity in the body. So I'm saying for all those who are using the materials, nanomaterials in the market, taking from the market, the government has put so many regulations in the research. I'm chairing some NASF, National Agricultural Science Fund, and it has been said that whatever research you are going to do on agricultural products, you have to see, or food products, you have to see that the size should be less than 50 nanometer. Material should not be toxic at all, because it is for human consumption, and nobody wants that the consumption should harm anyone. So these are the various constants, and people are trying to overcome these constants. I have told about this thing about in brief, but now I'll be coming from nano device and solid state device. I'll come to the I've taken names as carbon nanotubes and spin transistors is there, quantum dots are there, then resistance temperature devices are there. Molecular electronics is very important. I'll come to the molecular electronics part, where I will be using an polymers or plastics or organic materials for making OPV, organic photovoltaics, or organic light emitting diode, OLEDs, or organic DNA sensors. I will come to this point. That will be a little technical talk, but in molecular electronics, I would like to say that still we are behind. We are not very far behind, but up to 2030, we'll do before that. Moore's law, everybody knows in your, electronics, that it said that transistor density will double in every 18 months, and I think the Moore law, the time will come. The Moore's law will not be, it will be overcome. We are just hoping about that. So then when the molecular electronics, I will come to that also. I'm just seeing about 20 minutes are left. Then a number of materials are there. So when I talk of the molecular materials or the polymeric materials, or basically I'm saying about the polymers. Polymers basically are non-conducting. Polymer plastic is there. Polymer is nothing but plastic. Your utensils or various things that made of polymer are not conducting. So it's very bad. But I will talk to you about the conjugated polymers, which has changed the scene in 80s. And I'll tell you, the Higa Shirkawa and McDermott got Nobel Prize in 2000, in the year 2000, from where we started working in the area of the conducting polymer or organic electronics. Now, LEDs have come to the production phase, and everybody is using LEDs rather than using CFL or even old bulbs, resistance-based bulb or tungsten filament-based bulb. So you are saving energy. I say saving energy is equal to produced energy. So you are saving energy or producing energy. Transistor chips are being used. Solar cells are still struggling. Well, people are trying to make. I have also tried to make, but in case of organic LEDs, I have not been able to go more than 6, 7, 8% because there are so many problems. There's so much of degradation in the atmosphere, but still we are trying, and people are trying to make different types of solar cell. In 2018, it was made about 18% efficient. They have made special solar cells, and I'll come to that if the time permits. So there are very small devices available there. The problem with the conducting polymers is the mobility is very low. In case of normal semiconductor, the mobility is about 10 power 4, 10 power 3 centimeters square per volt second. But here in case of the conducting polymer, it's 10 power minus 4. There it was 10 to power 3, here it is 10 to power minus 4, 10 to power minus 5 centimeters square per volt second. So we have to see how the mobility is to be increased to increase the efficiency of the device. Otherwise, there are various advantages of the conducting polymer based devices. They are flexible devices, they are environmentally friendly, their low cost processing is there. Many things are there. Only the worst part is that in some cases there is a lot of degradation of the devices, and people are trying to address this problem. So you can see this is a device which is a foldable device, organic thin film transistor. You can see how good it is looking at, and you can put it, you can have it on your clothes, or you can wear it on the clothes. It's foldable, so there is no harm. So it's active matrix, light emitting diode. So these type of things they are used. Carbon nanotube you have already heard, and if you use the graphene sheet, it's a 2-dimensional sheet. If you roll it down in different dimensions, you get you just roll a paper, and then it becomes a carbon nanotube, similar to that of the carbon tube. And fullerene is C60, is the nanomaterial, and then is how it's being used. We have used these materials for making the devices. C60, fullerene, PCBM, etc. We've used carbon nanotubes. I have been just showing you. It was discovered by Ijima in 1991, and Ijima came 2 years back to Jamia Millia Islamia, as Manika Khanuja had mentioned in a transparency. So he was the person who is responsible for carbon nanotube. Nowadays, so many nanotubes. You can have silver nanowires. You can have zinc oxide nanotubes. You have zinc oxide nanorods. So carbon nanotube was in the very beginning. It is a material which is mostly used, and you can see it has very high tensile strength. And people say that you can make a stair or ladder up to heaven, it will not break. I'm just saying it for saying, but just to mention that it is so strong that it's not easy to break it. And it is used in many electronic devices. The mobility is very high, so it supports the mobility of the conducting polymers also. So many things are there. most important point I'm going to discuss in 5 minutes, and then I'll go to the actual devices. Now, what is the hazard is we are using so many nanomaterials in the, I mean, they are coming in the market. Everybody is making nanomaterials. So without having any regulation, without having any check on these materials, what is happening that so many studies have been done. They suppose some inhale a material which is a nanomaterial, they go to the respiratory organs, they go to the lungs, and small size particle pass through skin, enter the bloodstream, lungs, cross cell membranes, and even travel through nerves directly to the brain. And some studies have been made. So we have to be very, very careful when we use the nanoparticle. And direct use, I will tell you, most of the, I should not say girls also, ladies also, boys also use sun cream. Why? Just to protect them from ultraviolet light. What is sun cream? It's having nanoparticle. You are putting on the skin, and the nanoparticle may go in the skin. And what's happening, you can see they can go to the skin, they can enter the bloodstream, they can go to the lungs, they can go to the membranes, and even up to the brain. So they may be very, very harmful, and these are the hazards. So every good thing has a bad thing also. So we have to take care with this. And then you have the influence of nanoparticles on biological systems. Toxicity is very, very important. And Ministry of Health and Agriculture have issued their guidelines, as I told you earlier also. Haldi is very harmful in nano form if dose is more than, in bulk, the particles are big. But when you take it in a very, very small size or nanoparticle size, it is used for, curing the wounds, nanocurcumin. Some work was done by one of the persons in MIT, Suman, Dr. Suman was working, she has left now, on the nanocurcumin, and some work is also going on there. So these materials become toxic for women and for the environment. So we have to be very careful, and we have to be, what we are using deodorant, soap, toothpaste, shampoo, hair conditioner, sunscreen, anti-wrinkle cream, moisturizer, foundation, face powder, lipstick, glue, eyes. Take the thing, they are all bad if they are not using properly. And you say that some of the things create allergy in the body. So even the aftershave lotion that people are using. So we have to be very, very careful. And a report has identified 7 face cream that list carbon fullerene as ingredient, and they are having toxic effects in human liver cells, you can say, brain damage. So all that glitters is not gold. It has the second side of the coin also. So you have to be very careful when you are working in the area of the nanomaterials, and for those researchers and also, because the size matters, and the size changes all the properties. Skin penetration is there. Inhaled nanoparticle go to all the things I already mentioned here. And it was the report given in 2000, long back 2006, that you have to have minimum skin contact. You have to put gloves. You have to have personal protective system. You have to have some proper type of clothing. So these things are there, and various remedial measures are there when we are working with the nanoparticles. So some of the importance I have said. Most important is when you use an nanoparticle system, first of all, find out how much harmful it is. Hand washing facility is also harmful. So HEPA filter, high efficiency particulate filter are there to remove the particles. They are used in clean rooms. So small particles are being used. Now, what we have done in our laboratory, in 10-15 minutes, I'll do it. We have worked in the conducting polymer solar cells. We have worked with single board carbon nanotube, conducting polymer, quantum DOS-based solar cells, SWAN-based alcohol sensors. We have based DNA sequencing, and we have made quantum dots. All nanotechnology is, and nanoscience, of course, and nanomaterials, of course. Materials are there, but for the science we have studied, and we have made the devices under a number of projects of DST or DBT, biotechnology project or DST. Now, I'm not going to say many applications because the day will pass. So many applications are there. I'm not going to discuss. I'm coming to mainly now method of preparation, top down or bottom approach is done. I'm coming to the device. It's very long procedure. And I would just like to say, when you go to analyze, a simple optical microscope will not do, because microscope work on the principle of resolution, and any resolution who have read optics know that Rayleigh criteria of resolution is that the two sources can be just resolved when principal maxima of one falls on the minimum of the other, or it is based on diffraction, and for diffraction the size of the obstacle should be of the order of wavelength. Most important, size of the obstacle should be of the order of the wavelength. So here optical microscope, optical has wavelength 400 to 700 nanometers, where our particles are 1 to 10 or 100 nanometers. We cannot use, because the wavelength is 400 and our particle is 100 nanometers. So diffraction will take place only when the wavelength of the particle is of the order of the wavelength of light that you're using. That's why we use electron microscopy, and electron is taken as a wave. You know, electron is a particle as well as a wave due to dual particle nature. And when the electron is moving with a high velocity, this half mv square is the energy, is equal to q into v, is electrical energy or kinetic energy. Half mv square you can make half q by half m by m square v square by m. So this becomes mv is the p, mv is the p, momentum. So P is equal to basically h by lambda you have heard. So P is equal to h by lambda means the higher is the momentum, smaller is the wavelength. So you can use in all these things, electron microscope, you use this property, then you have atomic force microscope and so on and so forth. It's not possible to discuss all these things, but now names I have given you these things which can analyze the nanomaterials and nanoparticles. And optical band gap increases, I told you, I'll show you some time. So many properties are there, and then these properties, I'm showing you, this is scanning electron microscope. The carbon nanotubes are like this, and this is seen under, you cannot see it by eyes, you see a black powder only by eyes. Optical, you cannot see this, only a scanning electron microscope you can see. Then you can see the carbon nanotubes like this by transmission electron microscope. Otherwise, you cannot see. These are the tubes, carbon nanotubes. I'm just trying to show you these things. Similarly, the atomic force microscopy, you can see the films. These are the films. This color show you how much unevenness is there in the films. So all these things are there. And I told you for the quantum confinement, for the devices, because I'm working with the optical devices, optoelectronic devices, solar cell, OLED. So this is the condition for the quantum confinement. And when the quantum confinement is there, then you can have quantum wells for 2 dimension, quantum wire for 1 dimension, then quantum dot for 1 dimension, 0 dimension, so on and so forth. Again, very good long thing. There is a term known as Bohr exciton radius. If the size of the particle is less than Bohr exciton radius, then only there is a quantum confinement, otherwise not. So 2, 5, 10 nanometers not quantum confinement. But if it is, if for say lead sulfide or lead selenide, the Bohr exciton radius is 6 nanometer, then the 6 nanometer or smaller particle is quantum confined. Suppose the for lead selenide it is 40 nanometer. Any particle less than 40 nanometer will be having quantum confinement. So it's very important condition. You can see the Bohr exciton radius for these materials. Any particle less than this size will be the quantum confinement. So small, difficult to control. It's very difficult to control. We have done that part, and we have spent months in controlling these particles. And these are the things which happen when we reduce the size of the particle. You can see the band gap changes, the density of state changes, the blue shift because the band gap increases. So wavelength decreases. E is equal to hc, h nu or hc by lambda. So if you increase E, lambda will increase, or when lambda decreases, it is blue shift. If lambda increases, it goes towards red. If it is decreasing, it goes towards the blue or violet, ultraviolet. So it's a blue shift. You have very small response time, which is very good for making a sensor. The electric constant changes, and non-linear property is very, very important for optoelectronic materials and devices for making optoelectronic filters. So these are the things which are used, and I'm not going to discuss. I'm just showing you that initially it was the band gap for normal material, for bulk semiconductor. When you go to the nanomaterial, the band gap, you see it was this much, it's increased because you have broken, you have all the energy levels are there. And then for molecule, it is again. So it used to be conduction band, it used to be valence band. We call it LUMO and HOMO here. It's the lowest of the molecular orbital, LUMO. Lowest unoccupied, conduction band is unoccupied, is also occupied. It is the highest occupied. यहाँ से चले highest, यहाँ से चले lowest, कंडक्शन बैंड के लिए और वैलेंस के लिए हाईएस्ट. तो इस हाईएस्ट ऑक्युपाइड मॉलिक्यूलर ऑर्बिटल, तो हम बजाय कंडक्शन बैंड वैलेंस बैंड के होमो और ल्यूमो बोलेंगे इनको. और इसी तरह हमने आपको यहाँ दिखाया लूमो और होमो दिखा है. और इसके बाद ये सब चीजें चेंज हो रही हैं, डेंसिटी ऑफ स्टेट चेंज होती है. ये सब छोड़ दीजिए, नहीं कर पाएंगे हम, टाइम बहुत कम है, हम तो मटेरियल उस पर आ जा रहे हैं अब. बहुत जल्दी से डिवाइसेस के ऊपर आते हैं एंड हम आपको बता रहे हैं कि हमने क्या किया था. Let me just come to the very important thing. I'm leaving the quantum dots also. These are the quantum dots. You can see under AFM, atomic force microscope, हमने आपको दिखाया था. And these are the under SEM. ये छोटे-छोटे आपको डॉट दिखाई दे रहे हैं. I'm coming here. Higa-Shirkawa McDermott got the Nobel Prize, and then we use the conducting polymer. They are the single bond, double bond materials. They have the pi electron. You must have heard about the sigma and pi electron. Pi electrons are responsible for conduction. Whereas in normal polymer plastic, there are no pi electrons, so there is no conduction. Here there is conduction here. They have the band gap also. I have written here, they have the pi electrons. They can be doped. So band gap is there. The ping is possible here. And you can tune these things. So all the properties of semiconductor can be harnessed here. So conducting polymers can make use of the properties of semiconductor. So if you make solar cells or light emitting diode from the semiconductors, we can make use of the semiconductor, the photovoltaics. We call them organic semiconductors also in a way. And then when we do this part, I'm saying a solar cell, how does it work? Light falls, electron hole pairs are generated. They are coming to the load and the current is flowing and you get something voltage in the output. What I'm going to do quickly here, I take here these polymers, polyethylene, radiolabeled polymers, and this is fullerene. You have the donor and acceptor. This donor acceptor is different from a normal semiconductor. In donor semiconductor, you had the N-type material. In P-type semiconductor, you had the acceptor material. It is different here. Here it gives electron, so it's donor. So it accepts electrons, acceptor. So I try to understand this. Don't get confused. And we make the solution of this material. It's so simple to make. And you make the solution, put it on a spin coater. जहाँ पे आपको film बनानी है, wherever you have to make film, you put the drop here and just spin coat it. Your material is ready. Device is ready. Just make contacts and go. But the things are not so simple. Saying is very easy, making difficult. The uniform you have to make, you have to optimize a number of things. You have to optimize the concentration of the solution. You have to optimize the rotation speed. You have to optimize time of rotation and so on and so forth. So many things we call spin coating technique. And we have made this device. We took a substrate and by spin coating, we made different layers. These are solar cells and this is the active material. P3 C60 donor acceptor blend. बाकी चीजें जो है वो whole carrying whole को आराम देती हैं. They are whole taking materials, similarly electron taking materials. Why? Whole transporting layers, because the velocity or the mobility is very small. I told you for polymers. So that's why we need a transport for them. We need a bus for them to take the electron poles. So we have made this HOMO and LUMOs here. You can see this the LUMO. Sorry, this is a HOMO. This is the LUMO. यहाँ पर आपका होमो है, हाईएस्ट ऑर्बिटल, ये लूमो है. उसके बाद हमने सोलर सेल बनाया. ये सब किया, selection solvent का किया, donor acceptor issue we have to done. This thing we have done. This is a very nice. This is bad. This is very uniform. We selected this material 1:1, made solar cells. We made IV characteristics of the device, and then as I told you in the very beginning, then we make a recipe in the kitchen. To make it good, we go on adding spices in the recipe. You go and adding spice. I am adding my spices in the form of carbon nanotube, in the form of quantum dots, in the form of graphene, and so on and so forth. And let me tell you very frankly, you have to add spice in a proper proportion. If you do not make this proportion, you put salt, so many lot of chilies and lot of salt, your device will, or your recipe will be spoiled. So our recipe is a device here, and for that purpose, what we are doing the quantum, putting quantum dots. We are putting carbon nanotube, we are putting graphene, and I would like to show here I have then put quantum dot here. You can see here the anode, the whole transporting layer, polyethylene, and this is my layer there. I put quantum dots and this cathode. This is my device, and I will see here that my device characteristics are very good. ये तो मैंने Venn diagram बनाया है, how the from here the electron hole pair goes and how the solar cell works. You can see here it's not working here at the moment, but anyway. It's not very clear, it's not come. This carriers are generated here, holes are coming here, and electrons are coming here. So this is the charge transfer taking place. IV characteristics, I have shown how it is becoming better. So this is there, then I could get efficiency about 5.1%. Then I did carbon nanotube. These are the carbon nanotube I have added. It is becoming still better, and it's still better. And then I added graphene. It is much still better, and so on and so forth. This is how I have added DNA, this is a biosolar cell. DNA means DNA CTMA. I have added as electron blocking layer. The carriers are generated here. I want that whole, the electron should come here and hole should come here. यहाँ पर I2 का hole आते हैं, तो electron should not go there because, sorry, the electron should not go there. So I'm putting electron blocking here. Okay, electron should come here and hole should go there. So similarly, a number of things, quantum dot, permanent, all these things I have made it and I have been able to do. The graphene is providing additional path to the carriers. The carriers become fast and you get a better reception of the carriers. So this is the final device I have made using graphene, quantum dot, polyethylene, P dot. So this is how the best device I have been made, and I am comparing the devices, which is very good. All these things I have added. So now I'm coming to the LEDs. I think I'll be given 5 more minutes. Same thing
Sir,
I have done in.
we
No?
would be running short of time. Yeah, I'm
Okay.
really sorry.
Okay, so I'll just finish in 5 minutes. So I have made LED, done the same thing, made in LED, and I'll just show you, if possible, this is I have done in LED, and you can see here what's happening here. So you can see that the electrons are coming, they are joining and making light is coming out. Zinc oxide nanorods I have used as a waveguide. So from LED, light is coming out, about 22 times light is coming out more. And in medical diagnostics, I have done DNA sequence detection, and I have used a phenomena which is known as FRET, Forrester Resonance Energy Transfer, and I have been able to detect in femtosecond. Believe me, in femtosecond, I've been able to detect DNA, which is used for the society nowadays. Okay, and then the FRET phenomena takes place. I take a cationic conjugated polymer and a probe. If your sample matches, there's a hybridization. There's a hybridization and FRET takes place. If it does not match, there's no hybridization and no signals coming. So many things are there. This light is coming out, and I think I should close here. I wanted to show you 1 or 2 films here, but people will say something. This is my very good diagnostics of the DNA sample. When I use the surfactant, this was my group, and here I close my talk. And if someone wants to ask a question, I'll be happy to do that.
Thank you so much, sir. You have got so rich experience that it is very difficult to confine in a 45-minute talk.
I just wanted to show you this movie. I don't know.
Okay.
If you can,
how long is it, sir?
A few seconds.
Yeah, please.
Okay. So, okay. If it is working, okay. I don't know it's working or not. Basically, it is showing you, it's not moving. I don't know why it's not moving at the moment. It shows you how the emitting diodes are being made. OLED displays. I'm just quick.
You can press the play button, sir, at the bottom.
Unfortunately, this button is somewhere.
I can see it right.
Okay.
Yeah.
You can see. So one OLED is there and one more, and then it's over. I'll show you the TVs which are transparent. I'll show you the TVs which are, foldable TVs, which has come to the market. So let us just I cannot do it now. So leave it now. Okay. Some other time. Okay. Thank you so much.
Questions are invited from the participants.
Thank you so much, sir. To hear you, it's always a pleasure. Your enormous knowledge, we really cannot confine in 1 hour. I know that. Sorry for that, but we'll call you one more time, maybe in a physical mode to talk more. And
see, I have given a trailer only.
So I know, sir.
Okay,
I know, sir. It's always, your talks are so enriching. Sir, one thing just not related to your talk, like I know you have, you've been working on sensors and OLEDs and all. What do you think, where are we in India towards commercialization? Are we somewhere, can we compete with the foreign countries who are coming up with these commercial items on OLEDs and all, using OFEDs, OLEDs and all?
See, these items are very, very expensive, even as on date.
Right.
If we join in Modi's skilled program or skill development program, I think they have done all these things in laboratory. And we have given
Exactly.
prototype devices to DST and DBT also for sensors and all these things. These we published long back. You can see these paper-based sensors. Now publishing means we have made it also. And in your MET, people are doing good job of making sensor. I know that. So LED and OLED is a distant dream, but new things are coming up. The prices have come down. It used to become about 3 to 4 lakhs. Now it's about 1.5 lakhs. So with demand, with mass production, the price will come down. And our various laboratories are working in this area, but they're doing on for defense purpose. I've done these so many sensors. You can see this sensor, and so many publications are there on sensors. This again is carbon nanotube sensor. So India is competing. It's not lagging behind now. Okay. The only thing is we do not have proper facilities, and we have to have more willpower to do the things in the interest of nation, not for our own interest.
I think policies are also to be amended towards, more fund towards these kind of research is also needed.
You must have heard that Modi has given a very good amount for this.
Semiconductor industries have got a big chunk of fund now.
Similarly, the OLED will get. Solar cell is somehow lagging behind. OLED will come forward. Okay. Yes.
Yeah. Thank you, sir.
Thank you, sir. Thank you for really a wonderful talk. And every talk gives us a new learning whenever we are listening to you. And it is really pleasure that your affections and the blessing with us. Every time whenever I am asking, sir, there is a talk or there is something, and you happily agree for that. So thank you very much, sir, for your time. And it is really wonderful to listen to once again.
So thank you, Sinha Saab. Thank you a lot. And I also learned while delivering the talk some new points. I try to understand. Some questions come in mind. So I am thankful to you for giving me opportunity to give it out. Thank you so much.
Thank you, sir.
The talk was so self-explanatory that there are no questions, so we can go ahead.
Moving on, we feel privileged with presence of our next speaker, Dr. Suman Lata, today with us. She is currently working as scientist too at AIIMS Delhi. She received her PhD in biochemistry from Rohtak University, Haryana. Then she worked as postdoctoral for 2 years. Dr. Lata's research contribution is published in 15 reputed international journals. She is a member of Indian Society of Hematology and Transfusion Medicine and Association of Clinical Biochemists of India. Her research interests include study and development of biosensors based on nanomaterials including CNT, nanoparticles, polymers, etc. She also attended a number of national and international conferences. To know more about her research work, we would like to call Dr. Suman Lata ma'am for the talk. Title of her today's talk is Conventional and Point of Care Diagnostic Tools in Leukemia. Ma'am, I humbly request you to please conclude your talk in 45 to 50 minutes, followed by 10 to 15-minute question and answer sessions. Thank you. Platform is yours.
You can now share your screen now.
Thank you so much, dear. You have given me such a wonderful introduction. Thank you so much for that. And now I would like to start about the, first of all, I would like to thank the organizing committee who had given me this opportunity to share my experience in nanotechnology, and now I'm working in the tertiary care hospital, that is the most prestigious institute of India, All India Institute of Medical Science. Now I would like to deliver my talk on point of care tools in healthy human beings and how we use these tools in the leukemic patient, and how we have moved from the conventional techniques to more advanced technique for the patient care, especially in a cancer patient and many blood disorders which we are facing nowadays that these cancer incidents, they are day by day increasing. So from the human point of view, I would like to share my experience in this prestigious institute, that how the patients, they are coming from the rural background and how they are facing lot of problems which is related to the blood cancer. So in if we see the scenario in rural areas, because most of, you know, in India, most of the population is oriented towards the village. So in that way, we can say that there is a need how we can move from the very basic root level to the most advanced, because everybody cannot access the tertiary care hospital, you know. So in that way, we need some more advanced as in India, to develop those techniques which can be accessible for the very poor and illiterate population also. Because in India, there is a variety, there is a diversity, that all kind of population is there. The farmers is there are educated people and more educated people. So everybody cannot access AIMS facility or a more advanced facility. So in that way, I would like to share my views that how we can use the very basic conventional technique from the laboratory basis to the more advanced patient care. So in from the root cause, I want to say that in medical industry, there is a continuous development of these technology. If we talk about the discovery of stethoscope, and then move on to the molecular diagnosis, the DNA sequences, or more advanced to the, you know, it's a very fascinating name, that is the next generation sequencing, etc. So these advanced devices, they have been developed in response to the industry demands for the not only for the national level, but for the global circumstances. So that the scenario is changing, that we are moving from the ground level to the more advanced techniques. So currently, if we talk about the most portable devices, that is known as the hospital-based, or you can say point-of-care diagnostic devices, which can be used for the diagnosis of the disease, which is centralized or hospital-based, which is oriented towards the hospital-based laboratories. So in the hospital, many expensive equipments are using. So to for using these equipments, they require highly trained personnel to pay. So how we can make these laboratory techniques to more patient friendly? We are moving towards that. Different, as Dr. Bhatnagar told about the use of nanotechnology and many portable devices for the environmental application. Similarly, that we are using many point-of-care devices for the medical field as well. For example, glucometer. Everybody knows about the glucometer. How it is so fascinating how a layman also can use it at their home. So like glucometer, we can also design so many portable devices for the diagnosis of more advanced diseases like cancer. If I'm working in the area of leukemia, as being a researcher, I would like to work in that area where we can design more advanced techniques for the betterment as well as for the diagnosis and prognosis of leukemia patients. So these portable devices actually, how they use, they simplified the diagnosis process. They are in very small size, miniaturized form, and yes, if we use the technology, in IT technology, along with the medical technology, these devices, they can be converted in a very small miniaturized form, right? So in that way, these equipment can be used as a user-friendly or patient-friendly. So how we can use these techniques, and we can convert these laboratory very tiring process on a small chip. So these are converting. The technology is transferring from lab to the chip, which is known as lab on a chip technology. Okay, so the best example is the biosensor technology. Me and Dr. Nidhi, we work together in this area, biosensor technologies, and we have used nanotechnology, and now I am exploring this technology in for the betterment of leukemia patients, leukemia patients' diagnosis and prognosis process. So it's very it's at a very early stage, but we are trying. So we need some cooperation to facilitate this lab on chip technology to the benefit of the patients. So once this laboratory will be converted, it can be used. For example, if we take the example of a pregnancy diagnostic kit, which is ELISA based, and it's so easy to use that a female can detect pregnancy at their home also. So there is no need to go for a hospital. So these techniques, these portable techniques, actually they are very patient friendly, and yes, these techniques are useful for the common human being also. So if we talk about the human being and the patient facility, these techniques, lab on chip technology, they are going on and on parallel. So if we talk about the leukemia patients, or any kind of patient services, these techniques, they can provide the portable device, and these are the tests. These tests can be helpful for the fast treatment facility. So now I would like to move on towards the molecular facility, because we at the AIMS, we are working in the diagnosis of molecular markers for leukemia patients. And these markers, actually they identify the root cause of certain cancers. Like if I talk about the example of CML, chronic myeloid leukemia, which is it's a very common cancer in blood cancer patients, leukemia patients. So in that case, these biological markers identification is very helpful. So at the basic level, we are working for the diagnosis of these markers, and we are working for the monitoring of these markers. So if we talk about the molecular markers, they provide additional information regarding the prognosis, diagnosis, and yes, the proper diagnosis gives the best prognosis. And one more thing which I want to share, that these molecular markers, they help for the pharmaceutical company also. How they help. They are very helpful when we identify the particular biomarker, molecular marker. We can target that marker and we can use as a therapy. So we can design therapy according to the presence of the biomarker. So the CML is a best example for the targeted therapy. As you know that we are facing this pandemic situation, and from last more than 2 years, since 2019, we, not only India, but the whole world globally, we are facing the COVID-19 pandemic situation. And everybody, from the layman to the scientist or medical science, and everybody is knowing about the this molecular term that is known as the RT-PCR. So this COVID-19 pandemic situation is it driven the pharmaceutical scientists and everybody to develop more patient-friendly devices. So to facilitate this device to the common person, to everyone, easy way. So these devices, they are converted into very compact, portable, patient-friendly devices. So it can be used for the near patient testing, right? So everybody knows that nationally and globally, these devices are used. So these devices, portable devices, they are able to provide instantaneous results, and yes, that support the provision of timely patient care by better informed healthcare professionals. So we can see that being a medico, or for the doctor and patients, there are no longer requirement to wait for the lab results in order to make an appropriate diagnosis, and yes, for the treatment also. So medical point of care devices, they are available throughout clinics and hospitals. They allowing medical professionals to acquire rapid, accurate test results, and they are offering them more time to focus on the treatment and patient care rather than waiting so long for the results. So from this conversation, from the very beginning to this point, I would like to say that these portable devices, they are very, very useful for the common person, because these devices, they can be used for the betterment and to facilitate the diagnostic and treatment facility to the common person. So I would like to conclude that these point of care devices, they provide wide range of benefits, like they provide the of lab quality results, certain like ELISA kit, they provide in minutes results. You can get in minutes. For example, the pregnancy kit that can detect results within second. So these they provide the robustic near patient diagnosis. And the third point, which is very important, that they reduce for clinical visits. Like, for example, if we talk about the COVID duration, at that time, there was very less accessibility for medical facilities. So at this time, so the time is changing. So we can say that these devices, they are very helpful. So due to the availability of these type of portable devices, the doctor or the medical staff, that can focus more on the treatment rather than on waiting results for the diagnosis. We are working in tertiary care hospital where we are dealing with the molecular genetics of leukemia, and these molecular genetics, which is our integral part of routine laboratory workup, and we are monitoring the hematological malignancy like CML, chronic myeloid leukemia, acute myeloid leukemia, chronic lymphocytic leukemia, and so many other different type of blood malignancy we are dealing at our hematological department. So for this reason, identification of biomarkers is very important for a diagnostic point of view, as well as for the prognosis or the better treatment of the patient. So how these molecular detection of genes in leukemia is important. If we see the molecular level, it's a downstream processing to identify at the root cause. So to classify, because these cancers, leukemia, these malignancies, hematological malignancy, they are so mixed that the one parameter can change the treatment criteria. So these molecular detection is very, very important to classify the particular cancer. So it's very important for the classification. And as we classify or we properly diagnose the leukemia, we can find out the risk stratification, that how the patient, at what condition the patient is lying. So what treatment strategy we can find out to get the best treatment to the patients. So for the management of leukemia, these molecular detection of genes in leukemia patients is very important. Yes, the cancer is, it can be cured, but early identification of these biomarkers is very important to identify the relapse. You know, as we start the treatment, the patient will get at remission, but simultaneously we have to monitor the minimal residual disease, that is known as the MRD, minimal residual disease, just to find out whether the patient is on relapse or on remission. So to monitor these kind of calamities, we have to find out, we have to monitor regularly these molecular markers. So these molecular markers, they offer the opportunity to develop new specific pharmaceutical agent. For example, as I told you earlier, that the best example is chronic myeloid leukemia. In chronic myeloid leukemia, the gene which is responsible is a fusion transcript gene that is known as the BCR-ABL fusion transcript, which is used as a targeted therapy. So in the cancer detection, they have developed a drug that is known as imatinib, which is very, very successful for the treatment of CML patients. If I talk about the progress of our hematology molecular department, initially we were using the immunophenotyping. Then in the 1998, before that, we were using the southern blotting, and we move on PCR, then RT-PCR, then for monitoring of disease, we have used real-time PCR. Yes, we cannot replace these conventional techniques because is more advanced technique is available, but for the proper diagnosis, we cannot replace these conventional techniques. So as I told you that initially my department was, before my joining, the department was focusing towards the more conventional technique that is known as the sudden blotting, which was discovered in 1973, but in print form, it comes in 1975. It's a classical technique that involves the separation of DNA fragments based on size, that is via electrophoresis, and then transferring onto the membrane, hybridization process. And yes, the labeled sequence-specific probes has been used, and there are many washing steps are there. And finally, we can detect the DNA bands on electrophoresis gel. So it's a tiring process. It was at that time, it was a gold standard method, but now it's a tiring process. More advanced is coming out, more advanced techniques are developing. So just to know the requirement of current scenario, we are moving from the conventional technique to the more advanced techniques. So after this sudden blotting, we shifted on towards the DNA sequencing. Yes, DNA sequencing is still, it's a gold standard method. It was came in 1977 with the development of Sanger's chain termination or dideoxy techniques. Everybody knows about this technique. It's a very, very important if we talk about the molecular basic detection or in diagnostic purpose. This DNA sequencing is still in very much demand. So yes, DNA sequencing is the basic technique, and similarly, more advanced techniques are coming out on basic principle of DNA sequencing. We will discuss more about this DNA sequencing, basic and more advanced techniques, which I told you, next generation sequencing. So in certain diagnosis, column chromatography is required because we are dealing with the, I'm working in the area of leukemia, but my department is working for blood disorder. Many kind of blood disorders are there. So at certain point, we need certain staining as well, very conventional techniques, and we are using the column chromatography in different advanced modified instrumental form. And yes, we are using high performance liquid chromatography, that is known as the HPLC. Enzyme linked immunoabsorbent assay, ELISA, is also used to find out certain proteins which are very important for the diagnosis of many blood disorders. We cannot replace this karyotyping techniques, because this techniques, cytogenic techniques, is very important for certain translocation identification. So, for diagnosis and prognosis purpose, we need a mixture of conventional and advanced techniques, right? So we cannot replace completely conventional, or we cannot move on completely on to the more advanced technique. So we need intermixing of these techniques. So somewhere the karyotyping is very much important. Somewhere NGS play very important role, right? So these techniques, as I told you, DNA sequencing, column chromatography, HPLC, ELISA, and karyotyping, these are basic techniques. As you know that we are studying about these techniques so long in 90s, era of 90s, but still they play very important, very crucial important for the certain for the diagnosis of certain cancers. So if we talk about my laboratory molecular work, we are working for polymerase chain on this technique. This is a very basic technique we are using in our laboratory, and we are using different type of polymerase chain reaction, PCR, like multiplex PCR, nested PCR we are using, and allele specific PCR, which is very important for the diagnosis of certain mutations, which are driver mutations for certain malignancies. So if we talk about the type of PCR, one PCR is the ARM PCR. It's a simple method, that is amplification refractory mutation system, which is known as the ARMS PCR. It's a simple method for detecting any mutations involving single base change or small deletion. So this ARM PCR is based on the use of sequence-specific PCR primers that allow amplification of targeted DNA only when the target allele is contained within the sample. If that mutation is present, then it will show the positive results. So we are working with these different type of PCRs in our laboratory to identify or diagnosis of different leukemias. I have discussed about the 90s era, and now we are continuously from the 2001, we are using this PCR technique. So just to give a brief comparison between these two techniques, Southern blotting and currently used PCR technique, there is a similarity, yes, both they are used in recombinant technology, but the basic difference is there. Like if we talk about the PCR techniques, there is only single reaction vessel is required, while in Southern blotting, we require multiple vessels. And if we talk about the time, this PCR technique is easy, and yes, it's a fast technique. And Southern blotting, it requires more time. So we cannot always use this technique, because for patient care, we need very fast result for the treatment purpose. For the basic laboratory, we can use these techniques. These are the very fascinating technique, but for patient care, we have to move on more advanced technique along with this conventional technique. So if we compare the sample size in PCR, a very minute amount of, just in microliter, we need DNA samples, while in the Southern blotting, sometimes we need a large sequence of DNA. So this is a difference between these two techniques. Although these techniques are itself, these are very, very useful techniques. From the very basic point of view, Southern blotting is, yes, very important. But for a diagnosis purpose, as a tertiary care hospital, we need to move on for the fast techniques. So PCR is very useful for the leukemia patients, diagnosis, monitoring. So if we talk about the progress of molecular techniques in the Department of Hematology, where I'm working at AIMS, New Delhi, since 1998, we are using PCR, polymerase chain reaction, that is used for different type of blood disorders, identification of different disorders. And since in 2005, we have the very important driver mutation has been identified, that is known as the genus kinase 2 mutation, that is very, very much important in the myeloproliferative neoplasm patient. It's a type of blood cancer. So in MPN, this mutation detection is very important, which is responsible for many kind of thrombotic events. Suppose the blood RBC level gets increased, HP is very high in PV, polycythemia vera patients. These terms are medical terms. Yes, these are different kind of myeloproliferative neoplastic leukemia terms. And in 2005, this JAK2 becomes the landmark, or you can say it's a diagnostic hallmarks of myeloproliferative neoplasm driver mutations. In 2014, there was one more driver mutation was identified. In certain patients, the platelet gets very high, more than 4 lakhs. In that case, there are chances of thrombotic events. Just to find out why the platelets are getting so much increased, just to find out that reasons, the researchers, because basic research is very important for the diagnosis and prognosis region. So in 2014, calreticulin, that is known as the CalR mutation, calreticulin mutation, that was identified. And we have started since 2015. We have one of my colleagues, she has retired, but she published one paper in 2015. So it was in 2014 was discovered, but in 2015 we have identified so many patients in which the CalR mutation was positive. So it's very important for the diagnosis in MPN patients. We are providing this RT-PCR facility. Yes, for the quantitative PCR, RQ facility is also available. So in routine services, since 2001, we have diagnosed more than 19,000 patients with these techniques, RT-PCR and RT-PCRs. So since 2001, we have dealing with the chronic myeloid leukemia patient. As I told you, is the diagnostic hallmark is BCR-ABL fusion transcript, which is responsible for this deadly disease. But because of this fusion transcript, BCR-ABL, which is a target. If we the pharmaceutical company, they develop a therapy or one tablet that is known as the imatinib or the Binet, which is known as a targeted therapy. So with the help of this only one tablet, just like a thyroid tablet, this deadly disease can be the patient can come on remission. So this molecular marker detection is very, very helpful for chronic myeloid leukemia patients. Similarly, we are dealing for another type of leukemia patients like AML, acute myeloid leukemia. These chronic and acute, they are distinguished on the basis of blast percentage. If the blast percent is more than 20%, the patient is like at very serious conditions. So they are not they are known as the acute myeloid leukemia patients. If the blast is less than 20%, the patient is at chronic phase. That can be manageable, but you know, as the disease progress, the blast level at the in the bone marrow is increased, and less than 20 is the chronic phase. More than 20 is the acute phase of myeloid leukemia. And if it crosses more than 30%, it leads to the blast crisis, which is very difficult to manage. And there are more chances that the patient may relapse, may not respond to therapy. So in since 2001, we are monitoring, we are monitoring and diagnosing these mutations by using these RT-PCR, RQ-PCR techniques. So these are the different translocations which we are giving as a patient service in the molecular leukemia diagnostic laboratory. Like this translocation 1517, if we talk about the PML RARA, this marker, this mutation, translocation, that is also just like CML, BCR-ABL, this also provide the target therapy. Only with the help of ETRA, that is arsenic trioxide, with the help of that, this patient can come to the normal cytogenetic or hematological response. So identification of these fusion transcript is very, very important for the treatment point of view. So these 821 translocation in version 16 and 15 translocation 1517, these are the good prognostic markers, diagnostic as well as prognostic markers, you can say. Similarly, like FLT3, that is known as FMS-like translocation 3 mutations, and the NPM is nucleophosphate mutations. So these are all molecular mutations which is related to the acute myeloid leukemia malignancy. So identification of these mutations, these are known as the driver mutations. Identification of these is very important for the treatment point of view. Similarly, is this ALL, that is known as the acute lymphoid leukemia, ALL, in which the this same translocation 922 is very important. This ALL is very common in pediatric patients as well as in adult patients. So the diagnosis and identification is very important. So these were the facility we are providing in our molecular diagnostic laboratory. Yes, we are using conventional. So I'm talking in between that why the conventional is important, why at one point more advanced technique is important. We cannot replace the DNA sequencing. It's a conventional, but it's a gold standard to verify. If you find something novel in the more advanced technique, or somewhere we are suspecting there must be some other reason, if these mutations are getting negative, in that case, we coordinate with clinician that there must be something else which is responsible for the disease. So we have to find out that reason. So to find out novel mutations, we move on the conventional DNA sequencing technology. So to find out the rare suspecting mutation in blood malignancy, we cannot replace DNA sequencing. So that is also very important for the leukemia patients. Yes. Now we have a very fascinating term that is known as the next generation sequencing, that is known as NGS. Yeah, this technique, it provides the chances to test many genes simultaneously. You know, in 2001, when the human genome sequencing was carried out, it was very very much costly, but because of this new advanced techniques, we are getting more advanced panels to identify malignancy, different malignancy. So NGS, this potentially saving time, money, and patient sample. Yes, we require in microliter or nanogram quantity patient sample if many markers are needed. So this next generation sequencing, at one panel you can find out many genes simultaneously. There is no need to go for multiple primer designing, PCR, RT-PCR, RT-PCR. This technique is very useful. Next generation sequencing for the identification or the diagnostic purpose. It can provide results not only for the mutations specifically needed, but it can also identify new markers that may offer additional treatment options. So we can say that NGS provides more platform for the diagnostic as well as for the prognostic purpose. So just to conclude that from the very beginning, as we told about the human welfare for more towards the patient services, these point of care devices, they are useful just to detect the complete blood count in a routine test, or from point of care devices to to find out the more advanced diseases. So the point of care devices, they have promising futures due to their ability to easily and easy and accessibility accessibly detect the health problems. And for medical field, these point of care devices, they provide robust tools for the diagnostic and monitoring. So if we talk about the progress of molecular diagnosis and progress and yes, routine services of the hematological department for leukemia patients, we are developing more advanced techniques for the better diagnosis and prognosis of leukemia patients. So it's a long journey from morphological examination, because still we are using the PS smear, peripheral smear formation, to histopathological, and we are moving towards the PCR to DNA sequencing. Yes, very fascinating. That is known as NGS next generation sequencing. So one and all, these are the mix techniques which we would like to implement for the better diagnostic and prognostic purpose of leukemia patients. And I would like to thanks. Thank you so much for listening me so patiently. And some terms are very much related to medical. Sorry for that. I haven't given much detail about that. But that is towards more towards the conventional and advanced techniques that we use, not only for the environmental or any other field, but for medical and for routine healthy patients, for routine healthy human diagnostic purpose. We use a lot of patients diagnostic services. So I thank you so much. I would like to thanks organizing committee. Thank you for giving me this opportunity to interact with the to deliver this talk and share my views. And I personally, I would like to thank my dear friend Didi Chauhan. She is as associate professor at the university, and all the delegates. Thank you so much. I'm glad to share my views. If any query, I'll be happy to answer if I can.
Thank you so much, ma'am, for
So
such an extensive talk. And it was really like, I also learned a lot of things. I'm not from bio background, but I learned a lot of things from this.
Thank you so much. Thank you.
We have one question from Professor P.K. Bhatnagar. Sir,
Okay.
if you could unmute
Pajama,
yourself and
yeah,
answer.
she can. Yeah, he can ask himself.
I'll be glad if I can answer. If I couldn't, please excuse me. Because I'm at a very early stage. I'm also learning a lot of things.
I'm
I would
also
like to
at
implement
I'm also at a
my
learning stage.
current knowledge to the patient care. Yeah.
I'm also at a learning
we
stage.
are all learning from.
And there's a simple question. Do you have
Okay.
any method where you don't use PCR, polymerase chain reaction? If
For
not, then I will
what?
suggest you a method by
Okay.
which you can do DNA sequencing in femtosecond and just visually And it is a method where you use the nanomolecular concentration of the sample. And you use a phenomena
Yes,
Forrester resonance energy transfer. So please do that. It is very fast.
okay, sir. Thank you so much.
You can
Thank
see
you
my
so much.
papers on
And
this. Okay.
yeah, thank you, sir. In fact, I am also thinking that why I should waste my earlier knowledge. Why should not interact with the more basic and advanced laboratories so that we can collectively do something for the patient care. You know, individually we cannot work, right? I am dealing with patient care. Our clinician, they are more focused toward the treatment. But we are the core scientists where we can find out something new to facilitate more patient-oriented cares like portable devices.
I hope you
Isn't it?
will interact and you will be able to do some more work. This will be very fast and very useful. Okay.
Thank
Thank
you. Sir. Thank you. Any other question?
Ma'am, we have another question from Dr. Nidhi Chauhan. She's asking, what is the cost of NGS? Is it affordable?
Is the cost of, okay. You know, NGS is a more advanced technique. Sometimes, you know, it's very difficult. NGS is we have panel because so many driver, passenger, and some new novel mutation we have to identify it. You know, this is not, still we are lagging behind. We are under, means our instrument, NGS purchasing is under pipeline. So that is completely towards the private laboratory. So it's very difficult for poor patients. You know, AIMS is a tertiary care hospital where all kind of patients are, they came from different reasons. Very poor patients, they cannot afford 10,000 cost. So it's very costly. Some panel is like, it's not less than 8,000. It's more than 8,000. Sometimes it goes 19,000, 20,000. So it's a very costly technique. Yes.
Okay, the next question by Dr. Nidhi Chauhan herself is, are you going to plan for making it
like,
more
for example,
patient-friendly?
if I talk about, yes, we can make it patient-friendly. How I'm working on that. We are planning to develop a panel where only that is for just to reduce the cost and to provide the best treatment. You know, there are certain mutations which are not very much clinical significant. But in a panel, they have, I suppose they took more than 100 genes. So as per the panel, they cost. So we are planning that if we can design a panel on a PCR or RQ-PCR technique, which can be used for the patient for treatment purpose, right? But as a research purpose, this NGS is a robust technique, yes. So we are working on that.
Okay, ma'am. We have another question which says, what do you think of DNA-based sensors for disease detection in terms of feasibility? Can it be further helpful in personalized medicine? The question is by Shringika Soni. Should I repeat the question?
Okay, thank you so much. It's a nice question. Yes, DNA based, because we are dealing with the molecular markers and molecular mutations. So these mutations, if in our laboratory, we are not having this facility, biosensor technology right now. We are dealing with the molecular diagnosis only. So to design or to develop a sensor, there must be facility, right? So what we can do, the lot of research articles are coming, you know, that, for example, if I talk about the TP53 mutations, which is very much important for many solid tumors as well as for liquid, for blood cancers. So there in literature, TP53 mutations detection biosensors are available. That is on ELISA based, and certain DNA based biosensors are also there. But you know, for practical point of view, there are some lacuna. We have to work together to facilitate more towards the patient care. Yeah, we can work together. Independently, I cannot do that. We don't have this type of instruments because we can work as a collaborative project for that we can propose. Yeah, we can do that. Thank you.
Surely, ma'am, we can definitely explore possibilities. Any further questions from
Yes,
the
yes.
panelists?
Thank you once again. Thank you so much for giving me this opportunity. I'm so glad and wish you all the best. Please give me more chance in future as well if I can share my knowledge, little knowledge, but yes, we can interact and we can learn a lot of things from each other.
Definitely, ma'am. We would like to have a more extensive session
Yes,
with you in
yes.
future.
Yeah,
Definitely.
we all are doing for the patient care or some for the betterment of society, right? So in that way we can collaborate. I'll be more than happy for that. Thank you so much. Thank you, Nidhi. Personal thanks for Nidhi Chauhan. Thank you, dear.
Thank you, ma'am. Thank you.
And thank you so much, organizing committee and all delegates. And yes, to all the listener who is listening to me, maybe somewhere they felt boring, but pardon for that. I'm so happy.
Thank you so
Thank
much,
you,
ma'am,
ma'am.
for such a
Thank you
brilliant
so
talk.
much.
And now I request Monica to proceed
ma'am.
with the session.
Thank you, Dr. Sumanlata ma'am, for such a wonderful lecture. Thank you on behalf of all of us. Now on to the next segment. We have our institution's young achievers. First, we have Dr. Shaheen, woman scientist, AINT. Dr. Shaheen Hussain is currently working as woman scientist at ICMR DHR at AINT, Amity University, Noida. She has completed her MSc and MPhil from Aligarh Muslim University, Aligarh, in the field of plant genetics. She has completed her PhD from Jamia Millia Islamia, New Delhi, from Department of Biosciences in the field of nanobiotechnology. She has published several research papers, book chapter, and review articles in renowned journals. She also got Young Woman Scientist and Young Fellow Award from Agricultural Technology Development Society, Ghaziabad, Indian Agriculture and Environmental and Technology Development Society, Uttarakhand, India. Today, she is going to be giving a talk on biosynthesis of silver nanoparticles using cyanobacteria and its applications. On this note, please join me in welcoming Dr. Shaheen Hussain to the platform. Ma'am, you have 12 minutes to present, which will be followed by 3 minutes of questions and answers. The platform is yours.
Just a moment. Monica,
Yes.
this is a 20-minute talk.
Oh, sorry. Yes, ma'am. So, Dr. Shaheen, ma'am, you will have 20 minutes to present, followed by 5 minutes of questions and answers. Part. Platform is yours.
Morning, everyone. First of all, I would like to say thanks to organizing committee and the chairperson for giving me a chance to deliver, to present my research work in this workshop. And the topic of my presentation is biosynthesis of silver nanoparticle using cyanobacteria and its application. First question will come in our mind: what are the cyanobacteria? Those cyanobacteria are aquatic photosynthetic bacteria. They manufacture their own food because they are photosynthetic and aquatic. They are also known as blue-green algae. They are known. They have distinction of to known as the oldest known fossil, more than 3.5 billion years old. In fact, it may surprise you to know that the cyanobacteria are one of the largest and most important group of bacteria on Earth. They are gram-negative bacteria. Cyanobacteria are the first organism known to produce oxygen. They can actually they can survive everywhere and in extreme condition also. They can grow even in snow as on polars, and some species can grow more than 60 degrees centigrade. These cyanobacteria are very easy to handle and they grow very fast. So that is why I choose cyanobacteria for my research. Next question will come in mind why I am doing biological synthesis. Actually, synthesis can be done by various methods like physical and chemical, but the biological methods are relatively simple, cost effective, and environmental friendly. And this is proven, they are also known for known a better method due to their slower kinetics, and they offer better manipulation on control over crystal growth and its stabilization. That's why I use this cyanobacteria for my research one. The objective of my study was screening and standardization of protocol for the synthesis of single nanoparticle from different cyanobacterial strains. And then I optimized it and I characterize it, and then I check some biological activities of these purified silver nanoparticles. My first objective was screening of silver nanoparticle from different cyanobacterial strains. For that, I choose 30 different cyanobacterial strains. They were grown in DOT at 30 degrees centigrade. And then biomass was harvested and stored at -20 degrees centigrade for further studies. And this was the protocol that I chose for my screening, only for my screening, but this was not the optimized one, and I optimized it later. This is my preliminary and the result of screening, and this screening work is published in journal of World Journal of Microbiological Methods. It's a journal from Spring Nature. And so I choose best strain for cyanobacteria for further studies on the basis of their size, shape, and time of reaction. According to the parameters, these parameters, microkeet was the best strain because the time reaction was only 30 hours in this, and the size was 40 nanometers, and that was spherical in shape. And this is the visual detection of all the 30 cyanobacterial strains. In starting of the reaction, the color of the reaction was transparent. And after 24 hours, it turned into pale yellow to reddish brown and brick brown. And this is the UV spectra of all the 30 cyanobacterial strains. And as you can see, this is the sharpest peak which came in microkeet species. And this peak is at 440 nanometer. And so on this basis, I also choose I also select my best strain for my further studies. These all are the SAM images all the 30 of AGNPs that were purified from all the 30 strains. And and the size of nanoparticle was 40 nanometer that was purified from microkeet. And then after after screening, I optimized my protocol for the better results screen for biosynthesis. So first of all, I did a growth curve of cyanobacterial strain by adopting optical density method, dry biomass method, and chlorophyll estimation method. And then I saw that in all the methods, I found that the stationary phase of bacteria was at 24th day. So I harvested this microkeet species at 24th day, and then I crushed that, I washed that, and I lyophilized that and make a fine powder for the synthesis. And I altered the reaction condition also, and for the better result that were biomass quantity, pH, temperature, and AgNO3 concentration. So these are the result from biomass. You can see that this is the effect of biomass on the synthesis. Biomass was hard. Biomass play a key role for reducing AGI. To optimize the amount of biomass concentration was varied from 40 microgram per 40 microgram per ml to 400 microgram per ml. Keeping and I keep other parameters constant like it was in the screen. And I found that 80 microgram per ml was the best for the AgNP synthesis. The AgNP, the synthesized AgNP showed maximum absorption peak at 440 nanometers. This is the microgram per ml. Like, and there was no aggregation seen in this concentration. As you can see this data, as the concentration increased, the peak shifted toward the red shift, and that is known. If peak shifted towards the red peak, it means that there are large particles in the synthesis, and this peak is at approx at 440 nanometers. So on this basis, I can say that 80 microgram per ml is the best biomass concentration for further studies. And this is the TAM results, and it shows the size of nanoparticles was 60 to 80 nanometer, and the shape was spherical. And this is the results of pH. The pH value of the solution were investigated. Exposure to the reaction mixture of different pH from the range of 3 to 11 showed different responses during AGN. Size of NP at 5.5 pH was 4 to 10 nanometers. This is the result from temperature, and I choose 30 to 60 degrees centigrade temperature for this study, and the best temperature was 50 degrees centigrade. And at this, the size of nanoparticles were spherical again, and the shape of the nanoparticle was spherical, and the size was 40 to 150 nanometer. The enhanced rate of synthesis of AGNPs might be the direct result of the effect of temperature on the functional group that were present in the extract. This is my final optimization condition, that was AgNO3 concentration, and I took from 1 millimolar to 2 millimolar concentration of AgNO3. And I found 1 millimolar AgNO3 was the best concentration for this synthesis. And the shape was spherical in this, and the size was approximately 20 to 70 nanometers. And then I took all the best condition for the final reaction. So I found that the synthesis held just after 12 hours. The time decreased from 30 hours to 12 hours. These were results of synthesis. In starting, the color was there was no color in the reaction mixture, and changes in condition. And then after the reaction, I purified these silver nanoparticles from nanoparticles through centrifugation at 9,000 RPM for 10 minutes, and then 10 minutes, and I washed these for 5 times. And then I characterized all the purified nanoparticles using SEM, TEM, XRD techniques. And this is the SEM results. And SEM and TEM studies reveal the presence of spherical nanoparticles in the EDX analysis showing that EDX analysis is showing that there is confirm the presence of EG nanoparticles in the samples, and EDX and particle size distribution data showed average size of nanoparticle that was in the range of 6 to 45 nanometer, and the maximum nanoparticles average size of the nanoparticle was 30 nanometer. Graphical images of nanoparticles. And this is the DLS data of 5 nanoparticles, and this is the FTIR spectrum of cyanobacteria, FTIR spectrum of cyanobacterial extract and AGNPs. That was taken to define the role of cellular biomolecules present in the extract and the AGNPs. FTIR spectra of AGNP solution was found to be less intense of AGNPs. Found to be less intense. The peak was absent at 1557, corresponding alkane and hydrocarbons. The peak for amide and amide group was also changed, also decreases. So on this basis, we can say that the member of amide and amine group is responsible for the capping agents of silver nano. XRD data is showing the 4 peaks between the silver nanoparticles are crystalline in nature. And after this, I did antioxidant. Different antioxidant assays of silver nanoparticles. And, these were DPPH, ABTS, nitric oxide and hydrogen peroxide assays. And antioxidant activity of AGNPs was showing the significantly high. It is very close to the standard. This is the standard, that was vitamin C, and this is the results from AGNP, and this is the extract. So this is showing the quite good antioxidant activities. This higher antioxidant nature of AGNPs is better for the drug delivery. Then after it, I did antibacterial activity of these AGNPs. In previous studies, antibacterial assay was done by well diffusion techniques against 9 different bacterial strains. The zone by adapting this methodology, the zone of inhibition was increased with increasing concentration. I took different concentration like 5, different concentration like 5, 10, 20, and 15. And the highest of zone inhibition was 16 mm that was detected against S1S. AGNO3 itself do not show any zone of inhibition. An examination of the mechanism for the antibacterial efficacy of synthesized AGNPs was also performed. And this is the fluorescent intensity data. This is fluorescent intensity of AGNPs, that it is showing that it shifted towards the left, that indicate that there is increase in ROS. For the and further, I did live dead assay. This is the live dead assay of bacteria, and it showed the maximum intensity in case of 20 microgram per ml. per ml. That was 93 this is 93.64. And these SAM images of AGNP's treated bacterial cell exhibit those dependent cell wall damage that leads to the cell death. In previous studies, it was observed that elemental silver is toxic for the microorganisms, but do not cause any harm to the animal cells. This capacity of AG can be hypothesized to be increased in the form of AGNPs because of its large surface area. All the data indicate the fact that AGNP exhibit concentration-dependent antibacterial efficacy by damaging cell membrane, and this is the hypothetical mechanism of cell death. It is hypothesized that the AGNP is linked to the here on the bacterial cell membrane, and that is responsible for the enzyme degradation, cell protein interaction, and cell DNA breakage to be liable for the cell death. I went to conclude my studies. I screened 30 different cyanobacterial strains, and I found microkeene was the best result, showed the best result in 12 hours. The size of the nanoparticle was, maximum size of the nanoparticle was 30 nanometer, and it showed maximum zone of inhibition. These purified silver nanoparticles showed maximum zone of inhibition against Staphylococcus.
Thank you so much, Dr. Shaheen, for sharing your work with us. Now it's time for question and answers. I can see few questions in the chat box. So the first question is by Garima. She says, "Dear ma'am, a variety of biosynthesis of silver nanoparticles are reported in the literature. How your waste of cyanobacteria is superior in comparison to others. Please provide the insight about their benefits to societal applications in terms of cost and management."
This cyanobacteria is very easy to grow. In less time, we can plenty amount of cyanobacteria, and this is very human friendly. These are bacteria, but human friendly. So these are not toxic. We are not. It do not harm human, and we can produce in plenty of amount in less time. So they cost like nothing. That's why I choose this.
Okay. The next question is by Abhishek Mishra. He's saying, "Ma'am, have you observed any difference in the antibacterial activity or change in any specific property of the silver nanoparticles over different strains of cyanobacteria? And what are the reasons that different bacterial strains show different property enhancement of silver nanoparticles?"
Silver nanoparticles showed more antibacterial activity as compared to the cyanobacteria. And in extract, in the combination of extract and silver nanoparticles, the antibacterial efficacy increased.
Okay, Abhishek, I hope that answers your question. The next question is by Reena Thakur, and it's quite a general question. It says that nanoparticles are sticky on formation. How to get them in powder form for XRD and SEM analysis?
Actually, I purified them through centrifugation and washed them by distilled water and alcohol, and then I dried them in a one and make a fine powder by sonication. Then go for the XRD.
Yeah, that is the general protocol which is followed in most of the chemical synthesis, that you centrifuge and then you collect and dry.
Yeah,
absolutely. Okay, Mariam is asking for the slides of this presentation. I don't know if your results are published.
This
or
is
not,
my
but
published data. This is my published data. I can give her. This
okay,
is published in Material Science and Engineering C, and actually this is published in 4 papers. Optimization data is in Microbiological Methods, Journal of Microbiological Methods in Elsevier, from Elsevier, and screening data is published in Springer Nature Journal, that is World Journal of Microbiology and Biotechnology, and antibacterial data published in Material Science and Engineering C.
that's wonderful. So
I
Mariam, you
give,
can get the presentation.
please give me your
from the
email ID.
organizers.
I will mail you all the papers.
Yeah, sure. Okay, the last question says, hopefully last, that have you checked the toxicity studies of these silver nanoparticles? This is from Anu.
Yeah, no, I didn't. But in future I will do that. I know that I have to do that. I will check definitely.
Okay, so I don't think there are any more questions from the panelists. If there are any questions, we can take them up.
Yes, I will. This is not a question for Dr. Shaheen. Thank you, Shaheen, for
Thank you.
coming in, and I think we asked her to go ahead of time. Thank you for that, for managing your talk. And a couple of quick questions, even related to toxicity. I feel, anyways, when it is a biogenic synthesis, the toxicity level reduces than what
Yes.
is seen chemically.
Yes, ma'am.
So,
Yes.
but anyways, Dr. Shaheen is in the process of studying the cytotoxicity. But Shaheen, would you like to comment on, like you were saying, yes, these cyanobacteria are good bacteria, friendly.
Yes,
So,
ma'am.
did you really not face any kind of challenge in these kind of biogenic synthesis process?
Challenges as such? No, ma'am. Because I am used to do work on that, so I
So,
don't
like
feel that there
compared
is
to,
any
I
challenge.
would say, a chemical synthesis, is it all?
Yes, ma'am. It took
those-
long time. It took
Okay.
long time. Chemical
Time-
synthesis are very
time is
fast,
a
but
constraint,
it
right?
took.
Okay. Okay. Thank you, Shaheen.
Thank you so much. Thank you so much for giving me the opportunity to present.
Thank you so much, Shaheen.
Thank you so much.
Okay, so is Monica around?
Yes, ma'am. Yes, ma'am.
Great. So we can go ahead with the session.
Thank you, Dr. Shaheen, for such a wonderful talk. Next in our segment, we have Ms. Mausam Chaudhary, PhD scholar at AINT. Ms. Mausam Chaudhary is the Senior Technical Officer at CIPET under Department of Chemicals and Petrochemicals, Ministry of Chemicals and Fertilizers, Government of India. She is now posted at Aurangabad, Maharashtra, and has been working for more than 15 years. Her experience speaks of the vivid achievements in the areas of petrochemicals, plastics, polymers, and their elite composites and nanocomposites. She currently heads the academic team under AICTE approved long-term course as an HOD for diploma, post-diploma, and postgraduate diploma programs, and also heads the skilling department and is responsible for assessment core committee for policymakers under joint entrance examinations all India, establishing NSQF levels under machine maintenance, plastic production, and CAD/CAM mold development areas. She has also received several awards for her sessions, deliberations in the areas of plastic recycling, plastics, and petrochemicals and mass awareness under skilling department, and is an eminent speaker for state government agencies like MCED, District Collector, MSMEDI, DIC, etc. She was also nominated to the University of Toronto, Canada by Government of India in 2010 for over a month for her research expertise and has worked closely on wood polymer composites. She is also a social reformer and mostly speaks about women entrepreneurship and empowerment. In the areas of polymer technology, she has won patent and several international publications. To her credit, and also has won many awards for presenting her work in several international conferences like International Conference at IIT Kharagpur and MIT, etc. Today, she will be engaging us with an insightful talk on plastics and polymer nanocomposite for recycling, economic and social sustainability. Platform is yours, ma'am.
Yeah, thank you so much. Ma'am, am I audible?
Yes, yes.
Good morning, everyone. And it's really a pleasure being invited to deliberate a few words on this hot topic of recycling. So Yeah, as very well said, I've been working last 14 to 15 years in the area of plastics, polymer nanocomposites, and the
Ma'am,
burning. Yes, ma'am.
ma'am, you will have 30 minutes for the talk, followed
Yes,
by 5 to 10 minutes of question answers. Sorry.
yes.
Now you can continue.
Thank you, ma'am. So today's topic would majorly deliberate upon what plastics and polymer nanocomposites are, and how much streamlined we are, and how much India is progressive. There's a lot many discussion happening worldwide, which we call it as a global level, and they talk about the sustainability. So sustainability is one of the most burning topics, and we'll be discussing that also. Plus, what all we have to offer, like we from CPET, because I represent both Amity as well as CPET. I'm a research scholar there, and I'm working with CPET last 14, 15 years. So this is how we go ahead. So this is the first slide that we shoot. Um, we are going to discuss about the sustainable polymer nanocomposites. When I was browsing through the articles that were posted yesterday and day before yesterday, we had a plastic waste management workshop. This workshop was majorly discussing about the single-use plastics, plastic recycling, and the EPR, the end producers responsibility. So we had a lot of industrialists who discussed about the sustainability also. So sustainability to a major core, what about to discuss that what if polymers are not going to sustain further. We all know that petroleum products are the major agenda that talks about why and where we take polymers ahead. Now, petroleum products, they give naphtha, and the naphtha is further cracked down to polyethylene, polypropylene, and different kind of monomers, which are further polymerized to make a polymer. That is how the main streamline thing is for the polymer thing. So when I talk about polymer, automatically the word rubber and plastics and polymer nanocomposites and composites, they come into picture. Now, discussing about this, we will be seeing the antibacterial polymer nanocomposites. We'll be talking about the sustainable polymer composites as well as their framed nanocomposites, the characterization and application of micro and nanocellulose based environmentally friendly polymer composites. We are seeing a lot of cellulose nanofibers nowadays around, and even on I believe 5th of June, when we had the World Environment Day, instead of planting trees, nowadays people are like distributing the jute bags, which is kind of a very old thing. I come from West Bengal. I know jute is kind of, I don't know how many decades old thing. It's majority production has been done there, and then this eco-friendly bags and the cellulose nanofibers, they are now, but then jute and everything has been done for quite a long time. We all know polymer plastics being a wonder material, and that eco-friendly nature is known to us. Issue is the littering part. So we'll be discussing about the cellulose nanofiber and the eco-friendly polymer composites, and then the characterization and applications of these synthetic, polyolefin based eco-friendly polymer composites. So discussion about these things will bring light. So first we start with very briefly, what exactly are we going to discuss about the innovativeness. Now today's topic is about a sustainable thing. If I talk about the sustainability of polymer nanocomposites or its innovativeness, we are going to show, or we are going to know, that the world is actually dealing with a lot of supplies of this petroleum products. Now petroleum products, in the coming slides I'm going to show Bureau of Indian Standard, BIS, it's a government body. It regulates each and every consumer product which comes in the market. You and me, we all use consumer products. Anything that reaches us through the forum is that. So anything and everything is actually hallmark or it's BIS mark. So BIS, Bureau of Indian Standard, plays a major role because it's from India. So it represents the Indian standard. In short, technically, it's also called as IS standards. So we'll be discussing that PCD department of New Delhi, it's situated there only. The head, yesterday we had Srimati Meenal Pasi ma'am, and she was like telling us how BIS is dealing with these kind of progressive petroleum products. We call it as PCD department. It's a very important department. I'll show you in the coming slides. Now, we have a lot of dependency, on these plastics. I wake up in the morning and I take a brush in my mouth, and I sleep in the night and I switch off the lights, everything A to Z. We have these plastics around us. So we need to have a regeneration, of these products with 100% renewable resources. Now you will tell me that Mosam, this 100% renewable resources is also a very old idea. बहुत दिनों से चल रहा है. How do you connect? So this is a major solution for environmental impact. Now, polymer nanocomposites comes to the rescue. The major things that industries do not know, or maybe they do not want to know, because industries, they are into business. They are manufacturers. They'll buy a blown film plant. They'll manufacture blown film. They'll send it to maybe this Big Bazaar or DMart or any other supplier. The end user is now the Big Bazaar or DMart, and now they'll install it there. We are the consumers. We take that and we fill in vegetables. We get it sealed and we bring it home. Now that the entire thing comes on us. Now we are the end user consumers. So these all things, it has to be implemented in the first place that the petroleum based plastics may please be replaced by polymer based bio nanocomposites. That is the talk of the day. Now these bio based natural polymers, what are those? Everything that we know, the chitin, that is the chitosan, the collagen, the keratin, the starch, these things, when they are functionalized. Now they may be functionalized from different areas. They may be functionalized with carbon nanotubes, with these graphene, with the nano clay, with the metal, nanoparticles. With all of them, this is the coming future. Tomorrow, like whenever I take any classes for, we had this women entrepreneurship program on 17th of June. I had a lot more. I had an opportunity to speak about this upcoming future. The people, they have a second-hand machine and they manufacture, and they're making something. They're doing a good packaging. They're selling it. They have export licenses. They do it in India. They mostly do it outside. They export it. When they export, what is the new future that you have? The new future is the recycled polymers. One, or single-use plastics day after tomorrow, like on 1st of July onwards, you will not see single-use plastics, and if somebody does it, it will be illegal. So it's all published everywhere. Single-use plastics is a big no. So this is the new future, bio-based natural polymers, which talks about the chitin, that is chitosan, collagen, keratin, starch, PLA, PBT, the biopolymers, biocompostable biopolymers, and biodegradable polymers. These three are three different arenas. People generally change and mix and match, and people do not know what is what. So that is where we come. So what are the possibilities for advanced eco-friendly packaging? So I'll just browse through this quickly. Eco-friendly packaging is the new requirement. बहुत सारे हो गए MSMEs, like MSME is a different ministry, and the pollution control board comes from a different ministry, and then CIPET is a different ministry. But then what people have been portraying is, make industry dalo, be an entrepreneur. Okay, start your own industry. You can start it with a small scale. You'll get, say for example, 200 crores, 75 will be given, 25 only you'll have to take care, etc., etc. But then what happens day after tomorrow if you have to close your company? So you'll have to go for eco-friendly packaging. You'll have to go for fibers and clothing, like 1200 liter goes in making one pair of jeans. You do it with recycled PET, what Levi's does. So that is how the tissue engineering, antimicrobial sensors, this. So we are going to throw light upon the environmental industrial. So earlier one was sustainable. This is the industrial and environmental applications, wherein for the rescue, polymer nanocomposites are there. So these polymer nanocomposites, first and foremost, to know the least, plastics or polymers, they are nothing but long chain, called as macromolecules. Monomers, they join hands together, they make a long macromolecule. Now this macromolecule, when you infuse them with some kind of filler or some kind of fibers, or maybe some kind of additive, anything which is added to them, which would make it a composite. Composite means one is a matrix, another is a filler or a fiber. It comes together. This has got an outstanding potential. So this is a composite. Now, when you add nanofiller to it, sir, it becomes nanocomposites. So polymeric nanocomposites are those wherein the composite's basic matrix is a polymer. So polymer nanocomposites, they have an outstanding potential, as you can see here. And nothing comes near, because of, especially if I talk about the packaging, because today's topic is about the recycling and the environmental thing. Recycling, packaging comes in forefront. And when we talk about the packaging industry talks about the synthetic polymers, specifically of the virgin grade. When we use virgin plastics, for example, yesterday my son went to a birthday party and he got 3 chocolates. He ate the chocolates and he kept the wrappers in his pocket. Seeing him, his friend also did the same thing. And his mother hit him, why are you keeping those wrappers in your pocket? You're not supposed to. You throw them in the bin or you throw them out. So I told her, educate your child to not litter plastics. Plastics has got no replacement. So we are going to coin them with the polymer nanocomposite. Second is low cost and low weight of polymer nanocomposites. Third is extended scope. Industries only know हमको manufacture करना है. These are the three different primary production equipments: injection molding, blow molding, extrusion. They do not know what is the extended scope. That is the new. There is a new pool, we call it. That is extended scope for these applications. So we are going to check what are the methods of preparation. Polymer nanocomposites can be done in situ synthesis, can be done by solution mixing, can be done by melt blending and electrospinning, of course. So today's talk of the day is environmental and industrial application of polymer nanocomposites. They are there. They have always been there, in the areas of water treatment, electromagnetic shielding in aerospace applications, sensors, food packaging, which is the new challenge, and the makeover. So I'll show you, if you can see on the screen, these are the left hand side shows a mold. Dhacha bolte usko, the mold. Why is a mold required? Because you need to make these samples. Why are these samples required? Because you are actually making samples to check if your polymer nanocomposite is actually going to replace the conventional synthetic plastics which are there. And that is how you're going to talk about the sustainable thing. Everybody talks about your biodegradable istemal karo. We do not know if biodegradable would be equivalent to a synthetic plastic. You need to check, verify, analyze, and then portray it. To analyze, you need to make samples. Samples have to be made as per international standard as well. If you want to publish them in an international journal, the samples are to be made as per international standards. They have to be conditioned as per international standards. They have to be tested, verified, and analyzed as per international standards. Mostly they are ASTM. We use BIS, Bureau of Indian Standard also. So we do it in both, for progressive, for applying for tenders, we do it inside India. For outside India, we do a comparative. So we use this. So these were the, sheets which were made. You make a sheet, you cut it with your hand, you induce some kind of stress. So you need to make samples. Samples can be straight away molded. So molding of samples can be done using this. So this is how it has been made. There's a mold. So when I use these samples and I make samples and I make these molds and I go for testing. Now I'll show you how to test these polymer nanocomposites, which will tomorrow speak about their superiority as compared to the virgin synthetic plastics which are randomly available anywhere, in my neighborhood and your neighborhood. So you need to get it tested through a plastic testing laboratory. The laboratory that I'm talking about at CPET under Ministry of Chemicals and Fertilizers, Government of India, it is equipped, situated at Aurangabad, Maharashtra, from where I'm at the moment I've joined. It talks about the state of art facilities, and it does as per ASTM, as I told you, international standard, ISO, International Organization for Standardization, Bureau of Indian Standard, BIS standardization. And we are accredited by NABL. We are done by as per ISO IEC 17025. This is very interesting. I'm also an auditor for ISO IEC 17025. I can go and audit any laboratory as such. And recognized by BIS for more than 64 standards. Now 64 standards means more than 64 products come into range. These products can be in mechanical, in chemical field. Mechanical, you will say, we have no relation with mechanical. Of course you do. The phone you're using, if you drop the phone and it breaks in the very first place, you'll say, yeah, the quality is really bad. Mechanical, any kind of pressure, stress that you induce and it still takes is like mechanical stress. Chemical talks about the chemical field. Then we have thermal, we have electrical, we have biodegradation. So these all things are there. I'll just go further. We'll quickly skip. We have a lot of slides as such. So these are all the, recognitions, accreditations, recognition, certifications that are needed. For example, if you have a pipe plant, you want to give it to the PWD and you want a certificate out of it, you have to come to us. You are manufacturing a recycling film, very simple. You want to give it to the government, you have to enroute it through us. So it has an enroute. So enroutment for the polymer nanocomposites are needed because you get a certificate which speaks, is it really biodegradable? And why has this come up? Since Say No to Plastics banner was on, people started showing non-wovens. Non-wovens are those plastics which are used in the sanitary napkins, which are used in the children's there's mammy poco pants and all, any such thing. Anything is a non-woven nowadays. Earlier we saw Subway and all, they used to give packets. We thought it is cloth. It is not cloth. It is non-woven polypropylene. So, but then it's not biodegradable, it's the same. It's non-degradable. So these are the certifications that they need to undergo. And apart from that, this is a list of instruments that we can actually render, and we can actually go through. These are some of them. We can also make the samples. And why are these required? These are required because we are coming up for a new future. The coming future is going to stop. Earlier, we saw say no to 50 micron plastic. Then we saw say no to 70 micron plastic. Day after tomorrow, say no to 120 micron plastic. Every new time we have a different change. I mean, an amendment, a different voice from the government speaking about say no to plastic in a different way. So accordingly, the industry people are also going to change. You and me will also change. Tomorrow, if I go to print a invitation card, marriage invitation card for anybody, the plastic which is an enveloping the the marriage invitation card, if it is less than 120 micron, somebody is going to help me responsible for it. And if I tell them I am bought it from such and such shop, they'll go and rate the shop. The shop says I bought it from such and such wholesaler, they're going to rate the wholesaler. So the end user producer's responsibility becomes the focus of the day. Like we file GST for everybody, we are going to file the EPR for every single area. So I'll show you how the plastic production or the testing happens for your nano composites, which are used for your social and this particular environmental sustainable mode. We are going to test it for every single way. And these plastics we use, we have a students also. You can see it on the you can see it on the this screen that the students are doing it, and the samples are to be tested with a lot of confidentiality, because tomorrow when you work with the quality control department and there are around 100 samples of biodegradation or maybe 102 samples of some other companies, they are fighting their competitors in themselves. So confidentiality becomes a very important clause, and we also sign MOUs accordingly. So yes, so these are the different products that can be checked by us. And these are only 64. Can you just imagine? We have only a list of 64 products that we are entitled under, of course, Bureau of Indian Standard. But then when you talk about the sustainable part of plastics, plastics can only be recycled, dear participants. We cannot go for saying, say no to plastics because we do not have a replacement. Of course, paper cannot be a replacement. It never was earlier also. And metal becomes too non-versatile. Plastics are the only thing. So instead of saying no to it, we can say no to the single-use plastics, and we can go and recycle, reuse, and reduce the normal plastics which are available. So in front of you are those products which can be recyclable only. Now recyclable are only the thermoplastics. Thermosets are non-recyclable. These are known worldwide. So thermoplastics, the following products which are there on screen, they take care of what is used. The parts you see in blue are actually the agriculture-based plastics. Now these are the polymers. These are the plastics, the polymers which have been mended through pressure and heat and made into plastic fittings. Now these products are purely plastic products. When I talk about nano composites, the first thing, if you see IS 2508, this is talking about, I'm just giving an example. I'll not take much of your time. This is an example, polyethylene films and sheet specification. Now tell me, if a simple polyethylene film comes to me, and I'm unable to take care of the polyethylene film because I know it is getting banned from 1st of July, I'll have to come up with a particular nano composite film. It is very easy. It looks very difficult. It's very easy. Just distribute some amount of filler into it, maybe nano based, you make a nano composite film. Check the barrier property, check the permeability, and then come back with the same specification. Any film can be tested as per IS 2508. Film testing is separate and sheet testing is separate. All the difference between a film and a sheet, as it logically sounds, is just the thickness. So you have ropes, you have this. I'll just go through it quickly. And these are, these woven sacks. If you can see woven sacks. I remember in 2010 when I was posted in Haldia, West Bengal, we were woven sacks talk about the, it is a PP, polypropylene and HDP, high density polyethylene bags which are used for packaging of cement or maybe fertilizer, maybe your food grains. Imagine if any of the PhD scholar comes up with an idea that, ma'am, why do it 100% pure virgin? Why not add some kind of composite, filler to it and make it a composite or nano composite, and then let us go for testing. Any composite can be tested for this 11652. You can actually patent it in case if you have a composite. Say you are patenting, one is patenting with a 2% of filler, another is doing it with a 0.5, 0.1, different filler composition, different patents, and they can be done. They can be tested, and once you have the test report, you can actually apply for the production anywhere elsewhere, right? So these are the products. I'll just quickly browse through it now. The proposed list, which we went to add on further. People are saying that we have a depleting line of water, then we need the geomembranes, we need the tarpaulins, which are actually textile, but they have a HDP, high density polyethylene lining. So these are the woven fabrics. The non-woven are, which I gave you an example of the kids and all, the cocoa pants, the diapers and all, they're non-woven. The sanitary pads are non-woven. These are woven. Anything that we weave into a warp and weft lengthwise and widthwise is woven fabric, and we do it using HDP fibers, of course. Yes, you heard it right. We do it using the HDP or the PP fibers. We also, the water bottle that we drink, talking about the sustainable future and the coming present, the PET bottles that you actually throw out of your railways, like, near the airports, railway stations, they can be taken up. They can be actually, again, made into fibers. They can be woven into sheets or like fabrics. And maybe jeans can be made out of it, shirts, you and me, we can wear. So these are the things that are to be added yet. And I have kept some topics which are related to horticulture and agriculture. I'm just leaving it to the audience that you can tell me. I still have slides pending. I'm just leaving this particular slide to the audience that these are the things that are needed, in the coming future to be made out of, particularly out of a composite, I may say that. But then these emitters or maybe these sprinkle pipes, if you can see these traps, they are made in SIPET only, and they have been given it to different government agencies so that the crops and all, they do not get damaged by those insects. So these are some of the many things which we do. This is a very interesting thing for the topic of the day, the biodegradation test setup. We do it as per standard. Obviously, it has to be as per standard. The standard talks about ISO. We can also do it as per BIS, Bureau of Indian Standard. We can do it as per ASTM, and we can also do it as per ISO. So this is as per ISO 17088, the compostability and the biodegradability of your plastic. If anybody sees a biodegradable plastic garbage bag being sold by XYZ, they can talk about it, or they can actually mark it. They can ask a question to its manufacturer. Sir, are these really biodegradable? If they say yes, you can mark a copy to any of the government body who does this biodegradation test. To just tell you, there are very few government bodies who do this particular test, because it takes around 6 months for the test report to generate. And after we are done, we find out that if the real polymer is actually biodegradable or not. Who tells us if it is biodegradable? And only if it's biodegradable, if it's compostable, it is going to be the new polymer for the sustainable future for us, right? So we are going to check how it works. So these are series of equipment, and these are the series of facilities that have been coined together. This is the laboratory in the first plot that I set here. So this is how the biodegradation has to take place. I'm not going to teach you how it goes because that is not the topic of the day. But yes, biodegradation is a new requirement, and for a sustainable future, people have to sell or go by the biodegradable polymers or biocompostable polymers or compostable polymers. Yes. Now, just to check if many sellers are selling it with the name of biodegradable, you can go with a test setup. So, which is something that we have. Now, these are the toys. Why do we have toys? If you see on the left-hand side corner, there's an Atmanirbhar Bharat logo that I've kept. We keep getting, the requisitions. We keep getting the star-rated questions from the ministry that, okay, from China, we have to reduce the import and enhance the production in India itself, so that we increase the employability also, one, Two is we go on a Atmanirbhar Bharat module. So when we go with that, we have to talk about the consumer applications. And when we talk about the consumer applications, we have to see that what thing is mostly imported. So we went with the toy thing, and I have just put down some of the consumer applications, which shows which toys are actually working up the best. Tomorrow, if somebody wants to actually put up their company, they can come up and check which toys. I've done a small survey also, which is of course not much of my need, but then this can be taken care of. And here is where polymer composites and nano composites they come into picture, because in the future we cannot have plastics which has lead into it, plastics which has high amount of mercury into it. We see the blood bags, there was a Raktadaan Abhiyan here only last Sunday, and people are using PVC blood pouches. We do not know if it has got lead content in it. Everything and anything can be checked for its composition, and then we can replace them with the particular nano composites which would have equivalent property. And this is a challenge, if I put it across for my research scholars, for my students, I'm also a research scholar, it is also a challenge to me that these are the things which can be worked up. Okay, this is, I'll just skip. Now, talking about the reverse engineering, I have kept this slide because many people, they come to us that for a sustainable energy basis, I was checking with a, like an Excite battery, just giving a name, not to take a name of any of the make, just a battery. Battery is made of black in color. If the battery is black in color, the dabba we see, we understand it's a recycled plastic, fine. Maybe if it has a right thickness, it is recyclable. Tomorrow, the CPCB, Central Pollution Control Board people won't even stop it. But if you have an idea, you have a product design, you can come to us, we can patent it. So during the patent, we do a reverse engineering, So these are the steps which are involved in reverse engineering. Like, for example, during COVID, when we saw that the, bottles of sanitizer went on black, and people were coming up, mujhe bottle banana hai, and they come up with an existing Lifebuoy bottle or Santur ka bottle, and we tell them, no, we cannot do it. It is under Copyright Act. We cannot do the same bottle. I cannot produce at least. So we do a reverse engineering. We finalize another design, and we come up with analysis, indigenization, and then that is how we develop a prototype. It goes for a validation, and that is how it is developed. So talking about the recycling at the moment, as I told you, under the BIS, Bureau of Indian Standards.
Mosam, sorry to interrupt. Can I please ask you to wrap up within few minutes?
Yes, ma'am. Just 5 more minutes, I'll take, ma'am. Thank you, ma'am. So this process of standards, this would actually involve the consumers, the regulatory bodies, R&D institutes, laboratories, and other member secretaries of BIS, which possibly talk about how to recycle and how to change over from the synthetic plastic or the petrochemical to the major polymer nanocomposite sector. So there is a stepwise draft, like, you make up anybody, if you and me, any of the students, any of the research scholar, any of the common person, any civilian, if he or she wants to make up a standard, they are they are welcome. They can go to the BIS portal, Bureau of Indian Standard. That's a Government of India portal. They can propose a standard, that, okay, I feel this is how it has to be tested. And then the standard works. It takes its own time. It's a new work proposal. The draft goes and gets submitted. It's a preliminary draft which gets approved. Then it goes for a circulation. Like, there are many people who may say, no, this is copyrighted. This was my work. See, I've published it. So it goes for a period of, say, 3 to 6 months, wherein it gets tallied and validated, and then the finalized draft comes up. So this is how it goes. And I am particularly talking about this topic because we are polymer or the plastic nano composite. So this comes under PCD, that is Petroleum and Coal Department. Petroleum talks about naphtha. Naphtha talks about all the synthetic plastics which we are using now and which may get banned tomorrow. So these products are there in the front. So this is PCD. It's like Petroleum Coal Department of this. These are some of the standards which are like produced and which are single use. They are getting banned. No wonder. There are many companies, many industries who are going to lose their jobs, who are going to lose a big chunkable amount of their work. But then there has to be an alternative. So today's topic, the theme is such a burning thing. I mean, even the government officials would agree to it that the packaging or the pouches, the water, your tomatoes, sauce which is given in the sachets have been actually stopped. You won't believe, like in the government office also, they do not use it now because they are multi-layered and they are less than 100 microns, right? So these are the things. I'll just quickly browse through some of the products and pre-consumer sources. Yes. Now, where are the pre-consumer sources of materials that we would want to discuss? So the sources are like plastic producers. Anybody who is producing the plastics, plastic is from polymer. Polymer is the basic monomer se bana hua polymer, and then it goes under heat and pressure and then gets treated and it's made into a product. These usable products are the plastic products, and people who make these are the producers. So plastic producers, off-grid materials, processors. There's a primary processing, secondary processing. So these are processors, scrap products, and others. Post-consumer disposables and durable. So I'll just quickly go. These are the guidelines. You can browse it to the website also. If you want, I can share my slides. I know the slides are kind of really a lot. So you can check if you find Aurangabad very far, you can check any of the CPET center under government, which is located near you. So we are around 42 centers old. Basically, we have 46 centers old. Another 4 got inaugurated last 2 months. I have not uploaded it here. So we have pan India presence, and we work with a STAR concept, skilling, technical, academic, and research. And we are here to help with the research part here. And I am also heading the skilling department, as ma'am very well said. And these are the NSQF levels, National Skill Qualification Framework levels, on which we work. So level 5 to 6 is this is diploma, post-diploma, and postgraduate diploma, which is also taken care of here at Aurangabad. Level 1 to 4 will be the complete skilling, and the skilling certificates are NSQF compliant. Level 10 is, of course, the PhD. CPET also offers PhD. So with this is what we are, and this is me. And thank you so much for patiently hearing. And I'm sorry for skipping the slides more. Maybe I had more slides. And thank you, Richa ma'am, Rano ma'am, Mittal sir, for giving me this opportunity, and also to OP Sinha sir for enabling us, attend this and give a presentation. Thank you, ma'am.
Mausam, we must thank you for educating us on this very current topic of interest. Okay, we all should be educated in this topic. Thank you so much.
Thank you, ma'am.
Now the time for questions. So we have a couple of questions over here. Aniket is asking, what about nanocellulose? Can it be a replacement to plastics?
Yes, Aniket, that's a very good question. Cellulose and nanocellulose, there's a wide difference. Cellulose is normally available, and we all know it's a natural polymer. When these cellulose are used using an electrospinning or maybe some other method, and they are drawn into thin fibers, these fibers can be added as a additive to the base matrix. So a direct answer would be exactly no. It cannot be a direct replacement of the plastic, because if you make any kind of composite, Aniket, you need a matrix. Matrix is something that binds it together. So nanocellulose will be fibrous. To attain it, you would need a production unit. Yes, if you have a equipment which gives X and Y, Z tons of material per hour, per day, on an 8-hour shift, then yes, you can think of changing it. When we do it on a lab scale, no, it may not be used at the moment. To replace it, we may probably need a TOT, transfer of technology, in case if we come up or we make equipment which produces or which is able to give so much of nanocellulose fibers in one go. So yeah, Aniket.
The next is, I don't think it's a question, it's a statement basically, which says that many researchers are doing nanocellulose for plastic application, especially in packaging, since nanocellulose is renewable and biodegradable. This is by Jessalyn Grumo.
Yes.
Do you agree to this statement?
Yes, ma'am. Yes, ma'am. Okay. And nanocellulose will be the coming future. As I said, it will be added in quantums of fiber. Now, this is an extended question of Aniket also, because I understand when we make a composite or a nano composite, we mix two different things. One is a matrix, another is a fiber. the matrix becomes the 70 to 80%, sometimes 90% of the composite, and 10%, 2% to 10% becomes the fiber. So nanocellulose, when you add it, certainly it becomes a bio-based composite. But if the regulations of CPCB are to be seen, Aniket, I would tell you that Central Pollution Control Board is talking about the thickness, and in the packaging applications, if the synthetic fiber is able to withstand or give a good, barrier property to the air. For example, if you're packing a particular Maggie and you sell it in the market and you say it is good for 6 months, and you're using a particular PP or a PE film, tomorrow you make a composite, a nano composite using nanocellulose fibers. I'm just talking about a practical point of view from the industrial level. If you're doing that, and if it does not stop the oxygen from coming inside and the inside oxygen to go outside, maybe it won't last for 6 months. So the problem of packaging, especially for food products, may come into picture. I mean, I'm talking this because last week I had a lady who gifted me a bottle of Ashgod, क्या कहते हैं उसको शरबत, Ashgod sharbat, and she was telling me that, ma'am, the sharbat is for you, but this is a bottle. This bottle is of 500 ml, but the manufacturer has made a little bit big. So I give 500 ml, the extra amount of area which is kept open, that has got air into it. So when I seal it and I sell it, it goes to Nagpur, which is high temperature. It goes to Mumbai, which is high in humidity. वहाँ पे जाके the product, it goes bad because of the permeability. So that is the problem. The leachability, barrier property, or permeability of natural polymers is a big challenge as compared to synthetic. Otherwise, ये बहुत पहले this would have been replaced. Yes.
Absolutely. I think we can have a one-day awareness session with you, because this is really a matter of concern for the entire globe. Thank you so much, Mausam, for such an informative talk. Now we move on to the next speaker. Monica, are you there?
Ma'am, with your permission, I'll. Yeah, thank you.
I think Monica is having some network issues. This is the main disadvantage of the digital media. Anyway, we'll proceed with the next lecture. So moving ahead to today's last lecture before lunch, we are pleased to welcome our next speaker, Dr. Anjana Dogra. The brief introduction about the speaker: she received her BSc degree from Osmania University, Hyderabad, MSc and MPhil degree in physics from Saurashtra University, Gujarat. She completed her PhD in physics from Inter-University Accelerator Center, New Delhi, and Himachal Pradesh University. She started her career at Bhabha Atomic Research Center. In 2008, she joined CSIR National Physical Laboratory as a scientist. Currently, she is working as principal scientist at NPL. Her research interest is oxide heterostructures, thin films by pulse laser deposition, low temperature physics, and magnetic materials. Her research work has been published in 59 SCI international journals. She is also involved in international and national projects as principal investigator and co-principal investigator. She is the member of many societies, including Meteorological Society of India, Magnetic Society of India, Neutron Scattering Society of India, Swadeshi Science Movement of India, Organization of Women in Science for the Developing World, OWST. Today, she is going to discuss with us the role of thin films towards smart nanotechnology. So may I request now Dr. Dogra to throw some light on her topic. You will have 45 minutes for the talk, followed by 15 minutes of question answer session. Over to you, Dr. Dogra.
Thank you, Dr. Richa. So, please stop me in between whenever I'm exceeding the time in case. And is audiences able to speak in between, or because I was thinking it can be an interactive.
They'll be able to speak in the end.
Oh,
maybe
okay.
They'll put up their questions in the chat box, which we will share with you.
Okay, fine. So as the topic suggests, we will be into the thin films, and I will be describing how these thin films can be useful for the nanotechnology. This background is of our institute, National Physical Laboratory, NPL, the NMI of India. NMI basically National Meteorological Institute of India. So coming to this thin film, what exactly thin films? Of course, since as I understand, the audience is from the nanostructure background, so they might be aware of these few things which I will probably be sharing with in my slides. So as we go to nanostructures, we say the sizes have been reduced. So similarly, when we talk about the thin films, again we are talking about thin comes into the picture. So again we are talking about the dimensions. Okay, so the material whose thickness is very small, almost negligible, I should say. So as compared to the other two dimensions, as we are aware, like this figure shows XYZ. So if we have the dimension, one of these out of three dimensions, I have reduced one dimension and I'm coming to two dimensions, then I am into a thin film range. And of course, if I'm saying this definition, it has again the vast definition, which I will not go through that. So thin basically, which is very less, about 1 micrometer, or you can say 1,000 of nanometer. Okay, and film is nothing but when you are depositing some layer on some other material. So that is a thin film. Okay. So as this figure is representing, when your like thickness is very less compared to the length of your material. Okay, so one dimensional is significantly smaller than other two, which I have represented in my earlier slide. So basically the interest in thin film is, as you people are also interested in structures. So this is also, you can consider the thin films are into the nanostructures only. Okay, so the interest is similar, like basically the properties will change when compared to the bulk material, and the thickness, film thickness and microstructures will basically control all these properties. Okay, so for example, I have given this indium oxide material. So if you see the indium oxide material, if it is in 300 nanometer thickness, then it is act as an infrared reflector. However, if you reduce down the thickness to 2 nanometer, then it acts as a Josephson junction. It can be used in Josephson junction kind of devices. So this particular figure I have shown, like probably in class 12th or 11th, this experiment was there, first experiment which you have seen in your school days. It's a oleic acid which you put in the water. So oleic acid is a soapy liquid and which has the molecular size of order of 10 raised to minus 9 meter. So nothing but you take a pipette and then put the drops in that liquid, the oleic acid in that liquid, and a kind of layer is formed. Okay, so basically the oleic acid is spreading in a thin film form. So this is the first example basically when we talk, when we see in our school days. So this is the thin film. So if you see the thin film, if I'm saying a lot of advancement has occurred in thin films or nanostructures, but the creation of the thin films, when we talk about, since we are reducing the thickness. So in the earlier days, basically in Egyptian time, in 2500 BC, when people are basically melting and I mean, they are beating the gold and bring to some different shape. So they used to make, like for example, in this leaf samples which they can produce in the 18th dynasty, that was the period of 1567 to 1320 BC. It was the thickness they could have produced to 0.3 microns in thickness. So in that way, thin films has the existence from our ancestors. I mean, long time its existence is there, but only the change has been happened that we are reducing the thickness with day by day. Like if you see your here, it is 75 micron. Okay. So this is where I just want to have the interaction. Anyhow, I will just start with this. The left hand side picture showing the Graham Bell, who is using the first telephone when it was discovered by him, and the right side of image is basically of Martin Cooper, who has discovered the first cell phone in 1973. Okay. So if you see the cell phone, the size of the cell phone, which they also used to call it as a brick. It's the size of a brick. Okay. So it's very heavy and it is the size is too big. So that is why they have called it as a brick. Okay. So this has a battery life and which allowed to talk. A person can talk only for the 30 minutes. At the present moment, we cannot even assume. This much time we will have the battery backup, 30 minutes only. So how this brick size has been reduced to your small smartphones, which you can simply insert in your pockets and hold in your hands, and you can move around. Okay, so it is just because we are able to reduce the sizes of the electronics. Okay, and how we are able to reduce the size of the electronics? Because we are able to grow the structures or the microstructures into the nanostructures or in form of thin films. So that is the boon of the thin films or nanostructure that we have come from those kind of brick size. One example which I am trying to show, a brick size of mobile to a small smartphone which can be which is in your hand presently. So in first phone, the smartphone was launched in 1993, and which was basically it was from IBM, and you can see the change in the size. I mean, from this 1973 to 1993. And this particular image, the bottom one, where I am showing this Dynatac Motorola 1983, and from then 1999 Nokia, how the sizes have been changed. I could not show the thickness of these phones, but they were very bulge kind of thing. And now you are aware, like I don't know how many of you have seen, because it's our time when we have seen these bulky phones, and now very sleek phones we are using. So I have shown this basically graph to 2012 to Galaxy S3 Samsung. So the purpose of showing this particular image is the growth of nanostructures or the thin films impacting the advancement of the technology. Okay, that is the purpose. So this is the exponential growth is possible because of the miniaturization of the cell phone, which has made the cell phone smaller and smaller. And it is not only the smaller and smaller, the functionality in your phone has been increased. Earlier, we used to generally just talk like a normal telephone, okay, like landlines which I have. So, but now it's a multifunctional material. You can take pictures, you can record something, you can also create PDF files, I mean, a number of things. So we cannot say now it's a phone actually. It has a multifunctional, some different nomenclature we need to really discover actually. So this is the boon from the thin films. So this is one of the other example which I was trying to show in the medical, the pacemakers. It is a very much important for the cardiac patients basically. So few of the patients need this pacemakers. So if you see the first image where one nurse is holding one big machine with the patient, okay. So you can see the size of this. It is in 1950, and then in 1950s when with the progress in the fabrication of thin films and the nanostructures, it has been, if you see this 2016, it is a leadless pacemaker. So you don't have to, earlier the pacemaker was connected to the person and he has to carry a big machine. Now this pacemaker can be inserted inside your body, and you the second person is not even aware that he is having a pacemaker inside the body. So that is the beauty of the thin films, you can say. Okay, and future of course is there, where you have simple chip which can be just inserted inside your body, and this cardiac the patients can easily move around, and they will not even be aware of like what something is there inside their body or not. So that is the one of the advancement which we have done. So I was trying to show these two images. Both the girl is same, the specs are same, but there is a little difference. If you see the specs, one is having certain light reflection and one doesn't have any light. Okay, so thus it is nothing but one, the top one is without anti-reflection coating and the bottom one is with anti-reflection coating. So the cost varies. And why this coating? This coating, how we do, it's a kind of thin film, okay, which is coated on this the glasses of your specs. If somebody is using, they can understand what is the basic advantage of this anti-reflection coating. If you don't have the anti-reflection coating, you see the right side image, you have the lights. If you are facing the lights at the night, these lights will reflect in your eyes, okay, and you are not able to see focus if, let us say, if you are driving or moving on the road. So but if their anti-reflection coating is there, then what is happening exactly? It is, if you see this bottom image where I have put this, when the light is coming in to your the glasses, then 10% of light is reflected back and 90% is transmitted. Okay. And however, nowadays, the kind of advancement of this thickness, or I mean, not I should say the thinness of the layers of the film which are being coated on these glasses. Now the 99%, almost 99.5% is being transmitted. So if more of the light is transmitted and less is reflected because of this anti-reflection coating on your glasses, then what is the advantage? The advantage is that you have improved vision at the night and you have reduced glare from computers, because many people, like small kids also, now they have this anti-glare glasses, not the proper glasses, just to reduce the effect of the light which is falling from your computer screen on your eyes, or so reduce down that effect. And basically it also reduce the strain on your eye, and your eyes are more visible. I mean, if you see this image of the girl which I have been showing in this figure, the clearness of the eyes is also very much important, and it is very much visible if the anti-reflection coating is there. And so this is also one of this few of the examples which I am trying to show through the application of thin films in the smart technology, if you say. Okay. So nowadays, if I am saying, I will not talk about the material which they are using. Actually, various companies are having different materials. Generally, they talk about magnesium fluoride, but it again, the technology is varying at different companies. Okay. So they have different, you see, patent. So on that basis, they are doing this business of the anti-reflection coating glasses. Okay. So what is there in this anti-reflecting coating? It is consisting of multiple microscopic layers of metallic oxides of alternating high, low index reflection. Basically the layers, high, low kind. So what is happening? Okay. When each layer affects different wavelength of light, the more layers are there and more reflections are neutralized. Okay, since reflection are neutralized, so now this is the advantage that we are getting this maximum light inside, and also this is the advancement for the smart technology. If I say the coating, the thickness of or the thinness of this coating is reducing with time to time. Okay, so the entire multi-layer this anti-reflection coating stack, which is stacking of multi-layers, is there. So it is almost about 0.2 to 0.3 micron thick. Okay, so basically this is also one of the example which I try to share with you people. So now question comes, why we need thin films? Okay, so thin film science technology is playing a very important role in high-tech industries. Primarily because their need in integrated circuit industries, and we are very much aware, all of are aware where we are, I mean, every part, our computers, our televisions, our phones, everywhere we have this integrated circuit which is required. Okay, that is why this demand of for the development of smaller and smaller devices, because I don't want, if you have seen the earlier computer, it's a very first computer was occupying the whole room. and then with the time it was reducing the size, and now it's a very smart screen you see in front of you. It is just because we are able to bring those pixels, I mean, from a small pixel to the larger pixel, okay? And also why it is possible, because we are able to miniaturize the size in the form of thin films, or you can say the nano structure. And also the material cost, which is also very much important if we talk about the development of any technology, which is very small if we talk about the bulk material compared to the thin films, because here we are only talking about the surface processes, not the bulk, okay? And the knowledge and the determination of the nature, functions, and the unique properties, I should say, unique, and it can be new also. You never know, you are making some thin films and what unique property you see tomorrow, which will lead to one new technology. Okay, so that is why this new technology will lead to the future applications. Okay, so thin film materials and devices are also available for minimization of toxic materials. Like our earlier speaker was talking about this plastic, how we need to reduce the plastic, and kind of detailed talks he has given. So this thin films also lead to the minimization of toxic material. How? Because the quantity, let us say I am making, if I am giving the example of those anti-reflection coating material, if I am, let us say, if I am making something like magnesium fluoride, a bulk material and a thin film, you know, the material which I am using is, because fluorine is there, it's very harmful, right? So in that way, I'm using very less material. So let us say if I'm disposing this, so these materials, which are in thin film forms, they are minimizing the toxic materials into our globe. Okay. So also the energy consumption. When we are talking about energy consumption, making a big thing needs more energy. Okay. And for smaller, we need lesser. Okay. So basically, so these thin films are also considered to be environment friendly. So this is also one of the advantage if you work on thin films. And yes, I mean, it's not work on, if you work, it is a need of our life, today life actually. Okay. So coming to the development of the thin films, it's a first time it was observed by this Boyle and the Newton, the group, where they have observed the oil on the water, which I have given the example in the first slide, the oilic acid on the water. Okay, and they could see the interference pattern. So that time it was a discovery of kind of thin films. Okay, when people have really understood, okay, this is what we can call it as a thin film. And later on this, I mean, with the advancement of years, a lot of advancement has happened in the thin film world also. If you see this in 1990, when 1965 basically, when thin film technology has been developed, an integral part of the manufacturing in the semiconductor and optical industry has been into the picture. And similarly, the superconductors and all, many examples actually. So some of the examples which I just want to let you know where thin films are being used is the electronic semiconductor devices, and these includes integrated circuit chips, microfabricated mechanism, and your like MEMS, this LEDs, and all these like coatings we have already talked. And you have this photovoltaic solar cell, thin film batteries, which are being used in your, if you see this, your cars, or electric cars basically. So these kind of development, and not only this world, but also the medical. I mean, from the medical point of view, we need the some materials which are very like I have given the examples of this pacemaker. So similarly, some more requirements are there where you can insert the medicine through these small chips or the thin films, and then they at that particular area only. You need not to, because when you are eating some medicine, you are affecting the whole body as a side effect. But if, let us say, I have some problem in my hand, so I will just insert the chip there and put that medicine over there itself. I mean, that is the basically tomorrow's world which we might see because of the these thin films or the nanostructures. So there are a lot of examples which are being used, like in electronics, materials, energies. I mean, just you name, and these thin films and the nanostructures are being utilized. So I was trying to give more examples, but just I could not have much time to really prepare my slides. So it's like one of the examples which was very, I mean, very not very old, I should say, in the 2001, when they have one of the group, they have published in the paper in this science, where they have shown how molecular electronics can be utilized. So molecular electronics is nothing but when a single molecule is, we are expecting to control, I mean, single molecule should control the whole electron transport and explore the molecular functions, okay, for the electronic devices. So here, this kind of, when we are talking about this in molecular electronics, the semiconductors are being used, and they are being assembled on the solid surfaces and in the form of mono layers, okay. So now, the question comes, how we basically make thin films. So thin films are generally created or fabricated by a term called deposition. We are depositing the thin films. There are various methods, okay, and from 4 states, of course, from you can do with the matter, I mean this, solid, liquid, vapor, or plasma. So I have just showed you, like, there are the possibility, like you have CVD, PVD. CVD is a chemical vapor deposition. PVD is a physical vapor deposition, and other many methods which can be used to utilize, or you can make the thin films for your use. Okay. So now this is a schematic for the growth of a thin film. So how we grow thin films? Okay. If you see your right side of the image, you have a source. Source is nothing but a kind of material from where you want to grow the thin film. Okay. So this source you can use, the material is used, and you can take out that material by various methods. You can apply some high voltage, you can apply some kind of laser fluence, or you can heat the material at high temperatures. So in that way, this material comes out from the source and form a plasma, or any kind of, you can say, cloud of the material. And there is an environment, it can be gaseous environment or any kind of vacuum environment. And then it comes to the substrate. Substrate is nothing but where we are depositing. Like a substrate is a different material where I am bringing this material and depositing on my substrate. Okay. So what is happening? Creation of particles from the source, the first step. Then this, from the source, I am transporting the particles, whichever has been come out of the source, to the substrate. And finally, on the substrate, there is a condensation of the particles. Okay. In that way, we are making our thin films. So what are the basic steps? It's a thermal accommodation, binding, because when these materials are coming, how this bonding has been happening with the substrate, and also how the material is bonded along with that, within itself. Okay. Then surface diffusion, because it has to sit on the substrate, and the nucleation. Nucleation is basic a need of growing any kind of nanostructure or the thin films, right? And then you can say island growth, and then coalescence, and then finally you have the continued growth. So it can be amorphous, the thin film can be amorphous, it can be polycrystalline, it can be single crystal. And all these depend on how you grow the film, which method you grow the films, what are the growth parameters you have. So the conditions basically. Okay. So this figure, basically when I'm showing this finger inside one glass, it is nothing but like if you put your finger inside, let us say you take a Coke. So some of the bubbles just get stick to your finger. So it is nothing but it's a kind of nucleation. Okay. So I just want to tell you what exactly nucleation means. And these bubbles are nucleation, and further a kind of layer has been formed by your thin films. So this is basically picture representation, schematic for how this material has been transferred to your substrate. So like atoms or ions will come from your source. Then they come onto your surface. there is a few kinetics which are happening, desorption, then diffusion on your film on your substrate, and then interdiffusion may be possible. And this is basically the steps or your process when you grow a thin film. Like the basic steps I have discussed in my earlier slide. So a simple picture, okay, of a chamber where we can grow a thin film. Okay, let us say this. This is a, you can say, simple evaporator. Evaporator is something what if you this dome shaped thing is your chamber, which is a vacuum chamber. Vacuum is the first requirement for your thin film when you are growing a thin film. Okay, so like holder is there where I have kept my substrate, and at the bottom I have a boat. Boat is nothing but where you have kept your material which can evaporate it by any means. Okay, which I have discussed in earlier slide. So let us say I have two electrodes, I am providing certain current and high current. The current, what current is going to do? It is going to heat the boat. And if you are heating something, the material inside what will happen? It will melt. And once this melting has been happened, so the next process, evaporating. The kind of vapors have been formed, and this evaporative material will go and reach the substrate. And now how it is reaching? The vacuum comes into the picture. Okay, because more you can say, if you are you are in the MAT, and if you want to come to India Gate, more traffic, you can't reach, not even in 1 hour. Okay, less traffic, within, you can say 35 minutes, probably you will reach the India Gate from your MAT University to India Gate. So how? So that is if vacuum is doing that basically action. Vacuum is removing all the extra things and increasing the mean free path. Okay, so that the particles, whatever are being evaporating or taking out of from the source, they can reach the substrate. This is the source, this is substrate. The path is very clean, then they can reach and deposit on our substrate and make our film. Okay, so that is why the vacuum comes into the picture. That is why I said for thin films, the first criteria is to have a good vacuum. Okay, again, the vacuum levels depend. It's probably you people have studied the rough vacuum, medium vacuum, high vacuum, and ultra high vacuum. The better the vacuum, better is your films. Like if you grow the thin films in MB, molecular beam epitaxy, which is the most costliest technique, and most of the you can say your devices which are there in your appliances, they are they are being fabricated using MBE only. Okay, because MBE has the option that it can grow the mono layers and a very clean layers. Okay, so yeah. So as I told, thin films, when you grow, it can be amorphous, it can be polycrystalline, or it can be polycrystalline. Okay, so amorphous, when again, what you want to grow, you want to, it is not important that I always grow very crystalline, epitaxy films. No, some in a surgery application we need amorphous. So growing amorphous films are rather easier than growing crystalline film. Why? Because the conditions, like for amorphous, you require very low temperature. When you heat when you are making, you are also providing some temperature, okay, on the substrate. So very low temperatures are required. The pressures are not that much important. However, when you are growing a single crystal or epitaxial films, these are just opposite to that. You need very good vacuum condition. You need to have a very high temperature. And again, the substrate also play a very important role here. Okay. So now, when we are working on thin films, it's not a simple growth when you are doing. Okay. So how, when you're talking about smart technology has the background at the thin film growth. Okay. So how you're growing? So there is a kinetics, there is a thermodynamics. Okay. So as I discussed earlier, there's a phase transition from gas. If you're taking, you are making a solid, the nucleation, how the nucleation is happening, at what step the nucleation starts, and what is the growth kinetics. Okay, so these things will allow to you to understand what kind of films you are growing and what kind of technology or what kind of applications you can use those films into. Okay, and these growths again correspond to the properties. I mean, properties, when we are talking about material, they are nothing but the conductivity, resistivity, and band gap, magnetic properties, stresses, etc., etc. And it's a large amount of, when you are talking about the any application, a major role is of the structure. Structure, when I'm talking about this amorphous and the crystalline nature of the film, that also plays a role. What kind of applications you are working on, and the kind of defects are there in your films. Okay, so coming to this, basically when we are making the thin films, they are dependent on their properties. Basically, I should say they are dependent on lot of things. Okay, so they are what? They are the growth modes and what kind of structure you are getting, the deposition process, whether you are using some kind of CVD process, whether you are using the PVD process. In PVD also, which method you are using? Either you are using simple evaporation or kind of some pulse laser deposition or MB or sputtering, and thickness. How much thickness film you have grown? Then composition, structural and interfacial stability, film quality, the starting surface. Starting surface mean by your substrate. So these are the things which control the properties of your thin films, which may lead to some kind of application which can be used for any kind of technology. Okay, so the thin films interest, as I told in earlier slide, that the features from the bulk, if I am saying comparing thin films to the bulk, they are very much different than the bulk materials. Okay, so you can talk about density, resistivity, dielectric constant, any refractive index or magnetic properties. So these will definitely vary when you compare to the bulk materials and you are making the thin films. And why it has to be different? Why your thin film property has been different? Why? Because the size effect has come to the picture. When you are talking about size effect, it means what? You are talking about quantum size effects, right? So that is why this material property, because this is bulk, and when you are moving towards the thin films, you are basically doing the atomic growth process. Okay, in bulk, you don't have this atomic growth. And also the, as I discussed, the crystalline orientation, the multi-layer, everything will change. Okay, when you are into the thin films. So as I discussed this properties, I mean how the properties can be varied. So we can discuss few of these modes. When we are talking about growth mode, okay, growth modes, there are basically three modes which we talk when we grow thin films, or you can also discuss, of course, you might have read in nanostructures also. They are I mean the principle behind both of them are same. Actually, you can say thin films can be nanostructures. Okay, so you there's the first mode where you have the layer by layer growth. You are going one layer, then second layer, then third layer. So here, when you have layer by layer growth, that comes the Young's this Young's formula. Okay, Young's formula is nothing but you have gamma of S, substrate free surface energy, gamma of F, film free surface energy, and gamma I, which is substrate or film interface energy. Okay, so what is the relation between these energy, that will decide what kind of growth you will have when you are growing any thin films. Okay, so you, let us say you have this I mean, I will not, like, you can have any kind of growth. This slides, if you wish, I can share with you. You can have layer by layer growth as per the relation of your surface energy is quite more than this your film surface energy and your substrate energy. And you can have island growth, and you can also have the combination of both. You can have some island growth and you can have some layer by layer growth also. Okay, so three type of basic mode. So what kind of growth you are having, that will decide the property of your material. Okay. And this a very beautiful graph is representing nothing but if you see your x-axis, it is a lattice misfit. Lattice misfit is nothing but, as I said, I am growing one material onto another. So if let us say you have two friends, A and B, A and B will bond, will have, I will be very close friends if they have the bonding very good, right? And if they don't have any, I mean, similar characteristics to match, so then they will not have a kind of say good friendship. Okay, so this is what is happening here. Okay, so which we call, like when I'm using the substrate and when I'm growing a thin film on the substrate, you need to have some match between these. And what it is a lattice. Okay, so this lattice match is very much important. More the misfit, more is the chances you go towards the island kind of growth, not the layer by layer growth. Because most of the films or most of the applications are demanding the layer by layer growth, because they are the clean films, okay, for the devices if you're talking about. So if this graph, what I was saying, the x-axis is showing the lattice misfit, and your this right hand side is showing the surface energy ratio, okay, which we have seen in our earlier slide. So if your lattice misfit is very less, let us say very less, and in some points, okay, then there is a possibility that you have layer by layer growth. But more the misfit, you are moving towards the island kind of growth. Okay. So this we have already done, CVD and PVD. Yeah. So coming to this, as I said that growth mode, and second thing is what kind of film you are getting. So the most important, these things I'm discussing because every property of the film, when you are growing, every property will lead to what kind of application you are looking or seeking to. Okay. So the uniformity of the film becomes very much important when you're growing the films. What do you mean by uniformity? Uniformity of thickness or uniformity of the resistivity in the material. Okay. So basically this ratio we talk about, it has to be 1 to 10%. Okay. And also homogeneity in the material. It has to be like when you're growing in nanostructure, although you might have studied, if you have similar kind of nanostructure, then you have better homogeneity, better applications. Okay. And the same composition all over the film. So it means what? The grain size, you're talking about here, grain size. If you have some dopant inside your material, what is the concentration inside that? What kind of stress is there inside the material? So what kind of films people look for? It's a high density material, non-porous, okay? But if you're talking about the porous, definitely they look for the porous materials, okay? So again, I said, as what kind of applications you are looking for. Similar, according to that, you have to grow your films, okay? And it has to be defect free, or you can also put some impurities as per your requirement, and stress, low stress has to be there, or sometimes we need to create some stress, that is called the Taylor stress. And the stability, the film has to be stable and very much uniform, okay? And starting material or starting surface, I should say. Starting surface is nothing but a substrate on which you are growing. It is very much important, okay? And how we can say that what kind of surface I require, okay? Because the film, as I told, that lattice mismatch or lattice match is very much important for bonding, okay? So the lattice match is important, means what kind of film structure you are growing, it again depends on what mode you are using and what kind of adhesion is there on the surface with your material, okay? So you can prepare your surfaces. Basically, you can prepare your substrate. Either you can take, I mean, simple substrate. Let us say I take some silicon substrate, then I clean this silicon substrate with certain methods, and or suppose strontium titanate if I use. So that kind of, so I can prepare my surface by baking. Baking is nothing but heating. This is your substrate. Then etching, there is a possibility. Like for our cases, we require the etching because we need the terraces on our substrate for our growth. So we etch the film chemically, okay? And physically, there is also possibility how we clean the surface, bombarding with some kind of, like especially when you talk about sputtering where you are also a kind of cleaning your substrate with the bombardment of those ions when you are producing the plasma, okay? So in that way, you are cleaning your surface either by baking, etching, bombarding. So it can be in situ or ex situ. Ex situ is before the deposition, you have to do outside the deposition chamber. In situ, when you are doing this cleaning inside the deposition chamber. So again, when I am saying the starting surface, it has to be what kind of chemical nature it has, passive or active surface groups are there, or what kind of surface. I mean, it is smooth or it is a porous, and whether it is thermally and chemically stable or not, or like some surfaces are there which can be really, react with this UV light. So we have to look for these kind of things when we are talking about the starting surfaces, okay? Starting substrates basically. So coming to the films, when we are growing thin films, as I told, we can grow amorphous, we can grow polycrystalline, we can grow nanocrystalline, we can grow epitextual or in the texture form also. So when there is a no lattice match, like lattice constant of this particular material and this particular material are not matching, there are the chances that you get the polycrystalline or the amorphous films, okay, as the figure shows, the bottom figure. But if you have the lattice match and the conditions are very much appropriate, the conditions, what I am talking about here, condition, the temperature, the pressure, the distance between the substrate and your target, okay. So if lattice match is there, then there is a possibility that you grow the epitextual films, but still no guarantee, because again, it is not only the lattice match, it is also, there are certain parameters which I have discussed. I mean, this temperature and the distance, everything. So coming to one of the examples which I tried to show, like if I am showing that every parameters is affecting your growth of the films, which you are talking about, like you want to make device out of that film. Let us say we start with one example, which is a PVD method, PLD, pulse laser deposition. So this right hand side is a image, schematic image for the pulse laser deposition. It is nothing, a small chamber, which is a very this is a sphere shape which I am showing, vacuum chamber, and using pumps I create a vacuum inside this chamber. And in the laser I am using, for example, there are various lasers which can be used for growing thin films. Here I am using KRF laser, krypton fluoride, and with the 248 nanometer wavelength. Okay. When I hit this laser on my target is a material which you want to grow. Let us say ABC. So here are the 6 targets which I can utilize in the PLD. So I incident my laser onto this target, and when it hit the target, it forms a plume. Okay, plume is this triangle kind of thing, this colorful thing. If you see, it is moving towards the substrate. This right side of your chamber is the substrate which is there, and you get the thin film there. Okay, and substrate is on heater. Okay, and it is always at certain temperature, and your target is always moving, because otherwise laser may break your target, because it is a high energy laser. Okay, so yeah, in a brief I can just discuss that what is exactly happening. If you see the left hand side figure of this chamber, when the laser is coming inside with dotted line, you see the laser is going inside the chamber, and what is happening at the time t0, the high energy beam, what it is doing, we are providing with some certain kind of energy density. This it is ablating the target. Okay, I mean 0.1 microsecond, this laser used induced plasma is being created, which can be, plasma can be atomic, atomic or ionic. It forms the plume and goes towards the substrate cell. Okay, and at 2 microsecond, you have highly forward directed plasma which moves towards the target, and at 4 microsecond, your film is onto your substrate. So basically, this is in that kind of short period, you are able to grow the thin film with the PLD using the laser. Okay, as I mentioned, you have the source material, you can use anyway. Either you are providing laser pulse, or you are providing certain kind of heat in evaporation, like, or you can sputter by using some kind of gas plasma. Okay, so now why I'm discussing these thin film growth. Okay, as I told that all the properties, whether it is structure, whether it is your any property, resistivity, magnetic property, any property, they all depend on how you have grown the film. Okay, so, and how you have grown the films means how you have controlled the parameters. So parameters, as I discussed, temperature, pressure. Here, if I'm talking about laser has the energy. So energy, how much is the energy density of the laser? What is the distance between your substrate and your target? So these n number of parameters which control your thin film characteristics. Okay. So this particular figure, if I am trying to show left hand side image, if I see lot of 1, 2, 3, almost 9 images I have shown. This is nothing but when I am changing my pressure. Okay, I just want to show when I change the pressure, how the plume shape is changed. So if you see 5 raised to minus 6 millibar and 1 raised to minus 5 millibars, and then 1 raised to minus 1 millibar pressure inside the chamber, vacuum chamber is there, then I'm creating. So this plume, which I am creating with the laser, how the shapes of the plume has been changed, and the intensity of laser also changes. Okay, so you can see when the plume changes with the pressure, so you are able to control your growth with the pressure. So let us say I want to grow some XYZ film. So I don't want minus 1 millibar because it is too much of plume is there. I want only minus 6 millibar pressure. Okay, so I will adjust my pressure on the base of my growth parameter, that is 5 into minus 10 to minus 6 millibar. Okay, similarly, this is one of the example how you control the growth with the pressure inside the chamber. And second, towards your right side, if you see, it's a variation of the plume size, plume which we call, which is moving from your target to the substrate. Okay, so how you are controlling with the energy density of the laser which I am using. Okay, so if I'm changing my energy density, like first image is 0.59 joule per centimeter square energy density. When you are moving to 0.94 joules per centimeter square, and last, if you are moving towards 1.38 joule per centimeter square. Okay, so you see how the plume shape has been changed with the energy density. So now two parameters basically I am trying to show here, with lot of parameters which control, but two parameters I'm trying to show, pressure, and the second is the energy density. So now it depends on you which energy density you are looking forward for depositing your film, because the energy density will change material to material and kind of property you are looking for. Okay, so the discussion of these things is only because we are talking about smart technology, and smart technology starts with the growth of the film. Okay, how you are able to grow your thin films and how you are controlling the sizes and the nanostructure inside your thin films. Okay, so this is one of the very beautiful example which I try to show. Is a right hand side side is the SEM images. Okay, here as a different, it's a LSMO material, basically it's a manganite material, lanthanum strontium manganite oxide basically. So if you see the change in the plume, you can see that between your LSMO and heater, the change in the plume has been happened because of the controlling of your energy density or pressure, whatever. So A, B, C, D. If you see, this plume changes the how the morphology of your images have been changed. Okay, this is one of the example I'm trying to show that how controlling the parameters for your thin films, you are controlling the morphology of your thin film which you are growing. Okay.
And can I request you to
Okay.
conclude in 5 minutes?
Yeah. So this is the shape of the thin films which I have already discussed. For different material, you will have different material. Size of the plumes. And it is basically one example I want to show when I'm talking about the technology. Let us say I want to give a very brief example. Let us say I have one material which is insulator, SRTiO3, strontium titanate, and I have another material, LaAlO3, lanthanum aluminate. My substrate is SRTS, strontium titanate, and I'm growing thin film of lanthanum aluminate. So both of these materials are insulator, non-magnetic. If you see this table, which I have represented here, band insulators, LO, and STO band insulator, non-magnetic, and with a very big band gap. Okay, but when I deposit my lanthanum aluminate on thin film, what I am able to grow? I am able to see the two-dimensional electron gas at the interface, and this interface leads to the various properties. I mean, since I discussed that this is very much insulator, non-magnetic, but when you grow such kind of films, like for example, you see this particular image. The first image is showing the conductivity in these material. The insulator material has shown the conduction. When you are able to show, grow the two-dimensional gas at the interface. So because of the interface is the conducting, so you are able to see the conductivity in these insulators. So that is the beauty of the thin films, these kind of materials are basically used in this FET structures. Okay. So this is non-magnetic, but you are able to see the magnetoresistance. And the right-hand side, the top one, you can see the superconducting properties at very low, temperature in the millikelvin range. You can see the superconducting material property. So, and these properties can be varied. It can be modulated. The conductivity can be modulated if you apply the gate voltage and you change the gate voltage. Okay. But these all properties depend on the thickness, what kind of thickness you are able to grow. So let us say I give you one example. I am growing 20 unit cell of lanthanum aluminate on STO. So 20 unit cell is equivalent to, I say, 8 nanometer. Okay. So in situ, I am able to see the film growth as the oscillations. Okay. This is the oscillation which I see from the read images. This is basically the schematic of the read. Read is one of the, this is again the electron beam where we use, and we are able to control the oscillation through the beam when we are growing the film by MB or PLD, any kind of mode you use. This oscillation, when you count, then you say that we are growing, each oscillation is representing 1 unit cell. Okay. So if I am growing 20 unit cell film, then it means 20 oscillation I am seeing. So while I am growing my film, I am able to see the thickness of the film. Let us say left hand side of this green image, if you see, this is the STO, clean STO, SRTiO3, and right hand side when I am growing the films. Okay. So when I am getting this clean streaks peaks, it means I am growing the two-dimensional layer by layer growth. I'm trying to show this example because I have talked about layer by layer growth, but how you observe this. So when you grow by, like let us say these films are grown by PLD. So if you are getting the streaks, then you are, in situ, while you are growing the films, you can see, okay, I'm growing layer by layer growth. Okay, these are the few results which I will not discuss, but yes, this HR10, the cross-sectional 10 basically, if you see SRTiO3, LSO, the layers, very clean. There is no mixing of these, intermixing of these materials. Okay. So, okay. So basically what I'm trying to say, the control of your deposition parameter can lead to the growth of the thin films and later to some kind of devices which you are looking for. Okay, this is one of the picture which I have taken from the science journal, which was published in 2009. Later on, recently they have also shown, but I didn't take that picture. It is a basically schematic of the sketch fit structure which they have grown. You see this, there is a drain D, source and gate. So this is FET structure they have created with the kind of oxide heterostructure, the interfaces which I was showing you. Okay, so these kind of technological development has been happened that you can move to like nanostructures or certain kind of ultra low thickness layers or thin films which can be utilized for the devices for your applications. Okay, so in conclusion, I would say thin films is a major need. Why? Because we require higher functionality, increased memory density, and higher speed, and which is basically the driving need for this smaller dimensions. That is why we started with the smaller dimension. With this, I conclude and thank you, all of you. I hope you understood something. I don't know. I mean, I could really pass on some message to you or not. Thank you. If any questions, please.
Thank you so much, Dr. Anjana, for such an explanatory lecture. And I very well agree that if we are able to control the deposition parameters, then we can control many of the things of the thin film, and which is a societal need for many applications. So we have a couple of questions for you.
Yeah.
The first question is by Professor Arpita Bhattacharya. She's asking, what is the life and stability of anti-reflection coating on glass?
Yes, a very good question actually. So if you life, I should say, it again depends on how you use it, right? If you are putting the scratches, definitely it will go. If you give it to the child, it will go. But what this opticians tell, I mean, until as you keep on cleaning these surfaces, they will sustain for many years. Again, it depends on how the user is using that glasses. Okay. But yes, they are very much stable. The coating is very much stable.
Okay, the second question by Professor Arpita only, that by which method this coating is applied on the substrate?
Most of the coatings which are being there, let us say, if you are talking about anti-reflection coating, when the moment you talk about coating, the industries are using only sputtering. Okay, because when I'm talking about PLD has certain big thing, like you cannot grow very big sizes, and then ND is very costly. I mean, everybody cannot install the ND, but yes, if you're talking about the applications like this FET and these kind of devices, they have to go for the this MB kind of facility. Otherwise, simple coatings can be done with the sputtering.
There are many requests for sharing the presentations.
I will definitely share. I will share. I will share with you and Dr. Sina, so you can share with the people.
Then there is next question which says, this is by Nehal Ahmed. He's asking how to measure the hardness of the thin film.
Okay. I don't know whether you have attended the lecture by Dr. Dakate. So yeah, so there is a possibility, but for thin films, this especially thin films, what we grow, very much difficult because the hardness system, there is a instrument which can measure the hardness, but for these thin films, it is very much difficult. But basically, they are creating a kind of dimple on those material and see how much stress they are able to generate. So that kind of thing is same. But again, the sizes matter, because every instrument has the specification of what kind of material you are using, what size you are using, and also, I mean, if you say you put in 10 films, then definitely it is destroyed. So, I mean, lot of parameters, I mean, you need to see.
There are a couple of micro hardness tests which you can do for.
Yes. Those dimple tests are very much common for the people who are, yes.
The second question by the same person is that, is there any relation between film and substrate? For example, film and substrate material. For example, silicon or glass or alumina. I think we already discussed this.
We have discussed this because the substrate material is very much important. Its roughness, its surface, and of course, the kind of, I said, the bonding it made. And the most important is, of course, the lattice constant. Whether there is a lattice mismatch is there. Let us say I have the substrate of SRTiU3, which is having the lattice constant of 3.9 angstrom. And I am using some material which is having 4.5 angstrom. So it is very difficult to make it 4.5 into 3.9. There kind of lot of stress I'm generating onto that when I'm growing these kind of materials. Okay, so the lesser the mismatch, better your film.
Absolutely. Okay, the last question is how clean the surface should be before the growth of the thin film.
This also I have discussed. The cleanliness of your surface is very much important. Reason behind, because let us say for example, my surface is not clean. Something is there. So what it will lead to, I am growing some, let us say 4 nanometer film and some particles are there. So it is not 4 nanometer. The roughness itself will enhance to some kind of 10 nanometer. So I will not even able to say that I am growing 4 nanometer film, because the roughness will be enhancing to 10 nanometer because of that particles which are already onto the substrate. So the cleanliness is very much important, and few methods I have discussed by which you can do the cleanliness, like baking or the bombardment of some ions or any other method, which etching. So these few methods which I have discussed to clean the surfaces.
So to add to whatever you said, first of all, it will depend upon the application. Secondly, it should be as clean as possible.
Yes, cleanliness is very much important everywhere. Our country, our house, our substrate, everything should be clean only.
Absolutely. Thank you so much, Dr.
Very rightly, Anjana, wonderful talk. And you have clearly mentioned that why the thin film is important. See, unless and otherwise you have the thin film or the a small quantity, you cannot get the quantum tunneling effect. And if you are not getting the quantum tunneling or the quantum effect, you are not going to deal with the nanotechnology. And that's why the thin film is very, very important. We are talking about the sensitive, or we are talking about the smart nanotechnology, especially for the societal applications.
Yes,
And
yes.
basically, when you are depositing the film in any substrate, the property depend upon the interface. And if your surface is not clean, interface will be defected, and therefore your property will be defected. So cleaning, ultra cleaning is more important part when we are really looking for the high-end technological applications.
Yes,
So wonderful talk, Anjana. Thank you very much for your time.
Thank you, Dr. Sinha.
I know I have killed your lunch time because
No. I bring my lunch anytime I can have. By the way, one question when Abdullah has asked, I think, how to measure the thickness of this ultra thin. So I want to answer that question. Actually, for ultra thin films, either you need to have in situ provision. So in situ is what I was showing. I could not show much because of this time shortage. The reed which I was showing. We have the chamber inside which we have reed system attached to this chamber. So you count the oscillation and you are able to see how much thickness. Let us say we are growing 4 nanometer thin films. So 4 nanometer means 10 unit cell. If I am able to grow 10 unit cell, then I am able to see that I am growing the thin film of 4 nanometer. And apart from the in situ, you are able to also see through other profilometers and these things. You can always, an AFM. If you are able to create a step in your film, you can always measure with the AFM. Okay, because the resolution of AFM is, I think, better than 4 nanometer, if I'm not wrong. So you can go to AFM as well. So yes.
So best technique, if you have the ultra thin film or your thin film, you can go for the ellipsometry, from where you can get the thickness of your material directly.
Yeah, but the ellipsometry again depends on what material you are measuring, because their band gap matters.
So there is basically you need to put the dielectric constant of your materials, and accordingly you can deal it. And the one drawback with ellipsometry that you require the reflecting surface.
Yes.
So you need to deposit the film on the silicon or the some ultra reflecting surface. Otherwise, this is one of the strongest tools, because you simply work on the Newton rings, whatever you have read in our class 12.
Yes.
And that gives the really, depending upon the fringe edge, we can able to measure what is the thickness of your film. So that is, nowadays there are many cross-sectional tools through which you can measure the thickness. You can measure using the cross-sectional TM, you can use using cross-sectional ACM, but all depend upon what applications and how much fund you have.
And where is the facility, whether you can avail or not. Like HR time I have shown, like through that we have calculated the thickness. But again, we had only one figure only. After that, nobody entertained us for the measurement of our films. So anyhow, we have the read, so that is the boon for us.
That's why the Lakshmi is required everywhere. Thank you, Archana.
Thank you, thank you.
Thank
So
you
may
so
I
much.
I am permitted to leave now?
Yeah, yes, Anjana, thank you.
Yeah,
Absolutely.
thank you, thank you, thank you.
Over to you, Monica. I think again she is having some connectivity issues. So first of all, I would like to thank all the eminent speakers of this session. We come to the end of this pre-lunch session. And I would like to thank all the eminent speakers, particularly Professor P.K. Bhatnagar, Dr. Suman Lata, Dr. Anjana Dogra, and also our young speakers, Dr. Shaheen and Ms. Mausam Chaudhary. Thank you so much for joining in, and all the participants for being there and for learning through this value-added workshop. So a small reminder that the session assessment will be conducted at the end of today's workshop, and the link for the same would be given in the chat box at that time only. So you have to attempt the questions, and we would come back after the lunch right at 2:30 p.m. Thank you so much. We break for lunch right away.
Good afternoon, everyone, and welcome back to the day 3 post-lunch session of the value-added workshop in nanotechnology for societal applications. And I welcome everyone in this session. In this session, we have 5 eminent speakers. I welcome all the speakers as well as our guest in this session. Now, without wasting the further time, I would like to request our dynamic student, Abhyavartan Selvam, to start the session.
Thank you, ma'am. Welcome back, everyone, to the second half of day 3 of the Smart Nanotechnology for Societal Applications. I'm Abhyavartan Selvam, and I'll be coordinating this session with faculty coordinator, Dr. Monica Joshi, ma'am. So our first talk for this session will be given by Dr. Prashant Singh. Dr. Prashant Singh is the professor at the Department of Chemistry, ARSD College, Delhi University. He obtained his MSc in Chemistry from Indian Institute of Technology, Delhi, and his PhD in Chemistry from Delhi University. His research interests include computational tools and molecular dynamic simulations. He has published several research and review articles in reputed international journals. He has more than 2,000 citations. Today, he will be delivering a talk on use of computational tools in finding promising inhibitors against main protease of SARS-CoV-2. On this note, please join me in welcoming Dr. Prashant Singh to the platform. So you have 30 minutes followed by question and answer sessions. I request you to please summarize your talk in the timeline.
Thank you, dear, for introducing me with the participant and the faculty here. So let me share the screen and I'll try to wind up within 30 minutes. I hope the screen is visible to all of you. Is it?
Yes, sir. Yes,
Yeah.
it's perfectly fine.
Yes, so guys, my topic of presentation is use of computational tools in finding promising inhibitor against the main protease of SARS coronavirus 2. Yeah, as a layman, because most of us are using electronic gadgets like mobile phone, laptop, and we face difficulty in using time after certain, after buying it. That problem may be due to the virus. The virus took the control of electronic gadget. So we need an antivirus to take care of their electronic gadget. They simply scan the files of the electronic gadget and remove the infected files, or sometimes they have to quarantine them. Based on this, as a science student, we can understand a biological virus. It is an infectious particle. It has a genetical material which has a protein code. You can say that bacteria, virus, and others may cause infectious disease. They may spread. We have seen in the last 2 years, since December 2020, or in India, I'll say that from December 2019 or about 2 years back, we have faced lots of things. Yes. So the infectious disease comes under zoonotic diseases, and these are some of the pathogens which has created problems in humans. So let's come to the COVID-19. This COVID-19 name is given by the WHO. It's coronavirus disease, and we have seen it's a threat to human life. We have seen the third wave, and in 2021, we have seen many people have lost their life. Even in 2020, we have seen how the infection spreads. Sometimes people have it spreads only sneezing, or when human come in contact of other humans. But let me say, it has several other approaches, several other ways by which this virus can infect the human. So this is the general structure of the new coronavirus. Here you can see spike proteins, and my work is emphasized on how to target them, because these spikes proteins are very important in infection, in creating infection to human beings. So how it can be done, I'll focus on that. So this information is already available on the internet. I'm not going in the detail because I have to finish it in 30 minutes. And these are the human coronavirus. Usually people have a perception that this viral infection, this coronavirus infection is originated into 2 or 3 years back. But let me tell you, this coronavirus is discovered long back, about 60 years back. So what we can do, we have to target, my emphasis is to target the main protease of the new coronavirus. How I can do it? I can, my expertise is using computation tools. So using computational tools, we can find the potential or promising molecules to inhibit the activity of the main protease of the coronavirus, and so the viral activity can be inhibited. So what I used to do, I'm using some of the computation tools, and nowadays graduate and postgraduate students have lots of interest in using computation tools, although most of them are not freely available, but we can use them in collaboration, because here what I use, I need a protein, which I'm saying that main protease of the new coronavirus, the crystal structure of protein is available on RCSB, on that website. We need a target, and how it can be targeted. It can be targeted by using small molecules. I am working on small molecules in my PhD. I have synthesized several molecules. So those molecule and other molecule can be used to target the active site of main protease of novel coronavirus. How it can be done? It can be done by the molecular docking, molecular dynamic simulations. In the beginning, I feel that molecular docking is sufficient, but the molecular docking, it is used to target the protein, but it happens for a very, very small span of time. Therefore, we need an approach by which we can say this method is better. So molecular dynamics simulation is a better approach to understand the interaction of small molecule with the receptor site. So we'll discuss them here. This is a small clip for the interaction of a drug molecule with the receptor site. So the student can have an idea how a small molecule interacts with the protein. It is of very few seconds. So you can see that a molecule is coming towards the protein and binds with the amino acid of that. So here we can see that molecule is perfectly bonded, or shows the interaction with the receptor site. So now coming to the work that I have done, and it was published in the 2020. Here I have taken a library of the noscapin and its derivatives, because this is the work which I did in my PhD, and this molecule is discovered from our lab. means my mentor's lab. Here I have taken the noscapine and its number of derivative, and they were screened through molecular docking. And based on the docking, we came to know that this molecule is better than the others. And we have done the molecular dynamics simulations using Amber 18. And the interaction of small molecules with the protein can be understand by the different trajectories, like root mean square deviation, root mean square fluctuation, and other trajectories. After that, it is very important to know the thermodynamic parameters, because here we are talking about the interaction of a molecule with the receptor site. So definitely there is formation of complex. So we need to understand what will be the change in enthalpy, change in entropy, and finally the most important is change in free energy. So we have explored, or we have determined the thermodynamic parameters to understand the effective binding of small molecule with the receptor. Here we can see that we have the receptor, that is main protease of the coronavirus, which is orange in color, and the green is the green one for RMSD is for the complex. And here we can see that the RMSD value of the complex is lesser than the RMSD value of the protein alone. So it can be seen, it can be understand that the molecule effectively binds with the receptor. The similar pattern we can see in the RMSF, which is root mean square fluctuation. Here, the complex of the main protease of new coronavirus and the molecule has less fluctuation than the other one. After that, as I've told you, we need to perform the MMGBSA calculations to know the change in free energy, and we came to know that the change in free energy is minus 9.2 kilocalorie per mole, which indicates that if binding is effective, and this molecule could be considered as an effective inhibitor. Further, the MD simulation was carried out at 300 Kelvin, but we also need to understand that the activity of this protease at different temperature. So we have performed the MD simulation at different temperature, as on the RMSD and RMSF. You can see that we have performed it at 300, 325, 350, 375, and 400. Earlier one, the earlier plot was at 300. Now it is 322, 325 to 400. You can see that the RMSD value at 400 Kelvin it's going above 4. It is very important to know that if the RMSD value go above 3, that data is not acceptable. It means protein is disrupted. Protease is disrupted, so the complex is not formed. So we can see that this blue one at 325, here we can see the RMSD value is least. So the binding of 23B with the main protease of new coronavirus is the most effective one. Further, we have also studied it with MMGBSA calculation, and here you can see the change in energy, which is in kilocalorie per mole at 325, and at 350 it comes out to be -7, and it is a good value. But we have seen that at 300 Kelvin it was -9.2. So we can say that at 300 Kelvin the binding is more effective. So performing the MD simulation at higher temperature doesn't provide a good information, but we can say that we have studied, and at higher temperature the binding is not so effective as at 300 Kelvin. But here we have done the MD simulation only for a very small time, that is 10 ns, which is not a good one, while for at 300 Kelvin it was for 100 nanoseconds. For MD simulation, time plays an important role. So in some of the MD simulation, we also go in the microseconds, 2 microseconds. Now, the next one, we have taken the zinc database and we have screened the molecules, and they were dog and performed the and we have performed the MD simulations against the main protease of new coronavirus. Here you can see two of the screen structures. At the end, they are 70 and 35. When they were screened, when they were performed MD simulation with the main protease of new coronavirus or SARS coronavirus 2, we can see they shows effective binding, which can be understand by the molecular dynamics simulations. Here you can see that we have the RMSD, RMSF plot for the protein and for the complex with those two molecules. In the RMSD and RMSF value, it is very difficult to compare or difficult to differentiate that which has the effective binding. But by calculating the thermodynamic parameter, it gives a clear distinction that the last two digits 35 binds effectively than the 1870, because the binding energy is minus 4.5 kilocalorie. So by this we can screen, by this we can have some information, so we can explore these molecules for the biological activity. Here we have again performed the molecular dynamic simulation at different temperature. So as I have told you, the performing MD simulation at different temperature is very important to us to know what will happen to virus or main protease of new coronavirus at different temperature. Because everyone was everyone has a fear about 2 years back in the March 2020 that what will happen. We have to wash our vegetables, we have to sanitize our clothes, place it somewhere. So this is very important to know at that time what will be the impact of temperature on the activity of main protease of new coronavirus. And we came to know that still it binds effectively at 300 Kelvin. It is not as at higher temperature. Now, a year back, we have seen that the government of India announced that 2DG molecule is an effective molecule to cure the patient suffering from this new coronavirus. This molecule 2DG is an important molecule. It is because of biological potency in different areas. And I must say, as an anti-cancerous molecule, because one of my collaborator in South Korea is working on it. So I thought, why not to explore it through computation tools? So I took 2-deoxyglucose and 2-deoxyacyclic glucose. Let's compare it with this. What happened if it becomes acyclic? And then I have taken 2-deoxyribose. So first of all, the molecular docking was performed. Here you can see the poses. I have taken all the three molecules together based on the through the molecular docking, and here we can see 2-deoxy glucose effects better than 2DG. But as I have told you in the beginning, molecular docking is not a reliable source. Means we have to go for molecular dynamic simulation. Only then we can claim that this molecule is really it's really a good molecule or not. Therefore, this is based on the molecular docking. So we have performed the molecular dynamic simulation of those three molecules with the main protease of new coronavirus. And based on this, again, this study corroborate with the experimental work or the claim by the government that 2DG a potential molecule to cure the people from this infection. We have also performed at different temperature. Here we have performed the MD simulations at different temperature for 100 nanoseconds. While for the earlier work, we had performed it for only 10 ns at different temperature. Here we have taken temperature 310 and 315, means 295, 310, 325. We have not studied at very high temperature, because we have to think what is our physiological temperature. In our body, it is 310, 37 degrees Celsius. So this temperature is very important, because the reviewer has asked why you are performing at other temperature. Now the things are different, so perform it at this temperature. So we performed it, and try to understand that the effective inhibition is done at 295 Kelvin. So this is the conclusion for the molecular docking and MD simulation for this work. Further, this is an interesting molecule, litidapsine. Although this molecule is a very big molecule and created lots of hurdles for us to perform molecular docking as well as for molecular dynamic simulations. Because it's not easy to perform molecular docking if the molecular weight is above 500 Kelvin. 500, sorry. So here you can see the molecular docking through Discovery Studio. These are the pose 2D and 3D and 2D dimensional pose. How litidapsine interacts with the amino acid of the main protease of new coronavirus. So this is the root mean square deviation plot for the complex at 300 Kelvin and at 325 Kelvin. So here we can see the deviation. At 325 Kelvin, what we have observed that the RMSD value increases. And I have mentioned that the RMSD should be less than 3 angstrom or 0.3 nanometer. So it is in the nanometer. So I must say, and it was for 100 ns. So we can say that at 300 Kelvin, it shows effective binding with the receptor. So similar information is come from the root mean square fluctuation for the complex form between the litidapsine and the main protease of new coronavirus at different temperature. So the conclusion comes that it doesn't bind effectively at higher temperature. So the binding will be better if it happens at 300 Kelvin rather than at 325. So as in the conclusion, we can see that it effectively binds at 300 Kelvin rather than 325. So there are other works too, and this is gamma original. We have seen that we usually use it for cooking. This oil is very important. We are taking to increase our immunity. It is available in many daily we people are using in our everyday life. Not all, many of us. And what I have done that I have taken this molecule and performed the MD simulation against the main protease of new coronavirus. These 4 pics are not based on the or are not taken from the molecular docking. These are taken based on the molecular dynamic simulation. And here we can see that the position of the molecule, you can see it shows different interaction. The active site differs. The active site is not same. So we can say that as the temperature changes, this site also changes. There is some change in the binding or this binding of the molecule at a particular site. The change is not much, but it is a minor change can bring different observation. So we have performed root mean square deviation at different temperature 290 to 320 Kelvin. And here we can see at higher temperature fluctuations are more, but we have seen an interesting information at 320 Kelvin. The fluctuation are not much. At 310, the fluctuations are maximum, but we are unable to explain till now that what happens at 320 Kelvin, why the deviation is not much because what we have seen, the deviation increases as we increase the temperature from 290 to 300, then 310. But at 320, a new observation comes that the deviation decreases. And the similar, but when we are studying it through root mean square fluctuation, it is not as in the case of RMST. Here at 320 Kelvin, the fluctuations are maximum. Now this is the hydrogen bond trajectory, although it was also given for the other. Here we can see the number of hydrogen bond plays an important role, because as a chemistry student or as a biology student, we understand the importance of hydrogen bonding, because sometimes we have seen that the hydrogen bonding dominates over steric hindrance, and the stability also changes, like in the case of orthonitrophenol. Similarly here, we can see at 290 Kelvin, the number of hydrogen bonds are maximum in comparison of in comparison of performing MD simulation at other temperatures. So we can say that at 290 Kelvin, the number of hydrogen bonds are more. So we can say the binding is effective and the inhibition is maximum. So at this, I'm stopping my presentation, because I think you have given 30 minutes. I don't know is 30 minutes or not. So one more thing. So at the end, I would like to acknowledge the principal of my college, Professor Kyantosh Jha, Professor B. Jairam, where I have worked. My student also worked there, along with I forget to mention one of the facility WebGrow, where I have performed MD simulation along with the SCF Bio. And these are my collaborators and my students. Thank you, everyone. And you are welcome to raise queries, and definitely I will learn.
Thank you,
Yes,
sir,
please.
for your insightful lecture. Now we can move on to the questions.
Yeah, please.
Abhyavartan, you
First
are
of all,
on, yes.
if there are any panelists who would like to ask any questions, because I don't see any questions coming to the comment section.
So may I stop sharing the screen or be here as well?
Yes, sir, you can, sir. Thank you so much, Prashant sir, for excellent talk. It's means it is the other aspect of coronavirus too. Most of the time we have gone through with the experimental studies, but it's computation studies. And sir, I have one small doubt.
Please.
Sir, how much these computation studies are in line with the experimental ones? Means like so many groups are working, I think, on that experimental work also on the inhabitation of SARS-CoV-2. So how much these results are in line with?
Yeah, Dr. Doshi, I do agree with this. Is the first question comes in our mind.
Right.
That what is the reliability and how this study will collaborate with the experimental work. So I would like to say, as I've mentioned, molecular docking, it is not a reliable approach. So for the beginner or in the learning phase, we can say, yeah, I have performed molecular docking, but we should perform the molecular dynamic simulations.
Right,
And
sir.
for the molecular dynamic simulation, 100 ns, 200 ns is not sufficient. We should go for microseconds.
Okay.
At least, because all we know that for performing MD simulation for microseconds takes lots and lots of, or you can say huge time. Therefore, we always avoid in performing MDs for in microseconds. So we always go up to 100 or 200 nanosecond because of the lack of facilities. But let me say, if we perform it for a longer time, then definitely you will find some relation with the
In the that
theoretical
like,
and the experimental work.
one more thing, sir, you have shown some temperature dependent studies.
Yes, ma'am.
So it means that higher the temperature, the growth is what I understand. I am not a biologist, but that is the growth rate is lesser or what?
No, ma'am. Actually,
For the spreading, I am asking.
let me tell you, because initially I was working on the non-structural protease of chikungunya virus and dengue
Okay.
virus. So when it came in 2019,
Right.
because I think in the beginning I have mentioned 2020, but when it was first reported in China, December 2019, so my student has approached me, sir, इस पे क्यों नहीं काम करते? So in India at that time, there was not much noise or sound on chikungunya, on this new coronavirus. But we started working on it. Then he realized, my student has, Dr. Durgesh Kumar, he's a faculty in DU. He said, sir, temperature plays an important role. So I do agree with this, because we have seen the virus infect us at a particular temperature when they becomes active.
Right.
So we need to understand that what will be the impact of temperature on this work. So this is replica exchange MD, molecular REMD भी बोलते हैं, and sometimes we used to say molecular temperature dependent molecular dynamic simulation. So I started working at different temperature. Earlier I thought I should go 325, 350, 375 and 400. Although at 400 Kelvin, it is not relevant to us, because our physiological temperature is 310. And later I would start working on that temperature, because the reviewer had started asking me why you are going to that temperature, because I was in impression that sometimes we have to iron our clothes, so it will be virus free.
At that time, that was a rumor also that the higher temperature it itself had
the activity decreases.
Decreases.
The virus will not be active. So later on, I realized that I should not go up to that temperature. So I should stick to 325 only, maximum. And especially I should focus on 310. And what I have seen, there is no regular pattern. It might be that the time for MD simulation is very small. If I'll take the time up to 500 ns or 1 microsecond, then definitely we can reach to a conclusion. So for different molecules, I have seen different observations, different information. Like in one of the work, I had mentioned that initially the RMSD value increases, but at 320 Kelvin, I have seen a decrease in the deviation. So there is a possibility that on changing, there is no regular pattern, but generally it is observed when the temperature increases, the deviation increases huge. And we consider up to 3 angstrom, not beyond it.
Not beyond that. Okay, sir. Thank you so much, Dr. Prashant, once again for the excellent talk. Abhyavartan, you continue.
Thank you, ma'am. Moving on, we have Dr. Amarpal Singh. Dr. Amarpal Singh is the Assistant Director of Forensic Science Laboratory, Delhi. He obtained his BSc from Delhi University, a certificate course in Forensic Science from Anthropology Department, Delhi University, Master of Science Forensic Science from Dr. H.S. Gaur University, Sagar, MP, LLB from Delhi University, and PhD from AIFS and AIIT of Amity University, UP. His accomplishments include second position at university level and graduation level, first position at university in post-graduation, received gold medal in MSc Forensic Science, passed UGC NET JRF twice, and examined and reported approximately 7,000 cases and 15,000 exhibits. He has visited several crime scenes and attended courts as an expert, and won the first prize of Dr. P.D. Sethi Memorial National Award 2017 for his best paper using HPTLC MS. Today, he will be enlightening us with his lecture on nanoforensics and its application in criminal justice detection. On this note, please join me in welcoming Dr. Amarpal Singh to the platform. We have 40 minutes followed by question and answer session. I request you to please summarize your talk in the timeline.
Thank you, Abhayji. Thank you, ma'am.
Good afternoon, Amarpal sir.
Thank you, ma'am. So nice of you for calling me here to deliver a talk.
It's our pleasure to learn forensics from you.
No, ma'am.
You are
I
an
have learned
expert.
a
आप
lot of
expert
things
हैं
from
इसके.
all of you. Yeah.
Expert, sir, on forensic.
From Dr. Monica, Dr. Nidhi Chauhan, my guide, I have learned a lot from nanotechnology department, and I will always remember the nanotech departments which has helped me a lot to fulfill
Sir,
my
pleasure, sir.
dream project of PhD, and I'm highly grateful to AINT. Thanks a lot. So my topic today is about nanoforensic, and it is a new field for
Sir,
society.
sorry to disturb you, Amarpal sir. You can share your slides.
My PPT is getting uploaded or not, ma'am?
सर बॉटम में एक शेयर स्क्रीन का आइकन होगा ग्रीन कलर प्लीज शेयर इट फ्रॉम देयर
Green से
ग्रीन कलर आइकन 1 2 3 4 फिफ्थ वाला फिफ्थ आइकन ग्रीन कलर अप एरो हाँ सर नाउ इट्स विजिबल
Now it's visible, ma'am.
हाँ सर इट्स परफेक्टली फाइन it's in the significance of forensics history of nanoforensics हाँ सर visible है
Okay, ma'am. Then you can
right.
start it now.
Yeah, please, sir.
So the today topic is nanoforensic and its application for the society. The main contents of this PPT is nanotechnology and nanoforensic, nanosensors and nanomaterial, nanoanalysis techniques used in forensic investigation, application of forensic nanotechnology. What is forensic science? Basically, forensic science is made of two words. One is the forensic and another is the science. So forensic means law, legal authorities, courts, and forensic also means forum where one can decide the cases, dispute. And the science is the thing that can be proved by the some technology, the facts which can be proved. That is the science. And where we use the technology, where we use the instruments to find out the facts. The forensic scientists draw knowledge from chemistry, biology, and physics to recognize, identify, and evaluate physical evidences during an investigation, crime investigation. They assist the authorities by using a variety of techniques to analyze evidence in the laboratory. Basically, conventional techniques we are using the TLC, thin layer chromatography technique, GC, gas chromatography, GC mass chromatography, gas chromatography attached with mass spectrophotometry, then FTIR and other chromatography techniques to solve the criminal cases. So basically, what is nanotechnology? Whatever I have learned from this here, from that is what is nanotechnology? It is the combination of various fields of physical, chemical, and biological science that study the phenomena on the nanometer scale. Nano is basically derived from the ancient Greek word that is nanos and means dwarf. Nanotechnology is the managing of matter at a molecular or atomic level. So basically, where is the nanometer scale? It is 1 multiplied by 10 power minus 9. So it is the nanometer where we works. And you see the DNA, the size of DNA is 1 to 2 nanometers. In the various fields where the nanotechnology, this nanotechnology is being utilized. So now you see it is basically it is now used in the water filters, microchips, and this air gel, nano solar panels, nano retina, nano DNA, artificial intelligence, some supercomputers, nanobrains, and in other various techniques like and other conventional techniques are also hyphenated or also improved using these nanotechniques or nanomaterial, such as Raman techniques, the search techniques, and this LC mass. LC mass is using these nano columns to detect the DNA and other proteins body. So nanotechnology advantage are used in various fields. They promote renewable energies. It enables new ways to obtain and store energy. It extends the limits of electronics like silicon microchip. Unlike silicon microchip, nanochips will make it possible to build very precise circuits at atomic level. It allows a more effective medicines, and with it also have some this technique some has some disadvantage too, and that this safety and security may be compromised. And because now the drones are coming, and they might be using this nano techniques in the drones. So what is nanoforensic? The forensic means legal, law. And nano means the dwarfism or the material has been reduced and to the nanoscales. So whatever material will come to us, if it is of that nanoscale, then we have to detect the nanomaterial. And these nanomaterials, now the companies and the others are manufacturing and are using in different products. So these products having nanomaterials may be utilized in committing crimes, or maybe found at the scene of crime. So then there may be a question, so whether this exhibits or this physical evidence contains nanomaterials or not. So in that conditions, we have to detect the nanomaterials using sophisticated techniques like electron microscopes and TEM, SEM, and others, other electrochemical techniques and AFM techniques. And there are various techniques where we can detect the nanomaterial as well. And we can prove that nanomaterial is used in poisoning or in the others way. So that is the nanoforensic now. Once the questions become, when it is disputed that whether it contains this nanomaterial or not, and it is if the case is registered, then the forensic science laboratory will provide the answer whether it contains nanomaterials or not. On the other hand, if these nanotechniques using these nanomaterials may be utilized to detect the presence of any compounds with high sensitivity, and in both way, the nanomaterials, we have to find out the nanomaterials, and we have to utilize the nanotechniques for the detections of the crime history. So it is a new area of forensic science, which is highly advanced, associated with the development of nanosensors for crime investigators and inspections of terrorist activity by determining the presence of explosive gases, explosive material, biological agents, and residues. So nano nose can be used in the explosive material in finding out the explosive hidden materials. So nano analysis is commonly used in the nanotechnology for detections of the crime. So nanoforensics may use nanoparticles, it also may be a nanosensors, nanotechnology, nanolithography. So it may be used in fingerprint development, DNA sequencing, drug identification, document examination, trace evidence analysis. The history of nanoforensic. The concept of nanotechnology is first mentioned by Dr. Richard Feynman in 1959. Nano comes from Greek words, means dwarf. Transformations of ideas in nanotechnology into reality started since 1980. Incorporation of nanotechnology in forensic genetics researches in 2006 by National Nanotechnology Initiative in US. The significance of forensic nanotechnology. Nanotechnologies in forensic science significantly transform the process of investigation by making them faster, more accurate, more effective, more sensitive, and easy to apply. Nano platform alone or in junctions with other technology has significant application in security, drug screening, explosive detections, and DNA analysis, which enables forensic investigators to perform complex analysis or to discover the smallest traces of evidence at the crime scenes. As I have told that these liquid chromatography mass spectrometry are using nanocolumns for analysis of smaller particle of DNA molecules in nanometers, having nanometers length. And whereas in drug screening, these SARS techniques, SARS techniques, SARS and Raman combinations techniques are being used for the detection of explosive. And whereas the other electrochemical techniques the performance of electrochemical techniques can also be enhanced using nanomaterials. So the nano platform or nanotechniques are working along with the conventional techniques, or we can say these nanotechniques are increasing or enhancing the power of our existing conventional techniques. In some cases, the trace evidences that are required and pose a problem of reliability and integrity, thereby giving a big question mark about the importance of trace evidences. So we should have the ultra high technology in the form of nanotechnology, which can detect the presence of, which can detect the evidence up to the nano levels. Sometimes evidences are tampered and destroyed behind the recognizable level. In such cases, the application of nanotechnology are extremely valuable. So the various instruments which we have to use for detecting the nanomaterials or for detections techniques. One is the transmission electron microscope and the scanning electron microscope, SAM, atomic force microscopy, AFM, and dynamic light scattering, DLS, Raman microscope, spectroscopy. Now, one of the most drawback with these instruments that these instruments are not so easily available within the instruments, as they are highly costly, and the actually researcher and the scientists has to move from one place to another. So there is a strong need for the institutions to procure all these instruments and for better analysis, to provide the better analysis. Then only it will be possible that we can utilize nanotechnology in forensic field or other fields. So nanoanalysis technique used in forensic investigation. These techniques assist forensic scientists in two ways: by making it possible to analyze nanoscale samples, and by making use of the specific effects of nanomaterial to identify and collect evidence. So it is also used and also helps in the identification and collection of the physical evidences at the scene of crime, because the nanomaterials may provide the adsorption surface for just like the cloths having nanomaterial which may adsorb the blood samples over it. High quantity of bloods can be adsorbed. So we can think it, or we can make a such material which can absorb a large quantity of the blood samples for further analysis.
Sir, your voice is not coming.
Sorry for interruption.
Now it's
Hello.
coming. Now it's coming.
So nanomaterials can be used for the collections of the physical evidences from the scene of crime. So nanotechnology contributes in the forensic science in the two ways. One is the natural way, the analysis of the sample in nanoscale that could not be analyzed before due to detection limits of the instrument, analyzed physically at nano level. And the second is the man-made material, that is a synthetic nanomaterial, which possesses the novel properties that can assist the collection and detection of evidence which cannot be acquired previously. So nanomaterials are of different size, shape, and molecular weights and charges also. The most common type of nanomaterial used in forensic science are nanosensors, and these nanoparticles, nanocrystals, quantum dots, nanocomposites, nanobelts, nanoclusters, nanorods, nanotubes. Nanomaterials are able to provide improved performance over conventional techniques, or they are working together with the conventional techniques and are improving the performance of the conventional techniques. They collect information from the crime scenes that would not otherwise have been possible ever. So microchips technology, nano manipulators, nano imaging are the tool used for visualizations at the crime scenes. So nanosensors. Nanosensor is a chemical or a physical sensor constructed using nanoscales components, usually microscopic, submicroscopic in size. Active nanosensors. These are nanosensors that have the ability to send signals which could be received remotely. Passive nanosensor. These are the nanosensors that rely on observation of a change in color, opacity, and fluorescence. So these nanosensors can be used to detect the various types of the compounds, and by using various techniques, electrochemical techniques, microfluidic techniques, and others techniques, we can detect the compounds of interest. Type of nanosensors: optical nanosensor, biological nanosensor, chemical nanosensor, and physical nanosensors. So friends, I have also made bio nanosensors, and this I have used this acetylcholine enzyme. So this will fall here for the detections of organophosphorus pesticide in forensic samples. So this will fall in this category, enzymatic interactions. And there are chemical nanosensors, chemical composition based for the detections of this explosive material. And the physical nanosensor, they detect pressure, force, mass, and displacement. And most of the watches now are coming which record your pulse also, and heartbeats, etc., etc. They also contain some this sensors. This may be a physical nanosensors. So application of forensic nanotechnology, and it is used in forensic toxicology for the detection of DNA fingerprinting, or in fingerprints for the development of the fingerprints, and for the detections of the explosive material. And it also helps to provide the security features and for counterfeit proofs. It improves the analysis of trace evidence. Nanotechnology accurate information at molecular level about trace evidences such as hair and fibers, aging of blood stains, paint examination, gun-shoot residue analysis, and the question document examinations. So hair and fiber examination. Now you see the high magnification of human hair sheds light on the thinnity of the suspect and whether the hair has been chemically treated or not. So the vehicle manufacturer you are using these combinations of nanomaterials in the paints, and so we can analyze and we can detect the compositions of the paint also in case of hit and run accident cases. So this can be, it will be possibly using electron microscope or X and some other techniques. So gun-shoot residue analysis, basically gun-shoot is residue analysis is required when one has used some firearms using left hand or right hand, or there is a question that person was right-handed, and whether it was left-handed, that he cannot fire from this hand or that hand. So in that case, the questions of GSR swab is to be taken from the hands of the suspects or the accused, so that in that case also the high resolution SAM imaging can be used to detect the nano GSR particles, and the X-ray spectrometry can also be used to determine the composition of elements. So in case of armor and this, for the safety point of view, bulletproof jackets. So non-availability of standards and effective ballistic vest is a common problem. The absorptive power of these nanotubes has been tested with the powers of the missile and has been found to be tolerant and has proved to be hard of any impact effect on the wearer. This is achieved through the carbon nanoparticles. So carbon nanoparticle is basically utilized in the manufacturing in the bulletproof jackets. So this is the carbon nanotube. So this is the bulletproof jackets. In the question documents, when the one person writes something and obliterate with the same pen, or there may be a question that this writing was earlier and this writing was written later on, or the stamp was put after the buying this affidavit and after the signing or before signing, before signature. So there may be various questions regarding the documents, and once the document become question, that will be sent in the forensic science laboratory, whether this stroke is crossing over the earlier lines or not. So AFM, atomic force microscopy, can also be used in finding out that which stroke was written earlier and which is later on, and the sequence of a stroke can be detected using this AFM techniques also. So now the toxicology, from the toxicological point of view, now these nanomaterials are highly energetic or highly energetic compounds, and they may be utilized as a toxic compounds in futures, or from the environment point of view, they may be enter in your body, blood, and may cause the harms to their body. So in that case, once the case is registered, the forensic science laboratory will look after whether this contains some nanomaterial from the toxicological point of view, and these nanomaterials will be detected in the blood, saliva, hair, vitreous tumors, and bones, and even remains of the body skeleton and fingerprints. So nanomaterial has unique nanostructure and specifically interact with forensic drugs also. So gold nanoparticles, silver nanoparticle, and titanium oxide nanoparticles are commonly used in enhance the detection limit. So most of these nanoparticles can also be used to detect some drugs as well as some other compounds which are toxic in nature. So nanosensor may also be used as a immediate spot testing and a major substitute for field testing, and because they are low cost and active, stable, and they also consume very less time in the toxicological drug screening cases. So nanosensor are used to identify the drugs clonazepam, a date rape drug. This is one of the. So date rape drugs are basically used in the rave parties where the drugs are added into the drinks surreptitiously into the drinks of a female, and then the crime is committed with the body of that girl, And these are the date rape drugs. And yeah, clonazepam is one of the drugs. Another drugs are the ketamines, and another is there are 2 and 3 drugs which are diazepam is also used, and sometimes LSD are also used. So various drugs are used for the in the parties. So nanomaterials will be useful in the detections of these used drugs. So the DNA technology, basically DNA extractions and analysis is very, very costly in forensic science laboratory. The cost of the chemicals is very, very high, and the process is also time consuming. Mostly in one DNA cases, I think it may take 10 or 15 days. So now by utilizing nanotechniques and nanomaterials, one can reduce the cost of DNA analysis and as cost of the DNA analysis as well as timing, and I hope so. In future, the nanomaterials will reduce the cost as well as timing and sensitivity too. DNA analysis of the blood stains, hairs, fiber Siemens can be carried out. Nano device that can be used are microfluidic devices, are the recent advanced devices used for forensic DNA analysis. The advantage of these devices are shorter examination time, risk of contamination is less. It is directly applicable at the crime scenes. So microfluidic chips technology are using single nucleotides polymorphism, single molecule sequencings, may also revolutionize this field by providing enhanced sensitivity for detections of the trace material. Extractions of the PCR ready DNA samples from body fluid and specimens of skeleton remains. Silica-based magnetic nanoparticles, and copper nanoparticles are used. Isolations of DNA by tight nanoparticles with carboxylic compounds act as adsorbent for PCR applications. Gold nanoparticles are also used to enhance PCR efficiency. So this is a improvement in PCR efficiency using gold particles. So now the different fields, now we are entering in the different field, which is the fingerprints. The fingerprints proves whether the culprit was present at the scene of crime or not. So fingerprints may be found at any surface, which may be a glass, it may be door, it may be a different surfaces. So to prove the presence of the culprit at the scene of crime, so we have to find out the latent fingerprint, which are hidden fingerprint at the scene of crime. So basically, we are using the conventional powders for deciphering, for visualizing these fingerprints. So now we are having some nano, with the help of nano powders, we can visualize these hidden fingerprints in a better way. So this zinc oxide nanoparticles, titanium dioxides, silver nanoparticles, and gold nanoparticles can also be used to decide or to detect or to visualize these fingerprints. Traditional chemical reagent methods with latent fingerprints are developed via reactions between reagents and amino acids and fatty acids from fingerprints. Basically, ninhydrin was used to detect the fingerprint for detecting the amino acid present in the fingerprint. And nanopowders also be used to generate latent fingerprint maze by detecting inorganic elements such as potassium and chloride. So nanopowders generate clear latent fingerprint. Now you see the clear-cut image of the fingerprints. And gold nanoparticle enhance old fingerprint on non-porous surface. Nanopowders. Advantage: stability of inorganic element allows development of old and contaminated latent fingerprint. So the foreign material can also be detecting using the foreign substance in the hands. Lotion and sunscreen detected due to residual TiO2 and zinc oxide nanoparticles. If some cream is used by some criminals or in any sexual crimes, so that this TiO2 and zinc oxide nanoparticle can be detected. So investigate food consumption by looking elements detected in saliva and food residue found in fingerprints. So detection of illicit drugs in fingerprints. One of my colleagues was detecting the amphetamine drugs using the nanoparticles and by making the various biosensors. So these drugs, amphetamines and other drugs, narcotic drugs, cocaines, etc., can be detected using these nanomaterials, nanotechniques. So this is the visualizations of fingerprints present at the scene of crimes using various nanoparticles. Now the explosive divisions or the chemistry divisions. These nanomaterials can be used in making the ultra-sensitive sensors and such as TNT, RDX, PETN, and other explosive substances can be detected using different types of nanomaterials and nanoparticles. One is the nanoparticles is curcumin nanoparticle is used to detect the high explosivity trinitrotoluene. And the nanoscale developer X-ray source and laser source may be helpful. It is possible to image the etched fingerprint even if the casing has been wiped or washed using nanotechnology. At the firearms, if it is washed and it is wiped out, so by using this nanotechnology, we can visualize the fingerprints on the firearms. Forensic explosive detections. So electronic nodes containing this nanomaterial as a sensor, as a sensing material, and can be used in making electric nodes or electric nanonodes, and to detect the hidden explosive material. Security features and counterfeit proofs. Luminescent nanoparticles could act as security features to make a document secure and counterfeit proof. Nanoparticles could be incorporated either in paper tissues or in specific ink. And in passport, in Indian passport and in other passports, basically the various countries for making it very secure, and the agencies are adding the nanomaterial as security features which can fluorescence, which can produce high fluorescence and may act as a security features for the to prove the whether it is fake or a genuine one. In currency note also, nanomaterials can also be used as a security features. And in various articles for security, these nanomaterials can be used. And in barcode also, nanomaterials can be used. So presence of nanomaterials in case of fictitious products. So these will be these holograms will be analyzed by the forensic science laboratory, whether it contains nanomaterials or not, to prove that it is original one or not. So now I have to sum up it. Nanoforensic is a very vast field and is rapidly expanding. It is providing promising solutions to the different medical legal challenges and various different fields. So in forensic science laboratory, we are having different laboratory we are having photography. So in photography, nanomaterials is in the film. Earlier it was the silver bromide film was used and hypochemicals were used, and now you see the chips are coming, and which is storing the large number of the photographs. And we are having now photography, we have document divisions. So in cyber cases, so different types of the materials are coming to us, and in near futures there is a strong need to open a nano forensic division in the forensic science laboratory to find out the presence of nanomaterial and to utilize the technology, nanotechnology, in the field of forensic science, and in the, to provide a better solution in the criminal justice system. Thank you, ma'am.
Thank you so much, Amarpal sir, for such a elaborative talk.
Thank you, ma'am.
Thanks a lot.
Thank you, ma'am. Thank you. Any question, ma'am?
Yes. Abhyavartan, are you taking some questions?
Currently, there are no questions in the chat box. So if there are any questions from the panelists, we can hear from them.
I have one question, Dr. Amarpal. The one question is that these are the techniques which are proposed for nanotechnology use in forensic science. They are excellent. With what you describe is excellent talk and excellent things, which some of them we don't know. But how much these are applicable now in like in Delhi or in India? So can you explain something? Can you throw some light on that? We are using now, my means.
Sir, presently, I think your question is whether we are using these techniques presently or not.
Some of them techniques, yes.
Sir, basically, these, you know, sir, most of the people are traditional people.
Yes.
They are following 100 years old methodology, old manuals. Basically, they don't want to explore the new things. One thing, they don't have the charms in their body, right, sir? But what I have learned from this AI entry departments, a lot of, you know, Josh, जिसको मैं कहूँगा आपको Josh, एक मेहनत जो hard work from all of you, and a strong zeal to utilize these techniques. What I have learned, the electrochemical is cheaper techniques which can be utilized tremendously for detections of the various compounds, not only inorganic compounds, but also the organic compounds, just like the pesticides which I have detected. And my colleagues, which are my doing PhD, they were detecting amphetamines. And a lot of work is going on using different technologies. Sir, microfluidics techniques are also used. And in pesticide, for pesticide detection in the agriculture side, the quantum dots, the gold quantum dots are using for detection of the pesticides. And sir, I am sure in DNA technology, sir, they are using nanocolumn.
Yes.
People are not aware of this, sir. But you know, these are our conventional techniques, which are old one. They are now getting upgrade. They are upgrading using these techniques.
Yes, you are right.
So there is a, we should be aware of that upgradations, like water filter, which were consuming waters, they are using. And in sunscreen, lotion, creams, we are also getting all sort of nano stuff. So we should be aware if these such type of material is being encountered at any scene of crime or anywhere, and suppose a questions may arise, sir, it is a fake one. We have used nanomaterial, but this is fake one. How can we decide that fake and original one? So we have to detect nanomaterial in that, sir. So once the question becomes a legal one, sir, then question will come to forensic laboratory, sir. And if it is of development of the nano techniques, it is, sir, up to you. We are actually user.
Yes.
We are user of your techniques. And in future, certainly, automatically people will know it. Sir, TV are now very small, very thin. Earlier TV was very big, sir.
Yes.
So conventional TV are no more now, sir. Phones are no more. So
Yes, you are right.
nanotechniques is entering in daily life, in society, everywhere with us.
Yeah.
It is monitoring us. So we have to adopt it with open heart.
So we have to need, we also need some expert of this. The problem is this: there are many people who don't know about them. Means the forensic people. You are the expert, but maybe some.
Actually,
Many
sir,
of
it's
them.
a multidisciplinary thing, right? They
Yes.
have problems. We have some techniques, but if it is in a group, then definitely that can be done in a very good manner.
Mittal sir.
Yes.
I have done my PhD is first in nanotechnology, sir. Forensic and nanotechnology.
Right.
Yes.
So it is a good combinations, and I have learned a lot of things. So I hope that a good collaboration with the nanotechnology departments and this forensic laboratory will give some better inputs to the students, coming students, that so that they may utilize these techniques
In
for better
forensic.
detection or better criminal justice system, sir.
Yes, you are right. Thank you, sir.
Thank you, sir.
Thank you, Amarpal
Over to
sir,
Bharti.
once again for such a elaborative, detailed talk. Thank you
Thank
so
you, ma'am.
much. With this, over to you, Abhya.
Thank you, ma'am.
Thank you, ma'am. Thank you so much, sir, for your excellent talk. Finally, we have our last eminent speaker of the day before we hear from our institution's young achievers, Dr. Ved Varun Agarwal. Dr. Ved Varun Agarwal is the principal scientist at National Physical Laboratory, CSIR. He has over 19 years of professional experience in material science, characterization of material, analysis, and kinetics. Currently at NPL, he is contributing towards biomedical meteorology and fabrication of biosensors for the detection of total cholesterol in blood, for cholesterol biosensors, high sensitivity, faster response time and linearity over required range has been achieved and optimized at bulk and in microfluidic system utilizing novel nanomaterials. The findings of research work are now being utilized for fabrication of handheld device for quick detection of total cholesterol and multi-analyte biosensor for simultaneous detection of blood glucose and cholesterol using microfluidic chip based on colorimetric detection. He has been awarded CSIR Young Scientist Award for year 2014 in Physical Science and Instrumentation, DSC Fast Track Project 2009, CSIR Empower Project. He has also qualified GATE 2002, qualified JEST 2002, and qualified Joint CSIR UGC National Eligibility Test NET for lectureship. Today his talk will be on nanotechnology and meteorology in biomedical sciences. On this note, please join me in welcoming Dr. Ved Varun Agarwal to the platform. So you have 40 minutes followed by question and answer sessions. I request you to please summarize your talk in the timeline.
Not audible.
Dr. Agarwal, we are not able to hear you.
Though he has unmuted himself.
Maybe he is not able to hear us. Seems.
Might be, ma'am, some network issue.
Call him. Let me call him.
Yeah, now he is, I think.
So please check your mic setting. So you are using headphones, so go without your headphones, sir.
Wait, sir, go without headphones.
Now we can see him. Yes.
Yes.
So we can see him, but he is not audible. Sir, please rejoin again. Yes, sir, please rejoin again. मैम सर को फोन करके बोलिए रिजॉइन करेंगे दोबारा से.
Okay, okay.
Hello, is this audible?
Now, yes,
now,
sir.
now you are audible.
Yes,
very
you
good.
So rejoining is not a correct solution because if the problem is there, it will still be there.
Okay.
Anyway, it's nice introduction. I just forwarded CV and it was not supposed to be read line by line. Some wisdoms was to be used. Anyway, thanks for that reading, and I thank Dr. Upi Sinha for inviting me for this workshop. And I really like all the talks actually. In the morning, some BIS introduction and the quality system, even just now this forensic science. So I'm happy to see people are more in, for measurement and going just away from fancy science to actual science. Um, and something which actually contributes to society and also to the industry. So that is our idea, and more happy to see the amenities taking a lead. I mean, which I assume that some government organization should be putting these people on a common platform. So amity being having a role of just educating people, but they are still taking a lead and joining like scientific institutes like us and industry people and other things. So this is a good step, good forward step. So I'll begin my talk. I'll not waste much time. I was very confused because we are not the teachers, so and we don't keep our presentation ready. We are mostly working in a lab, but still, let me try to justify how best I can do. So, yeah. So nanotechnology and metrology in biomedical science.
Sir, your screen share.
Hello?
Share your presentation on the screen.
Yes.
It is not visible.
I almost forget that. So entire screen. So is it visible now?
Not exactly. Yes, now. Yes, now it is. Yes, now it
Presentation is visible. Yeah, fine.
Yes.
Fantastic. Okay, so nanotechnology. So I was trained as nanotechnologist, but over a period of time, I have become meteorologist. So and I'm working in a biomedical science. So it's a combination of all three. So the societal application. This topic actually took me on a drive that what societal application I should be talking about, because the societal application, the meaning itself is changing with the time to time. For example, especially after COVID, I think every definition has changed. This concept of offline mode, meeting in offline mode, what is this? I never understood. Earlier we used to say that there is a meeting, but because the concept of online came, so the normal meeting we call it offline meeting. It's like underrating the usual interaction between the people. Suppose two people are sitting in a restaurant eating, so we'll say that they are in offline mode. I don't know. I mean, so this is like society. The definition is changing with the time. So is the importance in the application. For example, there was a time when leaded petrol was considered to be good, but now it is not. Similarly, the online system was not appreciated at all. For example, IGNU, it was universities in India since so many years, but it was never, see the light of a day. But suddenly now everything is online. People take online tuition, they do online learning of music, everything. So the societal application changes with the time, and COVID-19 was one of the things which has changed. So is in the diagnosis. I remember Dr. K.K. Agarwal was talking in one of his interviews that today, after COVID, every household has become kind of clinic or laboratory in itself. Everybody has this SpO2 meter, blood sugar level monitoring meter, cholesterol meter, even this, blood pressure meter. So we are have evolved in a way that we have brought many things to the site. So that is called home school, home hospital. The concept has changed. So is the science has also changed. So I will talking about point of care, lab on a chip, little bit, and this societal application. I really do not know what application is, because today, like sir said, people are using nanomaterials even in sunscreen and everything. So nano is considered to be very good today in today's generation, 2020. But you do not know. Maybe after 2040s, people will say, no, do anything, but do not use nanoparticles and nanosystem. That also may come in coming years. We do not know. So societal application and nanotechnology in societal application, in the present context, yes, it is valid. But in the larger context, once we understand the science, it may change. So I'll take a little background because I mentioned COVID. So when COVID came, Indians were not just, I mean, we were just not knowing, what viral infection, what bacterial infection. An ordinary person now can tell you that this is viral infection, this is bacterial infection. Many times our doctors, they will prescribe you, antibiotics in a viral infection. So we did not have clear idea of what is what. But today, I think we have evolved a long way. So in the COVID-19, India, when first time the system came and we saw on the Chinese people wearing, complete this blue kind of this coat, PP kit, which we call. So we were thinking, what is this? Is it a space suit or something? So anyway, so that was a kit which is supposed to, stop the or take care of the infections which other person has, especially the viral infections. And we were not even knowing that thermometer people were holding in a hand. Few people initially thought that what is this? They are scanning the virus using that machine, but it was just a thermometer. Anyway, so this PP kit, it is so when this kit came into the India, many people started making this PP kit just with normal cloth, and that was just not sufficient for the purpose. There are people because there is a certain criteria it should follow. Every PP kit should have breathability. For example, so, I've seen doctors wearing this, and in 1 or 2 hours they are sweating so much that they get all the skin infection because of this PP kit. So that was very surprising. You know why? The reason was that people were making this PP kit out of this raincoat material or just plastic, and that shouldn't be the case because you are supposed to wear it for a day, so it should have some breathability. If you don't keep that breathability aspect into it, uh, the moisture will retain. It will retain the moisture, and that almost will cause all kind of skin infections to you. So the few criteria for a good PP kit is a good or what system is that it should have a breathability. It should have some force handling system which is like it should not tear. It should not tear from the uh, where it is and also one the very important aspect is suppose somebody who is having some infection or some wound, and if that person is wearing a PP kit, the blood of that person should not cross the PP kit. So to check that, there is a test called blood penetration test. Okay, as listed. So the blood penetration test also has to be done at certain pressure, and of course that pressure is related with your blood pressure. If anybody has any question in middle, they can stop me and ask. Okay, because I just don't see anything other than my own screen. So this is also very strange way of giving presentation. So this is a in between. You can see there is a system which is to check the blood penetration in this PP kit. So we designed that system during the pandemic in our lab, and then the another criteria for this system is we could arrange the PP kits, but then to check a blood penetration test, you need to have a blood. Now we don't use real blood in this test. We need to have an artificial blood. So then the concept of artificial blood again is like a novel concept. What is artificial blood? Is it the blood which we can inject in our body and survive? No, this is not that artificial blood. This is a blood which possesses physical properties similar to the blood. For example, our blood is red in color, so this is one physical property. Our blood dries, it has particular surface tension. It is not very fluidic, it is little viscous. So all this, and it also is, little sour. It's like little, it has some pH. So these are the properties of a blood. So in artificial blood, which is subjected for this kind of test, should have those properties. There are nanotechnology efforts where people are, taking oxygen carriers and nano system oxygen carriers, putting in a blood and making an artificial blood. That is altogether a different research. That is also a topic of interest these days. People do make real artificial blood, though it was the research started some 30-40 years ago, in 1950s rather. But still it has not developed. Now people are working on this in the light of nanotechnology. So after having an artificial blood, you have to cross-check whether the physical properties it possesses is actual the same as the blood. Okay, so one of the property is viscosity, which is okay. You can use rheometer to check the viscosity. Another property which I am focusing on this talk is the surface tension. Surface tension sounds very simple, but like it involves a surface, and it's not easy to measure a surface tension to the accurate level. So I'll be talking about this. What are the challenges and how one can go for accurate surface tension measurement. So this is a like structure of the talk. So just to give a little brief, our length of our heart is around 15 centimeter, and weight, okay, doesn't bother, it's around 300 grams. So overall stroke volume, the heart volume which it carries one time, the amount of blood is around 70 centimeter cube. Okay, and in 1 minute we breathe around 60 to 80. So let's say 70 times. If you're playing, maybe it crosses 100 beats per minute. But usually, if you are normally sitting or listening to my talk right now, your heart probably is beating at the rate of 70 to 75. You have, if you have a smartwatch, which is again a technology, you can always check. So you in 1 minute you 5 liters of blood, around 5 liters of blood is passing through your body. This is a general value, and this 5 liters of blood is going through arteries and veins of a different diameter. Okay, near heart they are very wide, and near your finger they are very narrow. So the pressure is different. So as you can see in this curve, that you have pressure ranging from 120 to 80 mmHg, and that is near heart. Okay, and as you go away from the uh, aorta and near heart values, and you go to maybe finger side, so you literally drop that pressure, and it goes around 20 mmHg. So suppose I have to check for the penetration of blood. I should be checking because I do not know where my injury would be. So it should be ideally people take double the value of 100, that is 200 mmHg. But when you are injecting yourself with some IV or anything, because you are injecting in the arm and the blood pressure around that is around 20. So this is a typical blood pressure values you should be keeping in mind. This is just for your information. I will be using this reference in the talk later on. So this artificial blood, so the we can generalize them as a synthetic biological fluid. So I work on synthetic biological fluid. The kind of fluid we make is artificial blood, artificial urea, artificial saliva, tears, blood plasma. These are to be done things. So where are these things used? Enough. For example, artificial saliva. It can be used, when you have a dental implants and you make them with titanium or some materials. So you want to see whether again this saliva will have physical and chemical properties similar to your saliva, and whether it interfere or whether it degrade your dental implants. So those things people check using an artificial saliva, and the users are the industry who make this dental implants. Similarly, artificial sweat, this your specs you are wearing, or the frame, or any cloth, or even your bike, the polish, all these things people subjected to different kind of sweats and artificial sweats, and see whether any reaction is taking place or not. Blood I have already explained. So there are series of artificial fluids around us, and people make they have still not successfully able to make to the best of their ability to the replica of the real fluid, and that's where the nanotechnology comes in. People are using sometimes nanomaterials to replicate certain property. For example, I mentioned about the oxygen carriers in the blood, or maybe in saliva to viscosity, or different things. So this is a open area topic to be researched. So synthetic blood. So synthetic blood, we have some standards, ISO standards or Indian standards, to make the synthetic blood for blood penetration test, and that blood, synthetic blood, should have a surface tension around 42 Newton per meter, or 42 millinewton per meter, you can say, and pH it should be having around 7.3 plus minus 1. This plus minus what you see here is very important. This meteorology or even in forensic science, they give lot of emphasis on this uncertainty or error values, viscosity and conductivity. These are the 4 parameters which actually define an artificial fluid. So there are instruments which can give you the and this is a formula how you can make an artificial fluid. You need CMC, you need twin. Twin is there to give it this surface tension, sodium chloride and this potassium dihydrophosphate, and they are to make stable pH. They act as a buffer, and dye, amaranth dye to give a red color, and yeah, CMC is there to give a viscosity. So this is a typical formula, and I'm sure some physicist has designed it because he has just considered that adding these 4 components and they will not interfere with each other and they will give you the artificial blood. But that's not so simple. So surface tension. So I will be focusing on surface tension in this, and surface tension has a lot of application everywhere around us. We are using surface tension, for example, your contact lenses. They will have a surface tension. All petroleum products, they check the surface tension, and wherever you are using, if you are making a windshield or anything, all this surface, wherever you see a surface, assume that the company must have checked that surface against some liquid or some material and studied the surface property extensively, and also how it reacts with different kind of liquids, maybe rainwater or maybe something else. So surface, and that is one of the measurements they perform, is a surface tension. So surface tension is very critical, and accurate measurement of surface tension is even more critical. So to accurately measure surface tension, you have 3 primary methods. When I say primary methods, what I mean is that these methods are traceable or can be easily realized wherever they are. It's not that they are very complicated, but they are linked to some physical phenomena. So the 3 primary methods for surface tension measurements are pendant drop method, which you take a drop, hang, and that drop will never be spherical because of the gravity. It will always take a shape or bulge towards the ground. So it will make a pendant-like shape like this when you see on your right. Okay, so that is a pendant drop method. Second is Dunio ring, like you make a ring. You have seen the kids dropping a ring in the soap solution and blowing air and it forms bubbles. So that kind of ring, but only thing is that ring will be horizontal. You pull the ring from water or any liquid, and it will carry the meniscus along with it. And how far that meniscus goes and how much liquid. So that is a Dunio ring method, very layman method. And another is Wilhelmy plate method, where in a laminar flow system or many systems, people use, you have a vertical plate, you dip it in a water or any liquid, whichever liquid, you pull it up, it carries or pulls some liquid around it, and you accurately measure the angle and the force that liquid is pulling this plate with. So you can also find the surface tension using all this. But in the Dunio ring method and Wilhelmy plate, you need a lot of liquid. While in pendant drop, even a drop of liquid is sufficient to give you the surface tension. And also the evaporation is very critical. Kind of temperature we have in India and Delhi, and these conditions, even if you maintain the temperature conditions, the evaporation is very high. So pendant drop is most preferred method. So this is what we worked on. This is a typical setup. You can see there is on your left you have the instrument, which is on vibration proof support. You have a light source, and the light source, and on the other end you have a CCD camera, and in between you have a needle through which a drop is hanging. So what you see is the shadow of that liquid drop, because the light between so what we see is a shadow of that liquid drop on the CCD camera, and you have a dispensing unit. You can make that size of a drop smaller and bigger as per your requirement in the system, and you have that syringe pump associated with it. And these are typical drop shapes. Uh, Spherical is, in rare cases you see a spherical. When the drop is very small and the diameter of needle is very big, you see a spherical shape. I'll come to that, in which case you see spherical, in which case you won't. So this is a typical experiment, and what you do is, like, once you find a shape of this pendant, so this shape depends on the interfacial tension, and it comes from the Young Laplace equation. So you can imagine this way, that the gravity is pulling the drop downwards, while the interfacial tension of the liquid is pulling the drop up. So there is a tussle between gravity and the interfacial tension, and that uh, tussle is giving this deviation in the shape. So you can find the deviation in the shape by how much it has shifted from being circular, and if you can find that, you can solve that equation and find the surface tension. So we have done that, and this is a typical thing. If you see on your extreme left and below, you see around 60 and 2. So this is the water. The surface tension of water. Okay, I'll also give you the surface tension of liquids. Uh, in the liquid, the water is one of the liquid which has the highest surface tension. That is 72 millinewton per meter. Because of the hydrogen bonding it has. Even more than water is your mercury, and any other liquid is lesser than this. Take my words, the surface tension from any other system will be lesser than this. So somehow nature has made water in such a way, or that's the reason why water exists, that it is not so easy to go away or even to evaporate. That. So if you see the reading which shows a 60 surface tension of water as a 60, the drop shape in that case is almost spherical. It means I'm not able to read the correct interfacial tension when the shape of my drop is spherical. It should be really a pendant shape. So as I go away from, as I increase the size of water drop, so as the size of water drop increases, the shape distorts and it becomes more like a pendant shape. And that's where I see the right surface tension from the water. So on the right side above, you have values approaching to 72, and like every measurements, you will have 1 or 2 points because of the instrumental error or something. So how to find a correct or accurate surface tension? So the meteorologist will do, he will just repeat the experiment 1000 times, 100 times. And this is what we have done. We have repeated the same experiment 50 times. We got this kind of curve approaching to 72 millimeter per meter, and that too for a needle which diameter was around 0.9 millimeter. All this diameter is measured to the well accuracy to the national standards. So here is a chart. So we have taken 3 different needles, and their diameter is varying 0.9, 1.27, 1.65, and we assume that larger is the diameter of a needle, more water it should be able to carry. So if it's able to carry more water, so we should be having more accurate surface tension. That was our objective, but science is not so simple. So when we did the experiment with, as you can see, on the left you have 0.9, in the middle you have 1.27, and on the right you have 1.65. So as you increase the diameter of a liquid, the scattering also increases. And that is the reason, because of the evaporation is another factor which kicks in, and it makes measurement a little difficult for us. So these are the parameters which we have to keep in mind when we are working on the making something as a national facility at MPL. So I have a 3 system. All of them are giving around 72 millimeter per meter. But then which one to pick? Also, if you see carefully, the first phase of all the curves, in the yellow needle, it reaches to that 72 very fast. The slope is very steep, while as you go away from the or as you increase the diameter of needle, the the way it goes to the 72 value is gradual. So that slope tells us that I'm stuck in my spherical zone for a longer time. So when I'm in a spherical zone for a longer time, does it mean that my evaporation will be least? Because I know that anything which is spherical in shape should have a least surface area, and least surface area, I assume that if surface area is least, so evaporation should also be least. But that's not the case. So we have done the evaporation study, and we found that if you look at the fourth curve comparison, or maybe you can look at the slope. So evaporation, to our surprise, was least for the pink needle, which had the diameter 1.27. Now again, this is surprising. We were expecting that because this, the rise was gradual and the spherical shape of a drop was maximum for the white needle, so the slope should be least for the white. But then the volume of drop also increased, so that is the reason why it has a maximum slope. And yellow needle, it always was in a zone of pendant drop, so that is the reason why it has the evaporation higher than the pink needle. So my choice would be, or anybody's choice would be, pink needle in this case, because it is showing the slope which is 0.0040, least in all these cases. So, but then this is just an evaporation study. Now we have to see the effect of evaporation on interfacial tension. So when we computed interfacial tension for this corresponding drops, again we found that the slope is maximum in this case, meaning the and the value is closest, meaning that the pink needle, which was our choice in the previous experiment, is the closest to real value, and it deviates very fast when it is left for or it is unattended. So it means that we have to do this experiment with the pink needle in very short time, because as the time passes, the pink needle is the one which changes maximum. Okay, but then again it is most accurate, and this is a usual case in life everywhere, that something which is very sensitive cannot take too much of what you can say. I'm not finding the right word. Too much of changes. For example, if you have very sophisticated watch, you will not be able to play with that watch. It is not normally repeated. So same is with the system. A very sophisticated system has a very narrow range. In fact, biosensors is also like that. They are very accurate, but for a very small range. There are some systems which works for a wider range, but then the accuracy goes off. So the same is what we found in this case. So when we club all this, we could find our accurate way of measuring the surface tension. But then we still have to make an artificial blur, and to impart actual surface tension of water, which is around 42 millimeters per meter. So we have to add something to the water which doesn't evaporate so fast and gives me that value of desired surface tension of blood, artificial blood. And so we picked this twin 20. So we have taken twin 20 and again repeated the experiment with 3 different needles, and we found that yes, indeed, it is taking to 45, 44, but not to 42. And then we thought that maybe again this twin is something which comes in a variety of composition, like twin 20, twin 40, twin 60, depending on how long is the compound. So when we had taken twin 40, we found that surface tension actually increased. The average was around 50, approaching to 50. And when we further taken twin 60, twin 60, it has further increased around 54. So we were going away from the desired value. So we should be taking something which is lesser than twin 20, but we don't see anything in the market. So this is still open-ended. How do I bring down the surface tension of water, adding twin to it, but bringing it close to the surface tension of artificial blood. So maybe that's where the nanotechnology walks in, or some organic chemist walks in. So these are the areas which still have to be addressed. So my research on this is still continuing, and and uh, so, but I want to emphasize that in this measurement, in this experiment, what are the sources of uncertainty, which probably maybe I'm not measuring the correct interfacial tension. So we use this process of digitization. As I said, that what we see is the shadow of the drop. So shadow of the drop is the black thing is the shadow of a drop, and we find the pendant shape or the geometry, and we use this digitization methods, Sobel, Privet, Laplacian, and Kenny, and these methods also will have their own uncertainty. Is that probably I'm getting the right surface tension, but because of this methods which I'm using, I'm not able to accurately find the shape of a drop and do it. So that is also possible. So we, as a meteorologist, take care of all the things, all the possible sources of error, all the possible sources of uncertainty has to be incorporated. And this is the way to do it. This is a diagram. Some people call it fishbone diagram or something like that. So this takes care of all the factors which is affecting my measurement. And I think science should be done like this. In all the studies, you should always list down what all are the factors affecting your measurements. And I hope that this kind of practices are adopted by uh, the general day-to-day science also, because I've seen people do one or two experiments and they conclude. So, okay, not to comment on that, but yeah, this is a way. So we have taken into account that what all are the parameters, and very strongly we can say yes, indeed, whatever measurements we have done, what the surface tension of water is this, and the surface tension of our artificial blood is this. So we are going to come up with this method, and to ease, if somebody doesn't want to go with all that measurement, the easiest solution to that is you print the shape of that drop into slides like this and come up with a solution which is called a reference standard. So soon we'll be having such kind of reference standard for people to use, and to make that you need a proper photolithography setup, which will be designing this kind of system. Now I'll address a little bit of lab on chip, point of care. As I talked about system, that the societal application is changing. People are moving towards home and taking care of themselves for everything. So in typical lab of chip or point of care, so what is lab on chip? Is one can see the device which integrates several laboratory functions or practices in one platform or one area, maybe on a blackboard. Even a mobile can be considered as um, integration of so many functions on one platform. So that is equivalent to entire and function of a lab on a mobile. So that also is kind of lab object, but not in this aspect. Here we are talking about something experimentally. What we can do is, and the idea of LOC was to handle the liquids or to develop a microfluidic devices basically. So when we work on the microfluidic devices, we brought this term lab on chip. So why lab on chip? It takes lesser volume, faster time. It doesn't take abusing from environment like heating or evaporation we just faced, and the fabrication cost is lower. It can be taken into the masses, printed into the masses. Safer platform. Even you can deal with the hazardous chemicals or something, and because it is not exposed to environment, it will retain its sanity and better process. And these people are moving to this, but there are disadvantages also. They are not fully developed, and we have seen that even today we have this the glucose strips, they are microscope based for detection. So it is walking into our life with a very fast rate, but it is not evolved to the level which we are expecting. Like other technologies are evolving much faster than these technologies. Some applications or examples are this real-time PCR detections, the biochemical assays, they're already, we see them around. They're the real examples actually. The blood sample preparation, dielectrophoresis, that also is an actual example of laboratory. So, so how do you make these chips? So what we do in our lab is we use this PDMS on a glass slide, and this is a typical process. We take silicon or a glass wafer, we spin coat SU8, and that SU8 and then project the pattern um, in our lithography system. SU8 is negative photoresist, and we form a pattern which is very strong. SU8 is very strong polymer, it doesn't, and then we get a mold, and on this mold pour PDMS and peel off this PDMS. So SU8 remains there. We can make 70 to 80 patterns of PDMS with one SU8 mold or a master. So this is what on the sixth number you see is the finally formed pattern of PDMS with the channels inside it. This is the simplest channel as shown as an example with size around 200 micrometers. And so in such a small volume, if you want to pass a liquid, it will not pass just like that. You have to forcefully make a flow of it. So that also I'll talk in later, how flow is taken care of it. So this is typical way of making a PDMS based lab on chip. People make within various methods. People make on paper also. And so like I said that either you can place it on a glass, or you can have also glass which is having certain patterns. So in this case, instead of glass, we have taken ITU. We masked ITU with photoresist, positive photoresist this time, and make a pattern in that positive photoresist and etch away the remaining ITU from it. So what we are left with is a glass and patterned ITU. And I have written the formula of the etchants. So what we did further was we used them for cholesterol detection, the point of care devices. And cholesterol, again, like initially we talked about, that when you have a blocked artery or anything, so the cross section area decreases, and so blood has to be pumped little harder, and that is reason why the blood pressure changes when we have a blockage or anything, and people measure blood pressure. And this is again people measure at home and immediately diagnose what could be the problem. So, but this is a typical blockage, and cholesterol has a nature of going and sitting inside the system. So this is a typical scheme where we used anatase TiO2, the metal oxide. We have used numerous metal oxides. We have used titanium, nickel oxide, and other nanostructured metal oxide also. But this is I am showing only as an example. This was a very simple initial work where you have simple microfluidic channel inlet from where you are passing a cholesterol solution of different concentration, and you have a printed electrodes where you have printed anatase TiO2 on ITU. You have further deposited on ITU the anatase TiO2 by electrophoretic deposition and recorded using electrochemical methods. Like previous sir, he said, electrochemical is indeed a very robust and reliable method for all these detections, and we use that. And I'll just show you the table, comparison table, where we have found that the metal oxide shows a superior results as compared to typical gold system or carbon system. Further, we did on nickel oxide and other systems also, and we got similar results, in fact better than this. And also to simplify this, we also tried making that instead of PDMS, we tried making it on paper. So we had this 3D printer which we made it into a 2D printer. We removed the Z axis, and instead of Z axis, we had this syringe pump connected to with the pipe, and used that similar needle which I was talking about, 18G needle, the pink one, and we made, did optimization at a different flow, and we wrote on a different type of paper, different filter papers and membranes. And again, the problem with, so here we wrote with the PDMS in combination with hexane, but the problem is that it evaporates or it spreads a lot. There was optimization studies involved, and after that optimization, one can always make patterns like this of your choice, and you can pour your analyte of interest in the middle. It separates, and you can have a multiple detection. For example, here we have same solution spreading and giving you multiple colors. This is not very clean system. Here it leaked out. So these are the real problem challenges. It leaked out not because of the paper, but because it was standing on some surface, and that surface acted as medium for flow. So these are the challenges. And these are the studies which are still in optimization. But what pumps to be used in medical frame in this system, like I talked about, that pump is very crucial, and even in medical system, we or in the hospital or during the time of COVID, people were injected with different type of medicines, or even at hospitals, you give IV. So the pump which we use in medical sector are of various type, and mostly people use volumetric and syringe pump. Even for our application, the flow has to be consistent. So how do we measure the consistency of a flow in this pump is what this work about. So there are typically four category of pumps. You can say syringe pump, the infusion pump, the pressurized flow, and the okay. So which one among syringe pump, volumetric, and emblematic is more accurate? So these are the studies which say that syringe pump is always more accurate, and the parasitic pump is the least accurate. And we in our metrology institute, we NPL, we have to do experiments to ensure everything is perfect. So how do we ensure that which pump is very accurate and which pump is not? So for that, again, we have a primary method. Like I said, primary method is something which is directly linked to some physical phenomena. So here, this is a primary method which is called a gravimetric method by, again, Indian standards, IS 13450, to find out the consistency of the flow rate. So what we do in this method is we keep our syringe pump at particular flow, allow and collect water in particular duration, and we know that the water density is 1. So if 18 gram or 18 ml of water is collected, its weight should be around 18 gram. This is a physical phenomena, that density is mass upon volume. So this doesn't change. So that's where the primary method is sitting. So we measure the amount of or weight of that water and find the flow from that. So this is a primary method of finding a flow. And for a medical sector, for medical purposes, by the way, India still lacks the, uh, the calibration method for the infusion pump analyzer, which we are developing at NPL. And this is calibration setup for infusion pump analyzer. Infusion pump is the pump, like we have a syringe pump. This is a pump which is used in hospitals to deliver medicines, or even anesthesia, or even to drugs, or even a food to the patient. So this pump has to be very accurate, and it should not be able to cross particular pressure rate, because like I mentioned that in your IV, the pressure is around 20 mm Hg. So if you are delivering anything with a high pressure, it can just burst inside the person's vein or arteries. So it has to be, the pressure has to be maintained. So this infusion pump, unlike syringe pump, maintains that pressure, consistency of that pressure, and delivers the requirement or required dose into the human system. And this is a system for its calibration. And this is a chart that shows that which method of pump is accurate. And again, like I always say, that being a metrologist, we look for all the possible uncertainties or errors which is possible in that particular system. So this is a study related to that. And any questions? I'm done at this point. Hello.
Thank you so much, Dr. Ved, for such a detailed talk. You have covered different aspects of nanotechnology, especially like in biomedical applications, starting from biomedical, then the raindrops, then the point care devices, full strength variety of applications, and within a fixed time frame. Thank you so much, sir,
Oh,
for
I
that.
finished in how much time? 40?
You have finished exactly at 40 minutes. Like,
Oh, yeah.
but yeah, you
So
have to.
meteorologists keep.
Yeah, that's what I'm saying. That it's in a fixed 40 minutes, even with a perfect plan. And you have covered a variety of application. Right now, means while listening your talk, I was realizing that means so many areas are still where we can do a lot of work. Is still
Yes.
there. In fact, I would like to invite you sometime in campus if you have time, so that you can deliver a talk to our student also. So they must be benefited
Sure,
for.
ma'am.
Yeah, we will take
Sure,
your
sure.
sometime a proper a particular lecture on at least one topic from your side, so that the student can be benefited from that.
Sure, ma'am.
Over to you,
Thank you,
Abhya.
ma'am. Thanks for. Yeah.
Thank you, sir, for your fantastic lecture. So now we can move on to the next segment of the session.
Abhyavatan, I have one question to Dr. Ved, just a small question.
Yes,
Please,
Sir,
ma'am,
you
please.
have mentioned the POC point of care applications, the point of care devices. Sir, with respect to selectivity of any analyte, how much they are accurate enough if I compare it with the traditional sensors, sensors for any applications. Like in biomedical, a lot of interfaces are there with respect to the analytes.
Okay. So, ma'am, I'll tell you one thing. The mm, in the any microfluidic system, when you are taking these measurements, for example, there is a small room and there is a very big room. Okay, so if you have two type of or two three types of people in very small room, so you will be knowing the presence of each person very fast. Okay, if the same or the same amount of people are distributed in a very large hall, okay, you will not know their nature or will not know about their presence also. The same is with the microfluidic system and the bulk system. Okay, so the microfluidic system is much more sensitive. I have not shown the slide where you see the water or there is a diffusion which depends on the shape of a zone. For example, light diffuses more when it is passing through a narrow channel. Okay, it depends on the wavelength of light and the channel. Similarly, the analytes which is there in the system, in the microfluidic system, they also diffuse into the matter or the bulks or water around it, and that diffusion is different when it is a bulk system and when it is a microfluidic system. Okay, so in a bulk system it is more like a point source. They become like a point source, while in microfluidic system they diffuse in a very systematic way, like a parallel wave. Okay, just to you to picturize or imagine it. So that way it is very difficult for any analyte to miss out in a microfluidic system. There are chances that our electrochemical detection system will catch hold of that. So the sensitivity, suppose you are doing for analyte, it will be definitely higher, okay, because of the way diffused to the required surface. Also, if you are doing an interference study, that effect also will be pronounced in the microfluidic systems. So that is advantage of microfluidic system, and it is always more sensitive.
Thank you, sir. Thank you. Abhyavartan, there are two
Welcome.
questions in our chat box. Can you take it one by one?
yes, ma'am. So the first question is from Rohit Sharma. So does your lab have Langmuir plotted facility?
So this is not related to my talk, but yes, I do have the language alert system in our lab. And like I showed that Wilhelmy plate, so I told that, we use that Wilhelmy method in the language alert system also. And in fact, I have worked in collaboration with the people in Shivnadar and also in your institute uh, on this language alert system. If you have a good problem, you can always approach me.
Thank you, sir. And one final question from Ashish Gupta. What kind of biosensors are better, enzymatic or non-enzymatics?
It depends on the analyte. See, enzymatic enzymes are, you can see enzyme as a nature's gift to us. Okay, but nature has gifted us something which nature has made. For example, glucose and cholesterols are synthesized in nature, so you will find their enzyme corresponding to it. But chemicals like bisphenol or many other chemicals, you will not find in nature. Urea is not natural. There are many systems which is not natural. So, sorry, urea is natural. So there are many systems which is not natural. So you will never find an enzymatic or corresponding enzyme for it. So you will have to go for non-enzymatic sensor for it. So it depends on what analyte you are using. If your analyte is something which is natural system, go for enzymatic system. But if it is not natural, you have to go for non-enzymatic. We don't have a cell culture facility, and we don't do that cell culture with the blood. We have made an artificial blood. Toxicity study we are not doing right now, but and until being the physical lab, lot of ethical clearance are required for all the studies. So probably will not be doing it in NPL at least. Toxicity. Yeah.
Thank you so much, sir. Ma'am, so we can move on to the next segment.
Yes, please.
I just wanted to, Dr. Agarwal, thank you so much for your talk. In fact, for accepting our invitation in such a short span of time.
Yeah.
Couple of questions. I know NPL does this methodology work a lot. So, do you provide services like, say, I make a biosensor and take it to you and validate such kind of services? Do you provide such kind of services?
Ma'am, it depends on, see, NPL works for the services in two modes. We can validate your biosensors, but we have to first study, and the NPL do provide services for this. You can always come to NPL for validation of your biosensor, but it depends on what kind of validation you are looking for in your biosensor. For example, are you looking for its electronic validation? Are you looking for how much current it is generating, that kind of validation? Or are you looking for that sensing element, whether it is converting? So you have to really define your point of validation. We cannot just say that this is measuring this much of glucose.
Like, is it there in the website, like that these kind of, like?
No, it is not there. So these kind of things are consultancy projects.
Right, because you started your talk with BP kit and all, because there are textile research associations like Citra and Nitra,
yes,
who does these kind of antiviral, these antimicrobial testing for your
yes, NPL is
samples
coming
and
in a
all.
very short time. Yes, ma'am. NPL will be coming very shortly with this test, but specific to NPL already has facilities for wear and tear and fuse tests. But for this PP related, because it's COVID related thing, and during that time the government wanted us to take up this kind of projects. So we have already initiated, and very soon NPL will have this test coming up.
And one more quick question on your like the PDMS, the flexible microfluidics. So PDMS is inherently hydrophobic. So how
Yes, ma'am.
often do you face this issue with biomedical application, because the flow of fluid, it needs to be done in a hydrophilic environment? I mean,
Yes, ma'am.
I'm
It's
sure a functionalization is needed.
Functionalization very much needed, and these days people also come up with the PDMS. You add something to the PDMS and make it hydrophilic. So those kind of solutions are also there. So yeah, initially this is, I would say, one of the major problem with the PDMS, and also it is somewhere good also that it doesn't hold on to that liquid. Otherwise, you will always have uh, lot of resistance in movement of water will also be there if it is really hydrophilic. So that way, it is a blessing in disguise. It does have a problem, but as I said, it is taken care by a good flow meter, or not flow meter, just good syringe pump. With a good flow, the problem is taken care.
Thank you so very much. Thank you for accepting our invitation.
Okay, thanks a lot.
So now, ma'am, can we move on to the next one? You have 12 minutes to present, which will be followed by 3 minutes of question and answers.
Okay. Thank you.
You may.
My screen is visible.
It's yet to come, better. Welcome, Monica.
Thank you, ma'am. Is it visible now? Let me know if it is.
Yes, it's
Was,
visible.
is it visible, ma'am?
Yes, Monica, it's perfectly visible.
Okay, ma'am. Good afternoon, everyone. Myself, Monica Jaswal. I'm PhD scholar at AINT, Amity University, Noida. My today's topic of our talk is modified graphene in gas sensing application. So let us start with the basics, like what is it visible? Okay, yes. Let us start with the basic. What is a sensor? As we all know, sensor is a device that will give an output signal when it will be exposed to targeted physical entity that is meant to be detected as output signal by changing any of its properties. Need of gas sensor is at many fields, like for environmental monitoring, for leakage in industries, for in agriculture from crops to food packaging, in space application for survival of humans, in healthcare to diagnose various diseases through human breath. There is an administration called Occupational Safety and Health Administration, OSHA, which sets limit for the amount of chemicals that can be exposed to workers during their 8-hour work shift, which is called Permissible Exposure Limit, PEL. PEL limit for few of toxic gases is shown in the slide. Like for ammonia and carbon monoxide, it's 50 ppm. NO2 and SO2 have 5 ppm, etc. So these are the standards that are set by OSHA for standard working of gas sensors. So how does it work? For sensing measurement, first of all, we synthesize nanomaterial or nanocomposite. Then we deposit a film by drop casting method, and we place it inside the sensing chamber. This is the sensing chamber facility present at our lab, and it's being kept inside sensing chamber, and it is connected with the few gas inlet, a vacuum pump for removal of gas from a sensor element, a heating controller to control the temperature of sensor, which is embedded inside the sensing chamber. Range is around 350 degrees Celsius. It can be connected to LCR meter to detect the change in resistance or capacitance, whatever parameter we are measuring. So my work is based on resistive sensors majorly. So the sensing parameters that are measured during gas sensing are response time and recovery time. Response time is how much time the sensor takes when it is exposed to the targeted gas. Recovery time is when the gas is removed from its environment, how much time it will take to come back to its initial position for next cycle. Sensitivity shows the presence of increasing, decreasing concentration of targeted gas. Repeatability is how long you can use the same sensor for detection of same gas. Selectivity is that sensor should not get confused between the targeted gas and other interfering gases, including humidity interference, and operating temperature range. So calculation of response for resistive gas sensor is usually done by this method, RA minus RG by RA, where RA is resistance of sensor in air and resistance of sensor in gas. So this is the response percentage we calculate during the study of gas sensors. Why we use modified graphene? Because in pristine graphene is also able to detect various toxic gases in its environment, but it suffers from various various disadvantages like poor selectivity, poor repeatability, and high response and recovery time. And it also damps after few cycles. The response percentage damps after few cycles of same gas. So in my work, we have used intercalation compounds for multi-layered graphene. Intercalation compounds are formed by insertion of atomic or molecular layer of different chemical species called intercalant. And it will it goes inside the layered host material and sits there. So this compound is called intercalation. So here we used multi-layered graphene and we intercalated chromium trioxide inside the multi-layered graphene using HCl. So the ratio of 1:2:1 was kept at room temperature in light room for 120 hours. The process is very simple and cost effective for synthesis of this intercalation compound. After this, the characterization results showed that intercalation was done successfully in XRD. The peaks shows intercalation of second stage that was calculated. And SEM images shows a pristine graphene, multi-layered graphene with only presence of carbon and oxygen in it. And when chromium was intercalated inside it, the EDEX shows presence of chromium by 20.63 weight percentage and 5.82 atomic percentage. EDEX area scan also shows presence of chromium in after chromium intercalation in MLG. SEM images shows that the layers of multi-layered graphene have increased. The interlayer distance has been increased from 3.36 Armstrong to 4.83 Armstrong. This has been calculated using embedded machine in TEM, and EDEX of TEM also shows presence of chromium. This shows successful intercalation of chromium trioxide in multi-layered graphene. Then material was tested for all other interfering gases, and it was observed that it was highly selective for ammonia gas. But at room temperature, it showed high response. As you can see in B figure, the response for ammonia gas is very good at 30 degree, 60 degree, 100, although recovery was not observed at room temperature. So operating temperature was increased up to 180 degrees Celsius, and it was observed that at 180 degree, recovery was achieved at 100%. 100% recovery was only obtained at 180 degrees Celsius, although response is almost equal at all the temperatures. So 180 degree temperature was set as an operating temperature for gas sensor. Then multiple cycles were performed at 180 degrees Celsius, and it was visible that sensor is repeatable for ammonia gas at 180 degree. To calculate response and recovery time, there is one plot with response and after removal of ammonia gas from sensor environment. 100 ppm of ammonia gas was exposed to chromium intercalated MLG, and it was visible that response time was calculated to be approximately 10 seconds, as shown by TS, and recovery time was approximately 40 seconds, and response percentage calculated was 90%. Sensitivity of sensor element was tested up to 1 ppm of ammonia gas, and it showed a response of approximately 8% for exposure of 1 ppm ammonia gas at 180 degrees Celsius. So the sensitivity was studied up to 1 ppm. Then for humidity interference also, sensor element was exposed to increasing humidity at room temperature from 10 RH percentage to 80. And it was visible that at 30 degrees Celsius, although the response was high, but since operating temperature of sensor is 180 degree, so at 180 degree, the humidity interference was very negligible. Stability was also studied for 280 days, and there was a very slight, less than 5% of response was degraded in 280 days of repeatable testing of ammonia gas. So it is stable for a longer period of time. Mechanism for gas sensing was studied as since chromium trioxide intercalates in between the multi-layered graphene, and when ammonia comes, it will attract because chromium will donate electrons to graphene layer, and those electrons will attract ammonia molecule since ammonia is an electron withdrawing.
Monica, I think your voice is not coming. Are you disconnected? Seems she has some network issue.
Dr. Mittal, will you please contact Monica? Dr. Mittal?
I think she has some network issue. Now she is unshared.
She is disconnected right now.
Right.
Dr. Mittal, can you please call Monica Jaiswal? Okay, let me try calling her. Meanwhile, is Monica Dubey? Can you just see if the other speaker is there?
Ma'am, Monica Jaiswal, I just received a message for her. She is disconnected. She is trying to connect through hotspot. Just give her one more minute.
Okay.
Let her try. Otherwise,
अब किसका रह गया मोनिका?
sir, actually, Monica Jaiswal is presenting. She is about to finish, but unfortunately, she got disconnected. Now she's trying to connect. For last talk is for this session is by Monica Dubey.
Ma'am, you please start with Monica Dubey. She's writing that she's unable to connect.
Okay, okay, fine, fine. So, Abhyavartan, let's start with Monica Dubey.
So just in case audiences, you had any queries what Monica Jaiswal was presenting, you can write in the chat box. We can convey it to her. Or even she may see once she joins.
So finally, we have Dr. Monica Dubey, who is currently an assistant professor in IIMT College of Engineering, Greater Noida. She had submitted her PhD thesis in nanoscience and nanotechnology from Amity University, Noida. She has 1.5 years of experience as a lecturer at Royal College of Science, Dombivli, Mumbai. 1.5 years of experience as senior project fellow in CSIR, Central Electronics Research Institute, Pilani, Rajasthan. 6 months of experience as a project fellow in CSIR, Central Electronics Research Institute, Pilani, Rajasthan, and 1 year of experience in packaging sensor devices with low temperature co-fired ceramics technology in hybrid microcircuit group of CSIR, Central Electronics Research Institute, Pilani, Rajasthan. Her research interests include semiconductor technology, modeling, simulation and fabrication, MEMS devices and sensors, and packaging, nanomaterial synthesis, characterization, coating, dyes, industrial pollutant removal and detection, electrochemical sensor fabrication and applications for sensing, catalyst, photocatalyst, and water treatment. She has published papers in international journals, given 8 international and national conferences, and has 2 patents. Today, she will be giving a talk on the applications of magnetic nanocomposites for the degradation of chlorinated organic pollutants. On this note, please join me in welcoming Dr. Monica Dubey to the platform. Ma'am, you have 12 minutes to present, which will be followed by 3 minutes of question and answers.
Thank you, Abhay. My screen is visible.
Yes, ma'am.
Okay, thank you, Abhay. I'm very thankful to the MIT Institute of Nanotechnology for providing me this opportunity here in this workshop. Topic of my talk is application of magnetic metal oxide nanocomposite for the degradation of chlorinated organic compound. These are the contents of the talk. And for the
Monica, can you put
introduction
it on a
purpose,
slideshow mode? Please put it on a slideshow
yes,
mode.
ma'am, it is.
No,
Ma'am, it is already in slideshare.
no, it's not in slideshow mode, Monica.
Ma'am, again, I'm trying.
Please do it.
Is it in slideshare mode, ma'am? Uh,
Not yet.
Hello?
Not yet. No, not yet, not yet.
I think let
Now?
her continue. Let her
Okay,
continue.
please continue. Please continue.
Okay. As we know, water is very crucial and most abundant natural resources for the life on our planet. And reliable, accessible, and clean water for our consumptions are less than 1% of the whole water on presented on the earth. and simultaneously rapid growth, industrialization, population growth, and bulky urbanization. These also affect our water quality, and so water pollution has become a major environmental issue because of existence of a highly complex compound in water bodies. The discharge of industries contains 40 to 60% organic compound. These organic compounds contains 5 to 10% chlorinated organic compounds. And these chlorinated organic compounds are very toxic to the environment as well as for human life also. And they are carcinogenic and genotoxics. They persist in soil, and they also affect the flora and fauna for a long time also. Here for the chlorinated organic compounds purpose, in my work, I have selected two chlorinated organic compounds, 2,4-dichlorophenol and chlorobenzene. These organic compounds are highly used in the industries like pulp and paper
Monica,
industries.
sorry to interrupt you. Have you changed your slide?
Yes, ma'am.
We are seeing the introduction slide only. Okay, now I see it.
Monica, ma'am, I have shared the PPT with you. Will you please share?
Okay, you can continue, Monica. Monica Dubey, can you hear me?
Monica, I'm sure. I think she has some.
Yeah, maybe she's having some issue.
That's what she's asking me to share. Our screen is visible now. My screen is visible now.
Your screen is visible, Monica, ma'am.
But where is she? Let me call.
Monica, ma'am. Monica, ma'am.
Yes, ma'am.
Monica Jaswal has joined. Can
Yes,
in that case,
she is joining. I think she is.
Ranu, let her finish and then we will come back to the Monica.
Yeah.
ask
She
her
is
if she's
joining.
not able to do. We can do her talk tomorrow also. Just for, once you call.
No, she is mentioning that she is joining. No load at work.
No, she is already in. Actually, Monica Dubey is already in, but we can't hear her.
Just a minute. Give me one.
Monica Dubey, can you hear us?
She has again joined through another network. She will start now. She can start now.
In that case, IT person, can you please make Monica Shukla as the co-host? Yes,
Yes.
thank you so much.
Hello.
Yes, Monica. Now you are audible.
Yes,
So now
ma'am.
tell
Yes,
me.
ma'am. Yes, ma'am. So for the solution, magnetic metal oxide nanocomposite are low cost and they are also stable. And the most important is they can recover after treatment easily, just applying the magnetic field outward, and they can be collected. And they have high absorption capability also, so that they can absorb impurity at its skin. And uh, if we see the magnetic compounds, they this magnetite is the room temperature. Please forward the slide. Uh, I have selected 12.5 pesticides, and insecticide. They are also used in dyes and paints industries and in also pharmaceuticals industries. After the use, these compounds are discharged into the water bodies, and they are highly toxic for the human health. Even the conjunctions of 2,4-dichlorophenol for an adult. So and some mutagenic also hardly.
I think she has some network issue, Matuza. She is
हो
not.
सकता है हो सकता है
Ma'am, please.
Yes, you can continue now, Monica. Should I move forward?
Yes, ma'am.
Fine.
अगर भीग जाता है तो ठीक
So here I have synthesized nanocomposite of magnetite and octahedral molecular C magnesium oxide that is called alpha amino 2 also. So they are using reflex method synthesized alpha 1D nanowire alpha amino 2, and after that was mixing using co-precipitation method with the magnetite. So here in and after that it material has been characterized. Here in XRD image we can see the synthesized nanocomposite has the peak of both metal oxide magnetite and magnesium oxide both. In the TEM image we can see there are the two phase of the nanocomposite. One phase is the nanowire which are related to alpha amino 2, and the nanoparticles which are related to the magnetite. Material has a high magnetism at the room temperature and can be easily recoverable just after applying the magnetic field from outside. And this material also has the photocatalytic property for the degradation of both chlorinated organic compound in the presence of visible light as well as in the presence of uh, sunlight also. So first material was applied for the degradation of 2,4-dichlorophenol. Here we optimize the parameter like concentration, time, pH, and amount of the catalyst. We found that 100 ppm of the 2,4-dichlorophenol has been 100% degradable within the 80 minutes in the presence of UV visible light at 9 pH. So and material is also reusable, and we applied it successfully for the degradation of 2,4-dichlorophenol up to 5 run, and found that material is still stable and has the all peaks uh, as one as all peaks were present in the fresh XRD of the synthesized nanocomposites. The absorption power, UV visible light degradation, and degradation in the presence of sunlight all are compared with the alpha amino 2 magnetite and nanocomposites. Nanocomposites was found highly has absorption power and at room temperature, and 100% degradation of the 2,4-dichlorophenol uh, within 80 minutes in presence of UV visible light, and almost found 78% degradation in the presence of sunlight. Next slide, ma'am. This material is also applied for the degradation of chlorovengine and found the 100% degradation of chlorovengine using 100 milligram per liter nanocomposite at similar pH 9, and material was here is also stable and easily recoverable just applying the magnetic field from outside. Next slide, ma'am, please. Here we can see in the XRD graph of the uh, uh, of the graph. One is fresh nanocomposite, and another one is after the reaction, five run of the reaction. And we can find there was all peaks or almost present in the graph. Next slide, ma'am, please. So for the conclusion, this material, alpha nanocomposite of magnetite and alpha amino 2 is an excellent photocatalysis in the presence of UV visible light as well as in presence of sunlight. And material has 100% degradation of 2,4-dichlorophenol and chlorobenzene within 80 minutes. And it also has a outstanding absorbent activity, and this is extremely stable and recoverable magnetic nanocomposite. For the reaction purpose, this magnetic nanocomposite follow the first order kinetic reaction within just 10.45 minutes. Was the half time reaction. Next slide, ma'am, please. For the future avenue, magnetic nanocomposite have high absorption capacity against the pollutants, and they also have easy separation from the water pollution. So they can be applied for other industrial pollutants like dye and other organic compounds, and somehow some for inorganic compounds they are also applicable for the removal. This this material, this synthesized material, and this study also has a pathway for the degradation of other organic compounds, their removals in water for the point of care applications also, or for health safety issues also. Uh, Thank you so much. I'm very thankful to the AINT department to provide me this opportunity again.
So thank you so much, Monica, for your detailed study on iron magnetic nanocomposites. With this, over to you, Abhyavartan. I think if Monica Jaiswal, you want to...
We will do for her tomorrow.
Okay,
we have
fine.
to wrap up. We have to keep our timings. We'll get late today otherwise.
In between that, the assessment link is floated in the chat box. I request all the participants, please copy the link, because it will be not visible after 5:30. I request IT person to please upgrade Dr. Richa Krishna. IT fellow, please upgrade Dr. Richa Krishna. Over to you, Abhyavartan.
Thank you, Dr. Monica Dubey, for your talk. Now I request Richa ma'am to summarize the morning session, followed by Monica ma'am to summarize the post-lunch session.
Thank you so much, Abhyavartan. So today morning session, that was pre-lunch, we had 5 talks. First talk was by Professor P.K. Bhatnagar from Delhi University. He talked about some smart nanomaterials, their potential applications, and the hazards posed by them. And he also talked about the modus operandi of these nanomaterials. Then the second talk was about the conventional diagnostic tools and their comparison with the point of care tools for leukemia. Dr. Suman Lata talked about some of the conventional techniques which are still better than the current tools. 2 of our young speakers presented their cutting-edge research. Dr. Shaheen talked about the synthesis of silver nanoparticles using cyanobacteria and its applications. Then Ms. Mosam Chaudhary talked about the sustainable polymer nanocomposite, and she also educated us about some of the government norms and required certifications for recyclable and biodegradable plastics. Then Dr. Anjana Dogra from National Physical Laboratory talked about the role of thin films for societal applications. She talked about some of the sophisticated and very sophisticated techniques for developing thin films and the whole mechanism which goes in the formation of thin films. She also discussed the importance of growth parameters in deciding the quality of the films. This was all about the morning session. Now I invite Dr. Monica Joshi to give the summary of the post-lunch session.
Thank you so much, Dr. Richa. So the third day post-lunch session is full of learning, which includes the diverse application of nanotechnology in various areas. The first talk was in that second session we had 5 talks, 3 by our eminent speakers and 2 are by our young scientists. The first talk was by Dr. Prashant from Delhi University, who gave a very elaborative talk on the computational tool in finding inhibitor against protease of SARS-CoV-2. The second talk was given by Dr. Amarpal Singh from a Forensic Research Laboratory in New Delhi. He has discussed the application of nanotechnology in forensic science. Also, some of the challenges that the forensic experts are facing and for the analysis and how nanotechnology can help on that. The third talk was given by Dr. Ved Varun Agrawal from National Physical Laboratory, New Delhi. He has covered a detailed aspect of nanotechnology for biomedical applications. After that, we had 2 young scientists. The first talk was given by fourth talk was given by Miss Monica Jayaswal. She gave the application of nanotechnology on gas sensors, on the resistive gas sensors, and the work that she had done in her lab. The last talk of the day 3 session 2 was given by Miss Monica Dubey. She had given her presentation on the application of magnetic nanoparticles on water remediation, especially the chlorinated organic pollutants. So it's full of learning where we have really learned a lot of things about the various applications of nanotechnology for the society. I hope all the audience would learn a lot of, and they have gained a lot of knowledge from the various talks since morning. With this, I would like to thanks all our committee members, all the organizers who gave me a chance to coordinate this session. And for the audience, please copy the assessment link. Over to you, Dr. Rana.
Thank you, Dr. Joshi. Thank you so much for well handling this entire post-lunch session. And another thanks goes to Dr. Richa Krishna for handling the pre-lunch session. Along with that, our special thanks goes to Abhyavardhan Selvam and Monica Jaiswal for doing the mic coordination today. And again, as usual, like the last 2 days, today's talks were also excellent with eminent speakers and a lot of interaction from the audiences. So this is what we are expecting, more and more interaction from you. So today it's already time. Unfortunately, we could not wrap up all the talks today. So for Monica Jaiswal, if anybody has any question, you may put in the chat box tomorrow. We will convey it to her. That is on gas sensors. Unfortunately, it's already time, only 4 minutes left for 5:30. So we will be wrapping today's session. Again, I request everyone to copy the link for today's assessment, and it remains active till 11 p.m. And tomorrow's talk, the first talk is going to be by Dr. Pika Jha from DRDO SSPL, New Delhi. And please join us at sharp at 9:30 a.m. So thank you all. Have a blessed evening. IT, you can, I think, close the session now.